this year. But
Okay.
all the plenary speakers and the half plenary speakers are exempt from this because
Right.
they all deserve the prize. So
Yes.
we know that you're going to give a very nice talk, and it's maybe 2 a.m. in New York now, yes?
Yes. Yes. It's 2 a.m.
You look very dynamic, yes.
So far, so good.
Okay. Now,
I usually
just
stay till 2 a.m., 3 a.m. every night.
okay. Now, the award that I am going to announce is that every day we will have a ballot box somewhere here. I have 5 colleagues appointed, but anyway, they will probably come, and I will repeat this announcement at some time. So every day, each participant has a one vote to select the best presented oral presentation. Each day we will collect 5 best presented oral presentations. And the closure, we will select one of them as the best selected oral presentation. So the winner will be awarded 500 euros in cash, and we will prefer in-person participant because we cannot give this to online participant.
Okay.
Plus, it will be registration fee waiver for the next ICQMT. And hope this will be a tradition for the next ICQMTs. Maybe you can repeat this if I have explained it enough. Yes. Yes.
Yes. There is going to be a competition among the presenters, right? As far as I understand.
Yes.
And as a result of the competition, there is going to be an award towards the end of the program for the best presenter among the competitors.
Yes, but the plenary and half plenary speakers are exempt. They are not
Yes,
nominees.
yes.
Because they are
Plenary
already
speakers
best selected.
will not be included in the competition.
Okay.
Yes.
I think that's what I'm just telling. Oh, good morning, Paul. I think you were supposed to sleep 2 more hours. Right. Good. I hope you relaxed. This has been recorded on YouTube also. So we are expecting Laura maybe as a co-chair. Okay. Thank you. Gençler.
Today we are continuing with the second day of our program with again exceptional talks in our plenary session number 2. We start with Professor Ivan Bozovic from Brookhaven National Labs. He is at the same time an adjunct faculty member at Yale University. He is going to talk about electronic pneumaticity in cuprates and why is it crucial. The floor is yours, Professor Ivan.
Yes, thank you. Okay, let's try to share the screen. Can you see this? Can you see my screen?
Yes, we can see it.
Okay. Well, I wish to thank to Ali for this invitation. I am sorry that I cannot be with you for several reasons, one of which is that I'm actually still recovering from COVID. Anyway, distracted by COVID, you may have not, okay, let's see whether this works. You may have not noticed that the highest impact journals like Nature and Science have been flooded with papers on electronic pneumaticity. Nevertheless, this notion defies the common textbook knowledge of condensed matter physics. And given the abundance of high impact or hype impact discoveries and reports, I think it is prudent to question what, if any, of this you should actually believe. So in this talk, I will try to answer that question. There will be one more collateral benefit for you. More likely than not, like me, you have also encountered a particularly stubborn referee that is standing in your way to fortune and glory. And I will show you one strategy on how to fight back. Metals. Our understanding of metals was pioneered by Paul Drude more than a century ago. He imagined a metal as a gas of free electrons contained in a can. And this model was refined by Lorentz and Sommerfeld and later justified theoretically by well-known Landau's Fermi liquid theory. This theory successfully accounted for all of the key properties of metals, and in particular, the electric resistivity, which was attributed to scattering of electrons on impurities, structural defects, phonons, and other excitations. Now, indeed, one would expect a gas to be isotropic. To be more precise, all the physical properties of a given crystal, including the electronic conductivity tensor, effective mass, scattering rate tensors, they should all have the full rotational symmetry of the underlying crystal lattice. Now, we know of example where the rotational symmetry is spontaneously broken, and that's what happens in liquid crystals. Liquid crystals, when they were discovered, were also considered very strange because they flow like liquids, but are anisotropic like crystals. By now, the microscopic explanation of this is well known. Liquid crystals consist of rod-shaped molecules, and their attractive interaction, the cohesion, pulls them towards one another, favoring the closest packing. This is achieved when the rods align parallel to one another, and this is what breaks the rotational symmetry, and that's why liquid crystal, for example, polarizes light along one direction, etc. Now, much more recently, theorists envisioned electronic pneumaticity, which is analogous to the liquid crystal pneumaticity in the sense that there is a spontaneous breaking of rotational symmetry, but electronic pneumatic is spontaneous breaking of the rotational symmetry just in the electron fluid and not in the crystal. Needless to say, many people, including myself, first, when you hear it the first time, it sounds very counterintuitive. Because electrons in a metal run at enormous speed, like several hundred kilometers per second in cuprates, and they scatter on the femtosecond time scale in all directions, and they are not banana shaped. So how could they possibly be nematic? And the emergency exit is that experimentally, cuprates are quite unlike ordinary metals. For one, the single particle approximation fails. Cuprates are strongly correlated metals. They are doped multi-insulators. And indeed, they show many anomalous properties, including resistivity. Here is an example of a very good lanthanum-strontium cuprate film grown by molecular beam epitaxy. And what you can see is that resistivity is linear in temperature, up to 1000 Kelvin, which is not shown here. And this is quite unexpected because in a standard metal, resistivity should go as a third or fifth power of temperature, and then it should curve upwards, and then it should saturate at higher temperature. And more disturbing, if you use a Drude model and calculate the mean free path from this model, then you will conclude that at this highest temperature, the mean free path is shorter than interatomic distance. And now, if you go the other way to the low temperature, then in the sample, upon cooling down, the resistivity extrapolates to 0. And now, from the model, you would conclude that there are no defects or impurities. However, in lanthanum-strontium cuprate optimally doped, we have one strontium 2 plus replacing lanthanum 3 plus, and the spacing so it's a charged impurity, and these charge defects, they are spaced at about 8 angstrom from one another. And the mean free path that you would infer even from the upper limit on this residual resistivity would be like 1,000 times longer. So what we infer is that at low temperatures, the electrons do not scatter on anything, while at high temperature, they scatter on nothing, on vacuum. And this, of course, is absurd. The only sensible conclusion is that the standard Fermi liquid theory fails spectacularly. The right plot here shows the dependence of resistivity on magnetic field strength, and it also becomes linear in high fields and doesn't saturate up to the highest field we were able to measure, which was 80 or 90 Tesla. And this also is unlike in ordinary metals, where it should be parabolic, and it also indicates the breakdown of the Fermi liquid theory. But that's not all. There are many other properties that are also anomalous. The ones that I'm familiar with are infrared absorption, electronic Raman continuum. Those in good metals die out on a scale of, let's say, 50 inverse centimeters, which may be like 4 or 5 millielectron volt. And the reason for that is that the momentum is well defined in one band and in the other band, and the moment of the quasi-particle, and the momentum of light is basically 0, so the transitions are vertical. And that's why with the momentum, the infrared absorption dies very fast in metals, and so does electronic Raman continuum. But in cuprates, both of these extend to at least 1 electron volts and beyond. And what that tells you is that actually the quasi-momentum is ill-defined or completely smeared out. And there are these other probes that I will not comment upon, but basically, whichever other way you probe it, the normal state, normal metallic state in cuprate is everything but normal. And this was in plane. All what I was showing so far were in plane properties. But if you look out of plane, things look even more strange. Basically, the cuprates, when you look with the light which is polarized parallel to the copper oxygen planes, they look like metals, maybe bad metals or strange metals, but metallic-like. But if you look perpendicular to it, they look like kitchen salt. They are insulators, strong insulators. And if you have read the book by Phil Anderson about high temperature superconductivity, he has extensive discussion arguing that localization is a quantum interference phenomenon. So material cannot be Fermi liquid in plane and not perpendicular to it, or along the chain and not perpendicular to it. It's either 3D very anisotropic Fermi liquid or not. While okay, be that as it may, we have found experimental evidence. This is work in collaboration with Doug Natelson at Rice University by shot noise measurements, which directly measures the charge of the carriers that tunnel in tunnel junctions, which were lanthanum strontium cuprate based. So what we found is that a large fraction of electrons remains paired deep into the so-called normal state. That means at temperatures well above Tc and at energies way above the superconducting gap. And this, of course, is a very tough challenge for any Fermi liquid or BCS type theory. Okay, so while ordinary metal cannot be nematic, perhaps a strange metal could. And with this motivation, many experimental groups looked for signatures of electronic nematicity in cuprates and other strongly correlated materials. And lo and behold, when you look for something specific, you will see it. And indeed, many groups reported seeing nematicity in various high TC cuprates like YBCO, BISCO, lanthanum strontium cuprate, using various techniques. Here, I will focus on only one that I have been directly involved with. We call it angle-resolved measurements of transverse resistivity. So here is a little theoretical background. Imagine that you have a material which is tetragonal, then its resistivity tensor can be drawn as a matrix, and this matrix must be diagonal because every direction is eigenvector for the current because of the rotational symmetry. And then this matrix will stay diagonal no matter how you rotate the axis. On the other hand, if the crystal is orthorhombic, then this matrix is only orthogonal, only diagonal in the so-called principal axis coordinate system. If you rotate the current direction azimutally, then the current vector is not eigenvector anymore, and that means that off-diagonal matrix element must be non-zero. And if you go through this trigonometry quickly, you will find that as you rotate the azimuth angle, the off-diagonal matrix element must oscillate with period pi. It means that it will have 4 nodes. And what you can also see from this expression is that longitudinal resistivity oscillate around some average value. And if the amplitude of this oscillation, delta rho, is much smaller than rho, the average value, then this oscillation may be buried within the noise. Because when we measure a lot of different devices, let's say in different angles, then inevitably there is some device-to-device variation due to lithography, etc. And therefore, your signal to noise may be not good enough to pick up nematicity if the amplitude of this if the difference between rho A and rho B is small. On the other hand, the transverse resistivity will show that clearly, because if the crystal is tetragonal, then transfer voltage must be zero by symmetry. And then as soon as you see non-zero transfer voltage, that indicates that the C4 symmetry is broken, that the system, the crystal is not purely tetragonal. And this must be true for every orthorhombic crystal. And for this reason, we invented a new technique that we call angle resolved transverse resistivity measurement. So we grow a film, lanthanum strontium couplet film, by atomic layer by layer molecular beam epitaxy. Then we pattern it into what we call the sunbeam pattern. Looks like this. It actually consists of 36 hole bars, and we run the probe current along the hole bar, and then we can measure the longitudinal resistivity between, say, contacts 3 and 5 or 5 and 7, and the transverse resistivity between 3 and 4, 5 and 6, or 7 and 8. There are 36 hole bars at 10 degrees from one to the next. Hence, we can measure the longitudinal resistivity at 72 pixels and the transverse resistivity at 180 pixels with the angular resolution of plus minus 5 degrees. And here are some representative results for 3 lanthanum strontium cuprate films: underdoped, optimally doped, and overdoped. In each film, you see that spontaneous voltage appears transfers to the probe current. This is just like a Hall effect, except that there is no magnetic field here. What transverse voltage means is that electrons feel some lateral force, which is compensated by electric field from the charges that pile up at the hole bar edges. Now, if the material is tetragonal, the resistivity tensor is isotropic and there is no lateral force. However, if the material is orthorhombic, then the conductivity is highest in one direction, and if you force the currents to flow at a different direction, then there must be a lateral force and hence a transverse voltage. So that's the idea. Now, as you can see here, that as a function of in-plane orientation, both the transverse and longitudinal resistivity show oscillations with 2 periods, 4 nodes. In this plot in upper panel, the solid red curve is the fit of the experimental transverse resistivity data to the function A times sinus of 2 phi minus alpha. But in the lower panel, the broken red curve is not an independent fit. What I did is just translated the top red curve down and to the left by 45 degrees. So the amplitude of oscillation in longitudinal transverse resistivity is the same, while the phases are shifted by 45 degrees, as our little theory predicted. We can also plot this in polar coordinates with the radial distance measuring the amplitude and azimuthal angle being the angle. And blue color denotes the positive and the negative values of the transverse voltage. And this looks like a cloverleaf pattern showing that the four-fold rotational symmetry is broken. However, note that the crystal structure of the film is tetragonal. So one is tempted to claim a great discovery, electronic liquid crystal, a new condensed state of matter. But in America, people say if something is too good to be true, perhaps it isn't. And the bigger the claim, the more one needs to be cautious. And precisely because angle resolved transverse resistivity measurements are so sensitive, they will also pick up any anisotropy that is caused by some extrinsic factors. And for this reason, we assembled a list of all possible artifacts. Some of these are listed here. And then we check them and rule them out one by one through extensive and dedicated experimentation. We have been working on this for 16 years now. We first observed the effect in 2006, but first published it only in 2017, 11 years later. And in between was a tour de force exercise in material science. We did a lot of characterization by any and every technique available to us. And importantly, our accumulated statistics is enormous, with thousands of films and devices, perhaps without precedence in condensed matter physics. Characterization tool that we use every day in situ and in real time is electron diffraction. What it shows is that film is single crystal, no grains, no grain boundaries, atomically smooth, uniform, and epitaxially anchored to the substrate. What the latter means, since the films are very thin, typically 10, 20 nanometers, is that the film must be pseudomorphic to the substrate, meaning that the lattice constant of the film are the same as those in the substrate. We confirm this by read, but also by highest resolution synchrotron-based X-ray diffraction. If the substrate is tetragonal, so must be the film, and they are, as we verified. Now, in Hall effect measurements, there is usually some offset between the contacts. They are not perfectly aligned, almost never. And that means that you will pick up a little bit of longitudinal resistance, even if you are nominally measuring transfers. To show that this is not indeed the case of the nematicity we observe, there is a simple argument, which is a doping dependence. We studied many films, thousands of films, and they are all patterned with the same lithography mask, which means that the contact misalignment must be the same in every film. However, we found that both the amplitude of the nematicity and the orientation of the nematicity actually depend on doping strongly and systematically and smoothly. Here is the same thing except magnified by a factor of 100. What I mean by that is that here we have used technique that we call COMBI, combinatorial molecular beam epitaxy, meaning that we have deliberately created a small gradient of strontium along this central bar. The variation is about 4% on 1 centimeter, which then translates to the doping changed in the extremely fine increments, 1% of 1% for 1 pixel to another. And you can see that there is systematic and linear dependence on doping. And that, of course, rules contact misalignment and pretty much any other scenario that is based on some random extrinsic effect. Rather, I think this points to some subtle changes in the band structure and Fermi level with doping. So we have ruled out the contact misalignment, but are the contacts sonic? Schottky barrier, contact could fool you, as people who do this type of measurement know well. And for this reason, we check this routinely for each contact, longitudinal or transfers in each of the thousands of devices that we have measured. And all the contacts are indeed ohmic, and the contact resistance is in fact quite small. This may sound simple, but it took much experimentation until we developed a robust recipe to fabricate low resistance ohmic contacts to couplate films. Another important test is temperature dependence of the amplitude and orientation of nematicity. What you can see is that C4 symmetry is broken already at room temperature, and that implies that the resistivity tensor is always orthorhombic, even though the films are tetragonal. But as or more important, the orientation of the easy direction, the direction of the highest conductivity, is not aligned with the crystal axis. And it even rotates with temperature. And that shows that an anisotropy that we observe in transport is essentially uncoupled from the lattice. That means that it is purely electronic. Another very incisive probe that we have added recently is transverse magnetoresistance. In zero field, the transverse resistivity has a peak near Tc. When we apply a magnetic field, the resistive transition fans out like this, and the peak in transverse resistivity is suppressed by an order of magnitude. the transverse conductivity increases by 1000%. And for this reason, in analogy to the well-known colossal magnetoresistance, you may call this colossal transverse magnetoresistance. Interestingly, in this sample, we at this field we see essentially no magnetoresistance in the longitudinal channel. But you can also see that the direction of the orientation of the director changes with temperature. In zero field, when you go from room temperature to TC, it rotates by about 45 degrees. But when you put a magnetic field of 6 Tesla, it then rotates back to the high temperature zero field orientation. And obviously, this cannot come from the crystal structure because it doesn't change as a function of temperature, nor for any other random extrinsic factors. Another possible extrinsic factor that we know is there and we know breaks the symmetry is misorientation of the polished surface. No matter how much money you offer, you can never purchase a substrate that is polished with a perfect alignment to a crystallographic plane. Typically, they miscut the orientation by 0.1 to 0.5 degrees. And for this reason, the best substrate will still have some terraces on the surface, which are 1 unit cell tall and maybe a couple of 100 nanometers wide. The terrace steps are 1 unit cell tall. And these steps and terraces, they break the T4 rotational symmetry of the substrate and of the film because the film grows epitaxial on top of the substrate. To check whether this could be the explanation of the transport anisotropy we observed, we studied films of the same composition, like optimally doped, and on a substrate with different miscuts. We measure every substrate before the film growth by AFM, atomic force microscopy, and we determine the orientation of the steps in the film. Then we grow film, then we do AFM again, and we compare them, and lo and behold, the steps in the film are the same as the steps in the substrate. But these three substrates have steps at very different spacing and also different orientation. And nevertheless, the amplitude of the nematicity and even the orientation of the director are about the same. That means that these steps do not matter really when it comes to nematicity. And since we know the miscut angle, we can calculate, we know the in-plane and out-of-plane resistivity, we can calculate what effect would we expect. And indeed, it's like 2 to 3 orders magnitude smaller than what we experimentally measure. So that's not the explanation either. What else? Could it be due to strain?
2 minutes left.
Because
Professor Bozovic.
yes? Okay. The question is whether it could be due to the orthorhombic distortion and strain. And we varied both by using substrates with different lattice constant, like lanthanum strontium aluminate and neodymium gallate. Lanthanum strontium cuprate, lanthanum strontium aluminate is purely tetragonal, while neodymium gallate is orthorhombic, about 1% difference between A and B. So it's a large orthorhombic distortion in by crystallographic standard. But as you can see, the lattice distortion is larger by 1 or 2 orders of magnitude, but the amplitude of nematicity is almost the same in films grown on lanthanum strontium aluminate, which is perfectly tetragonal, and in these lanthanum strontium cuprate films, which are very, very orthorhombic. The only difference is in the orientation. And this also points to purely electronic origin. Okay, the final suspect on my list is lithography. It is conceivable in principle that some steps in our lithographic process may introduce some asymmetry into devices. And to test and rule this out, we develop a different technique that completely avoids any lithography. Rather, we use micro machine shadow mask and deposit gold contacts through the openings in the shadow mask in a circle like this. And then we can use the two orthogonal pairs of contacts, like these two for the current and these two for the voltage, and then we can rotate that in steps of 10 degrees, and this is what you get. It's the same sinus 2 phi sinusoid as we see in films that are lithographically patterned into sunbeam. We have done this with films which were square. We etched also away the outer perimeter to make it a disk, and we have done this with bulk single crystals, so they're not even thin films. And we always see the same effect. And finally, as another logical check, we perform the same type of measurement using the same mask on other materials, quite a few. What is shown here are two, strontium ruthenate and titanium. Strontium ruthenate is like cuprates, a strange metal, strongly correlated, and indeed we have observed an even larger nematicity signal. This is strontium 2 ruthenium 04, 214 structure. And in contrast, in titanium, that's this purple curve and purple line, it's completely flat. There is no signature of oscillation whatsoever on this scale. And this is another logical check because it rules out artifacts from the experimental setup or lithographic mask, substrate, etc. Okay, so so far I have discussed a small subset of artifacts that we have actually considered, examined, and ruled out. And you will find much more in the article that I'm preparing for the conference proceedings. I will take a bet that whatever you can come up with, we have already thought about it and we have experimentally ruled it out. I think that burden of proof is now with the skeptics. It is not enough to hand waves and say disorder or strain. You need to propose a concrete and detailed model and show that it is consistent with all the experimental facts that I've shown and more. So in summary, cuprate superconductors are strange metals. They defy the standard textbook description of metals, which is based on the Drude model and the Landau Fermi liquid theory. Moreover, I think I have made a strong case that cuprates are indeed electronic nematics, that the rotational symmetry of the electron fluid is lower than that of the underlying crystal structure. However, before making such a bold statement, one must systematically rule out any conceivable experimental artifacts and possible extrinsic factors that may break the crystal symmetry. And this calls for some meticulous material science, employing a range of material characterization techniques and studying comparatively and systematically a large set of samples. So in the end, you might ask, why should I care? Well, for one thing, this calls for a critical re-examination of some textbook chapters on metals. Apparently, some metals are qualitatively different from a Landau Fermi liquid. And next, it is quite unlikely that the onset of superconducting coherence could magically restore the full rotational symmetry. In that case, the superconducting state must also be nematic. And indeed, we have gathered some experimental evidence, not published so far, that the superconducting fluctuations first develop in one direction and actually along a copper, oxygen-copper implant bond direction. And this is very hard to reconcile with the standard BCS theory, which postulates Fermi liquid normal state. In any case, this very tightly constrains the correct theory of high TC in cuprates. It informs on the character of the pairing interaction, which appears to be anisotropic. Note that this is quite unexpected. If the crystal is C4 symmetric, then so must be its electron band structure, the spectra of phonons, magnons, other excitations, as well as their coupling. So this may prove to be a crucial issue. Let me end up with some open questions. Good experiment, answer one question and then open many more. Eventually, we would like to know what is the microscopic mechanism of electronic pneumaticity. I have shown no evidence, no hints to that. How is this related to other strange metal properties? How is it related to high temperature superconductivity in cuprates? Can we manipulate electronic pneumaticity, increase it, decrease it, perhaps raising TC and JC in this way? And what we can learn by comparing cuprates to other materials that are showing electronic pneumaticity, strange metal, and other unconventional properties. Thank you so much.
Thank you, Professor Bozovic, for this excellent presentation. Now we can take questions from the audience, if there are any.
Good night, Ivan. This is Amit Kern. I don't know if you can see me. Very beautiful experiment, and I have absolutely no question that the experiment is correct. I just want to suggest something that maybe you considered already and maybe not. Even in the overdose side, there are about 80% of spins that are free. You dope a magnet, LASCO. Is it possible that the longitudinal current somehow polarizes the spins and you actually get a Hall effect from internal magnetism?
Okay, so, what is, my talk was just trying to convince you that electronic pneumaticity is real, because there are still people who don't believe it. And that was my fight. What is the microscopic mechanism? I do not know. But all I'm saying is that it is intrinsic. So every lantern strontium cuprate, every device shows this effect without a single exception. Yes, something must be anisotropic there. I think that we have hints that there is anisotropic electron. Okay, so my guess is that it comes from electron-electron correlations, which of course involve spin and whether spins are parallel or not. There is this pairing that we see well above TC and also well above the outside of the superconducting gap. Now, we also know, you're right there, that even outside of the superconducting dome, there are still antiferromagnetic correlations. They are short-lived and with a very short coherence length in space. So we have done this experiment with Mark Dean and John Hill about 9 years ago, Nature Materials 2013. What we looked there using GRICS is the magnon spectrum. And the magnon spectrum basically doesn't change from undoped to overdoped metallic non-superconducting sample. What changes is the lifetime. So the peak becomes broader, the lifetime becomes shorter, but the magnitude doesn't change. So yes, there are antiferromagnetic correlations. Is that, just saying that is not enough. I think it's a good starting point, but one has to work out how can that break the rotational symmetry on microscopic scales. Our sunbeam is like 5 millimeters. So there is something very macroscopic happening.
Any other questions? Okay, there's one more over there.
Yes, Ivan, I, of course, as you know, believe all your experiments, and this one is no exception. But I have a terminological question, and
Yes.
it is, there is a well-known instability of the Fermi sphere, quadrupolar deformation, which is called the Pomeranchuk instability.
Yes.
Now,
Right.
would you call a system with a Pomeranchuk instability a non-Fermi liquid? Or is it still a Fermi liquid for you?
Well, it's a semantic question, and whatever majority accepts and uses, so do I. I have no preference one way or another, but certainly in the original, formulation, Pomeranchuk instability goes. It is not anymore a single particle description. You have this, pair entanglement in some sense, and maybe more than pairwise. So whatever majority says, typically when people say Fermi liquid theory or Drude model, they don't invoke Pomeranchuk instability. Is that a possibility here? Yes, Pomeranchuk instability may be operational here, but Pomeranchuk instability will, for example, deform the Fermi surface along X and along Y. But these two will still be degenerate. Something has to break that degeneracy here, and on a microscopic scale, like 5 millimeter scale. So maybe it's something much more general than that.
Thank you. I would just
And-
like to
Right. And okay, Pomeranchuk instability, I'm not sure that would explain, for example, what we see in the infrared, what we see in Raman, what we see in tunneling, what we see in NMR, what we see in transport. It will have to be, very strong. And then presumably ARPES would pick it up. And so far they didn't. They don't see any nematicity between, X and Y.
Okay, thank you.
Okay, yeah, I think there's one more
Yeah,
question
just
from
sort
our
of like
moderator.
to make a comment. Yvonne, I wish that you were here because I'd love to talk more with you about this in person. And your talk was fabulous. Thank you very, very much. We used to disagree on nematicity, and I think we're on the same page now. But in response to the
Yeah, well, I think it works in favor of my talk because Laura is my witness, and so is Seamus Davis, that I was very vehemently opposing it as long as I could. It took me like 10 years to say, okay, it's a hammer to the head. I see no way how I can wave this away. It just didn't want to go away.
science wins, but I just
Oh yeah, I think it's real. I think it's real.
wanted to add one thing, which was that one of the questions was about Pomeranchuk instability. There's two main theories about what causes the nematicity, and one of them is spin-spin correlations, and the other one is orbital ordering. And I was involved in orbital ordering. I actually think they're both correct, and this was for the nematic phase in the iron-based superconductors. And so, so I'm actually having trouble hearing you because the speakers are placed funny, Ivan, but maybe it's my own hearing, yeah, okay. But I just wanted to, so sometime we can talk about these two different theories and compare your cuprate data to some of the old iron-based superconductor data. But it was very, very, very nice, thank you.
Oh. Well, I think different, the transport measurement that I have shown here will not answer that question. If we are talking of orbital ordering, I would more hope that the state-of-the-art X-ray scattering experiment like RIX and things like that may detect, for example, orbital ordering if it's present. As for the Pomeranchuk instability, off top of my head, I don't know a good experiment that would directly probe that. But will think about that.
Yeah, we'll discuss it sometime, but it was just a great talk. Thank you.
Thank you.
Okay, thank you for all the questions and comments. I think now we continue
Oh,
with...
yeah, let's thank Professor Bozovic again. Okay, moving on with great talks, I'm sure. Our next speaker, are you present or online? Yeah, hi, nice to see you. So it's Roland Weisendanger from University of Hamburg, Germany, and the title is Bottom-Up Design of Topological Qubits for Robust Quantum Computing.
One, two, three. Okay. Yeah, good morning. First of all, let me thank for a very kind introduction. And of course, I would also like to thank the organizers for a very kind invitation, and especially Allegenza for having organized another wonderful meeting. Thank you so much. So for my talk today, I have decided to focus on a topic which is very relevant these days, quantum computing. And I would like to discuss the bottom-up design of topological qubits for robust quantum computing. Now let me first motivate what I'm going to talk about. So as you all know, it was only 5 years back in time when IBM announced the first universal quantum computer for business and science. And that time, there was a 16-qubit processor, you can see it here, consisting of superconducting qubits. And very soon after, in the next years to come, actually the number of qubits could already be increased to 53, and then even up to 70, and now we are already above 100 qubits. And companies like IBM and Google could also demonstrate quantum advantage. That means that you have advantages of using the quantum computer compared to classical computers in solving very difficult problems. Now, the scaling up in terms of the number of qubits is full under control. The hardware is sophisticated, but it's based on cryogenic technology, which is available, of course. And no matter if you look at the hardware design of IBM or Google, of course, it looks quite complicated, but that is just as in the early days of classical computers. That's not the major issue. The major challenge ahead in quantum computing is actually visualized here on this slide, which is actually from IBM. And here on this slide, you can see basically cubes which represent the so-called quantum volume. The quantum volume represents basically the performance of a quantum computer. And this quantum volume is actually plotted as a function of the number of qubits here on this axis and the error rate. Now, what does this diagram tell you? It basically tells you that if you start, for instance, with 100 qubits and you increase the number of qubits to 200, 500, you do not increase your quantum volume. Likewise, if you start here, for instance, at this particular error rate, you can go here all the way along larger number of qubits, you do not gain quantum volume. You have to go along this axis basically here. That means you have to reduce the error rate. This is the most important way to go. And concerning numbers, we have to say that the error rate of quantum computers is still about 12 orders of magnitude worse than for classical computers. So this is really something we have to worry about. And this is why we are all looking for more robust qubits for quantum computation. And this brings me naturally to the so-called Majorana qubits. Majorana qubits which could solve the problem of quantum computation in terms of quantum mechanical decoherence. Now, where does this concept come from of a Majorana qubit? Majorana was actually a very famous elementary particle physicist. You can see him here. And in the mid-30s, he considered on a mathematical basis possible solutions of the famous Dirac equation. As you all know, the Dirac equation describes relativistic fermions. And of course, you know the Dirac solution, which is a complex solution describing particles and antiparticles which are not equivalent, like the electron and the positron. However, Majorana found a real solution to this equation, and that is very exciting. On one hand, it describes particles and antiparticles being equivalent. But moreover, because this is a real solution, it does not have a typical quantum mechanical phase factor. And that's the exciting property of this solution. So this solution does not suffer from any quantum mechanical decoherence and problems related with this property. So if we could realize such Majorana states in condensed matter systems, then that would be a natural solution to this quantum mechanical decoherence problems of qubits. So how can that be done? And of course, we have to consider the analog of electrons and positrons in condensed matter. In condensed matter systems, as you all know, we have electrons and holes. And in particular, if we consider superconductors, we have a very nice electron-hole symmetry, for instance, of in-gap states in the energy spectrum of a superconductor. For instance, if a magnetic impurity is interacting with a superconductor, you induce in-gap states, electron and hole-like states, the so-called U-Shiba-Rusinov states, and the electron and hole-like states are completely symmetric with respect to zero energy. Now, if you want to have these electron and hole-like states becoming equivalent, that can only happen, of course, if you finally have a zero energy state, as shown here, and these zero energy states can have these properties of Majorana quasar particles. Now, the problem is that this zero energy state does not exist for an ordinary S-wave superconductor. So we would have to go to P-wave superconductors, and there are materials which are candidates for P-wave superconductors, but these are very complex material systems. It might be difficult to make a technology out of that. So in the following, I would like basically to discuss how can we design such a kind of system which would host such zero energy modes. So basically this brings me to the first fundamental question I would like to address in my talk. How can we design a P-wave or a topological superconductor from the bottom up? Likewise, of course, we can discuss generally methods to create unconventional superconductivity from the bottom up. And secondly, of course, I would like to address the question, how can we prove then the topological superconducting state? This is, of course, very fundamental as well. So let me start with the theoretical predictions of such Majorana states in a platform where we have basically spin chains, one-dimensional spin chains, proximity coupled to an S-wave superconductor. Here you see references. They are about 10 years back in time. The basic idea is that if you create a chain of spins interacting with a superconductor, you basically hybridize the Shiba states, the discrete Shiba states of individual magnetic impurities in contact with a superconductor to basically create a one-dimensional Shiba band. And then if you add high spin orbit interaction, which splits the states in momentum space and the magnetic state of the chain, plus superconductivity from your substrate, which leads to a gapping of the state, then basically you can arrive at such a topological superconducting phase. And in this topological superconducting phase, you have a non-trivial band topology, like for topological insulators, but of course the energy scales are much smaller. They are typically a factor of 1,000 smaller than for topological insulators. But like for topological insulators, when you would like to go from this topological phase to a trivial phase, of course you have to introduce boundary modes. And in this case, boundary modes, of course, for a finite one-dimensional system means that you create end states which would exhibit such zero energy modes. And of course, if you look then to the local density of states as a function of energy, at these points here, you should observe a very strong zero energy peak inside the gap of the superconductor, in addition, of course, to trivial states which arise from the Shiba bands. And of course, if you look for the spatial distribution of these zero energy modes, as I said, they should be highly localized at the ends of the chain. So that was a theoretical prediction. And now the question is, how can you realize this experimentally? This is very challenging. So you need to fabricate one-dimensional spin chains. You need to characterize the spin texture. You need to have fantastic energy resolution to probe the states inside the gap of a superconductor. So typically you need energy resolution on the order of microelectron volts, and you need atomic scale spatial resolution in order to prove that these zero energy modes are really located where you expect them. So let me start first with the fabrication of these very well-defined spin chains. And I'm coming from the field of scanning tunneling microscopy, and there we have a wonderful method of single atom manipulation. That means we deposit atoms, here in this case manganese atoms, from the gas phase on a superconducting niobium substrate. In this case, it's a niobium-110 substrate. And then we arrange the atoms here on the surface in a way that we form, in this case, a one-dimensional chain of close-packed manganese atoms. Here you see the structural model of this chain. This chain was actually built in the 001 direction. I will show you that we can build chains in any kind of direction. And for the physics, it's actually important in which direction we are going to build the chain. Of course, we can also build chains with different spacings of the atoms. We can, of course, replace manganese with iron or cobalt, which we also did. We can, of course, also go for other kind of superconducting substrates, but niobium for the following is the best choice, because you know niobium is the elemental superconductor with the highest transition temperature. Therefore, it's the largest superconducting gap where you can nicely resolve all the in-gap states, as you will see. Now, I would like to point out that this is not a simple experiment. The niobium substrates have to be absolutely clean. There should be no defect sites around, and you know niobium can easily oxidize, but we prepare these substrates in a way that there are no defect sites around, and we make sure by constructing these chains that all the atoms we add here to the chain are really manganese atoms. We can do that by local tunneling spectroscopy. So we make sure that these are disorder-free chains. So the low energy modes you are going to see cannot arise from disorder effects. That's extremely important. Now, the first task is to characterize the spin texture of these chains. And this is, of course, already a task for the field of nanomagnetism, which we have solved over the past decades. We have developed a wonderful tool, the so-called spin polarized scanning tunneling microscope, which allows to correlate not only the atomic structure and the local electronic structure, but also the spin structure at ultimate spatial time and energy resolution. The trick was, and I first reported that more than 30 years back in time, that if you bring a magnetic atom or cluster or coating to a scanning tunneling microscope probe tip, then you can basically detect spin polarized tunneling between such a magnetic probe tip and your magnetic surface. The spin polarized part of the tunneling current scales with the cosine of the angle between the magnetic moment on your surface and on the tip. That means you are basically looking to the local projection of the surface magnetization onto the spin quantization axis of your probe tip. So by rotating this spin direction in a controllable way, you can basically map out all the spin components of your surface structure. And the spin polarization of the states of sample and tip basically determine the magnetic contrast. So that means that for a given sample, you might want to make the tip polarization as high as possible, 100%. And in fact, we succeeded in fabricating tips with 100% spin polarization. That was reported last year in this publication. And you can see here the beautiful results from these experiments. Here we created chains here of manganese atoms here in different directions on the niobium-110 surface. So this is the 001 direction. You have here a chain with a double spacing of the manganese atoms. This is this chain. You see here in the topography that the atoms are not close packed, but there's a double spacing. And then what we do is we take the spin polarized tip and basically map out the spin polarization of the chains here while a magnetic field is applied either in the minus Z or plus Z direction. And then we calculate the difference of these data sets normalized to the sum, which gives us a spin asymmetry map. And you see here in a color-coded fashion that the spin asymmetry changes sign here from negative to positive in a periodic way. And this is indicative of an antiferromagnetic ground state of such a chain. If we go to a closed packed chain in 001 direction, this is this case here, we see we have a closed packed chain now in the topography. And if we do the same kind of experimental procedure, we now see that the chain has a uniform sign of a spin asymmetry here. This is indicative of a ferromagnetic ground state. So you can change the ground state by just changing the distance between atoms. But you can also change the magnetic ground state by going to a different crystallographic direction. For instance, this is the 1, -1, 1 direction, and we are looking here to a closed packed chain in the 1, -1 direction. And you see here that there's also periodic change now of the spin asymmetry sign, and this is indicative of an antiferromagnetic ground state. So closed packed chains can be ferromagnetic or antiferromagnetic depending on the crystallographic direction. We have also built chains in the 1, -1, 0 direction where the closed packed chains are ferromagnetic. So you can actually address the magnetic ground state for all kind of nanoscale systems these days. And we did this for iron cobalt chains. We did it for many different substrates, including superconducting tantalum, but also rhenium, lanthanum, and so on. So this is very important that we have this kind of knowledge later on for a detailed comparison between theoretical results and experiment. So once we know the magnetic ground state of the chains, we want to look at the electronic signatures now of the individual atoms all the way up to the chains. So I now come to the spectroscopic results, obtained, of course, with the same technique, scanning tunneling microscopy and spectroscopy. And again, I take the example of manganese atoms and linear chains on these clean niobium 110 substrates. Here you see an STM image showing basically a very clean niobium substrate and 2 manganese atoms which have been adsorbed from the gas phase onto this crystal. Now, if we take spectra now, tunneling spectra, basically we measure the differential tunneling conductance as a function of bias voltage applied between our STM tip and the sample, which is a measure of the local density of states as a function of energy. We first see if we place the tip above the bare niobium substrate, this is the gray spectrum plotted here, that we have a very nice gap here, a so-called hard gap, no states inside the gap here, and it's very well resolved. Whereas if we place the tip above the manganese atom here, then we see the red spectrum, and now you can see all these in-gap states, these so-called Uji-Barusinov states here. They always appear in pairs, symmetric with respect to zero energy, and there are states which are far away from Fermi level, but also states which are pretty close to Fermi level, which is important later on for the physics of these Majorana states. I first would like to make the point that now if you do a spatial mapping of these states, which you can do by just selecting a tunnel bias voltage, which corresponds to the energy of these Shiba states, you can beautifully map out the orbital symmetries of these Shiba states. This is shown here. So these are spatial maps here of tunneling spectra at different energies here, and you see here all the nicely resolved orbital states of these Shiba atoms. It's like the atomic orbital symmetries, but here this is a scale here in energy on the order of milli-electron volts, which correspond to these multi-orbital Shiba states. This is very important for the following. I would like to come back to that we have multi-orbital Shiba states in this case. And due to the spatial anisotropies, of course, of the orbitals, you can already imagine that it now plays a crucial role whether you build chains now of atoms in the 001 or in the 1, -10 direction, for instance, because when you look at these different orbitals, they have, of course, different possibilities to hybridize in these different directions. So here actually I show you that we can also create, of course, perfect chains in the 1, -10 direction, which is the perpendicular direction I've shown you before. Again, we can go to very, very long chains, well above 100 atoms here on the niobium substrate. And now we really look to the electronic signatures of the chains, and this is shown here. For a chain consisting of 32 manganese atoms on the niobium-110 substrate in the superconducting state. And these chains have been built now in the 1-10 direction, where we have a ferromagnetic ground state of the chains. You can see here the topography of such perfect chains, and I first discussed the local tunneling spectra, the differential tunneling conductance measured as a function of bias voltage, meaning as a function of energy. What can we see? First, by placing the tip just above the bare substrate, again, we see in gray the spectrum here of superconducting niobium with the two coherence peaks, which are at about 1.5 millielectron volts. And within the gap now, we can observe states. If we position the tip above the chain center, this is the blue spectrum, you see, of course, that there are in-gap states, not only discrete states, but also some kind of mini-bands are formed. But interestingly enough, there's also a gap here in the blue spectrum where there are no states at all. Only if you position the tip above the chain ends, you can see here now also discrete states, and especially a zero energy state here, as expected according to the theory of such Majorana states. And indeed, if we go to real space now, making a spatial mapping of all these states, we can see that right at zero bias, at zero energy, we have basically most of the spectral weight here at the ends of the chain, whereas for the finite trivial Shiba states, we have, of course, the spectral weight primarily in the chain center. This is exactly what has been theoretically predicted, and we see here for the very first time a very pronounced zero energy mode, which is very well separated here from all the trivial states. That is the first observation of this kind. But there is something else, of course, to be seen here. If we take this example, that's a shorter chain of only 16 manganese atoms. It's a different kind of plot where we have here the spatial coordinate and here the energy. So the differential tunneling conductance is now color-coded, meaning high differential tunneling conductance is represented in white. We see here again the coherence peaks of the superconducting niobium at about 1.5 millielectron volt above and below Fermi. And you see again here this very nicely pronounced zero energy mode with most of the spectral weight at the ends of the chain. And we see that there is a gap within the Shiba bands, which are here at finite energies, but still inside the gap of the superconductor. And you see you have to resolve all that to really see what's going on inside the gap of the superconductor. So everything looks perfect, but there's a case of warning. And the warning is that we have seen in the past years that there could be also trivial states which have nothing to do with Majorana states at zero energy. And on the other hand, topologically non-trivial states can split away from zero energy. For instance, as a function of hybridization of Majorana states at both ends of these chains. So if a chain is very short, and in fact a manganese 16 chain is considered to be short, then you expect hybridization, and indeed we have also seen effects of this kind. So that means by just looking at zero energy states, and that has been reported so many times in literature, you cannot prove to have a Majorana state. You can only say, okay, your observations are basically in agreement with the theoretical predictions, but there is no proof that you have a Majorana state. So I would like to go a step further now. How can you really prove that you have a topological non-trivial superconducting state, and that as a result you really have Majorana states in your system? And that brings me now to the question, how can we design topological bands of a superconductor atom by atom? You know, of course, topological band structures of topological insulators, which can be measured, of course, with angle-resolved photoemission spectroscopy. And the energy scale is, of course, electron volts. But now here we really have to go towards band topologies inside the gap of a superconductor on a micro EV scale and for atomic scale systems. So how can we address such kind of topological bands, and what do we expect to see? Now, to address this question, what do we expect to see, I'm going back to the famous Kitaev chain model as a minimal model to describe topological superconductivity. It's about 20 years old, and it basically includes three important parameters, namely the on-site energy E0, a nearest neighbor hopping term here, and a superconducting pairing energy scale delta. And of course, there's a lattice constant for this chain and then the associated wave vector. Here's this famous guitar model Hamiltonian with these three important parameters. And the basic conclusion was that as a function of the strength of this nearest neighboring hopping term measured here in quantities of E0, you can observe a transition from topological trivial to non-trivial states. And this is shown here, where we basically have plotted here the energy as solutions to this guitar Hamiltonian as a function of a wave vector. And you see at t equals 0, we start, of course, with a trivial band topology. And if we now start to increase this t with respect to E0, we see a very nice transition here from a trivial to a non-trivial band topology. And once we are in this non-trivial band topology, we open up a topologically non-trivial gap. And as a result of this non-trivial gap, we should observe Majorana physics. Because there's a clear correspondence, the so-called bulk boundary correspondence to, of what we expect to see basically in the bulk and at the boundaries. So here you see again the three pictures of the trivial and the non-trivial state in K-space, and here exactly at the transition we see, of course, that we go from the trivial to the non-trivial topology. We have, of course, a clear correspondence to the real space picture, where we have here energy plotted as a function of spatial coordinate along the chain. And you see, once we cross the topological transition, we start to see, of course, the zero energy modes here at the chain ends, at least in a simple one-dimensional toy model, which was, of course, considered already a long time ago. Now, the question is now, how can we measure this band topology of a superconductor? That has never been done before. How can we do this? So let me explain this in detail in the following. Basically, what we do is, of course, we do measurements in real space. And what we have is a finite chain here, which is proximatized to a superconductor, so it also becomes superconducting. And of course, what we have are Bogoliubov quasar particles, and we can do basically an interference experiment of Bogoliubov quasar particles traveling back and forth in these nanowires. That basically means that we look to the interference of states characterized by minus k and plus k, and we create then a standing wave pattern basically in real space, and of course the wavelength is connected to the size of this k vector and to the energy. So if you go higher in k and higher in energy, it means that the wavelength is expected to become shorter here, and if you go even higher in k and in energy, we should expect to observe even smaller wavelengths. Now what we do is we basically measure these interference patterns of Bogoliubov quasar particles in the one-dimensional nanowire system. And before we do this, let me first show you now how we can really watch directly by adding atom by atom now how the one-dimensional Shiba bands evolve from the Shiba states of the individual atom. So here again, there's the spectrum record for the single manganese atom on the superconducting niobium. You have seen this spectrum before. I just rotated the spectrum now so that we have the energy axis here on the Y scale here. And you see again all these discrete Shiba states inside the gap. And now we do this in a color-coded fashion here for a single atom system. Here's the energy scale. Again, we expect the superconducting coherence peaks of niobium at about 1.5 millielectron volt. And now we add atom by atom. We create chains here up to 35 atoms. And now you can see how the discrete states evolve. Basically, they shift in energy. They cross here the Fermi level here, and they form basically bands. These are the so-called Shiba bands inside the superconducting gap of the niobium. So here are again the coherence peaks of the niobium, and inside the superconducting gap you see the formation of these Shiba bands very beautifully. And most important, you see the opening up of another gap inside the Shiba bands here, clearly. And this scale is, of course, much smaller. Now the question is this a topological trivial or non-trivial gap? That's the major question now. And we can only prove that, as I said, by doing k-dependent measurements. And we can do this trick, as I said. We measure basically Bogoliubov quasar particle interferences in these superconducting manganese chains proximatized to niobium. So we measure basically differential tunneling conductance now all along the chains here for a manganese 17 chain. We plot the energy here on this axis and the spatial coordinate along this axis. And again, the differential tunneling conductance is color-coded. High conductance means we have bright color. And you see we do the measurement here by basically doing a line scan with our tip and taking spectra simultaneously and then getting this beautiful data set here where you can now see again the coherence peaks of the superconducting niobium, and inside the superconducting gap you see all these very nice quasar particle interference patterns here. And indeed, of course, if we go to lower energies, we get larger wavelengths here. And we can nicely see this, of course, not only for this particular chain, but we can add now atom by atom to create longer and longer chains. So this is shown here. So for each chain length, we take these kind of data sets, and you see how these quantum mechanical interference patterns evolve now as a function of chain length. Notice that these are very demanding experiments done typically at 300 millikelvin, and with an instrument which has to be stable over at least 1 to 2 days, because these are very large data sets. And we have to make sure that the atom at the front end of our probe tip does not change over this time scale. Because to compare all these data sets, we should not have a change of the tunneling junction, and this means that the single atom at the front end of the probe tip has to be stable. So these are very demanding experiments done by Lukas Schneider, PhD student at that time in my group. Now, what we do, and of course I outlined this, we take these real space data and Fourier transform this to get this k-space information. This is done here for a manganese 34 chain, a chain of 34 manganese atoms. And you see here now a beautiful band structure. This is enlarged more here on the next slide. What we see is clearly a gap, which you have seen, of course, before, also in the other kind of experiment. We see clearly a gap, and if you look at the band topology, it's exactly following the expectations for a topological non-trivial gap, whereas a trivial gap here would look completely different. We can use, of course, a simple kind of one-band toy model to get a nice fit of the experimental data. So the data points experimentally obtained are shown in black, and the red curve is a fit where we basically have a spin-orbit coupling parameter as a fitting constant. And of course, we need a finite spin-orbit coupling to open up this topological gap. This is very well known. And of course, we can quantitatively then derive a topological gap size, which is 180 microeV, so 2 times the topological gap is 360 microeV, which can very nicely be resolved in our measurements. Now, of course, the question comes up, if we have proven now this topological non-trivial band topology, what about now the Majorana states? So they should be there because they are a consequence of this non-trivial band topology. And as I said, a simple one-dimensional band model, which so far has only been considered, and also only a single orbital picture was applied theoretically, then you should expect, of course, to have, again, these kind of end states. But sometimes it's really important to do experiments, not just to trust theorists. And this is what we did here as well. And the result for this chain now, built in 001 direction on the same niobium 110 substrate, is different from the chain built in 1-10 direction. When we look at the spatial distribution of the zero energy modes in this case, we see that we do not have the typical end features, but we have side features here at the sides of the chain. And they look completely different to all these finite energy states here, the trivial states. And of course, the first question is this just something which has to do with the finite size, the limited length of this chain? The answer is no, because we can go to much longer chains, 51, we can also go to 100 manganese atoms, and still we have the same kind of side features. Here we just have more side features if we go to longer chains. And if we go, for instance, from manganese to iron, we also have these kind of side features, interestingly. So it seems to be a quite characteristic feature. And we were very puzzled, actually, for a long time how to interpret this, until we had a very nice theory collaboration with Stefan Rachel and his group in Melbourne and Dirk Moore in Chicago. And they basically showed, theoretically, that you can have such side features in the topologically non-trivial regime under certain conditions. So they could reproduce for this 34 manganese chain exactly our pattern observed here, or for the manganese 51 chain, you see the very close correspondence. Now, what has been done here theoretically to arrive at this conclusion? We basically started from ab initio calculations, and that was done by Harald Jeschke in Okinawa. So they really did full ab initio calculations for manganese chains, one-dimensional chains of manganese in different crystallographic directions on niobium 110. And of course, you do not get a single band, you get hundreds of bands, of course. This is clear. And even if you limit yourself only to the low energy bands, which are relevant for physics discussed here, you still have 40 bands or so to consider. And that was exactly done by Stefan Rachel then. He built up a 40-band tight binding model where he took the results of the ab initio calculations and calculated the topological phase diagram. And in the topological non-trivial regime of the phase diagram, he exactly could reproduce these states with these side features here as observed experimentally. And the physics behind these side features is really that the real system here has multi-orbital nature. And that is the major difference to all the simple toy models considered in the past. For multi-orbital states, actually, you can have Majorana signatures which are different from the ones predicted previously. Now, I would like to point out that this is, of course, something which we can do now for many different kind of atom systems and for many different chain systems. And so we start always with the single atoms. We look basically at the orbital symmetries of the states. And of course, we can look also to the energies of the corresponding states. And of course, then we typically select those states which are close to Fermi energy, because these are the states which evolve naturally to Majorana states if we build up chains with these kind of states. And then, as I described, we build up the chains here in the 001 direction. We characterize the magnetic ground state. In this case, it's ferromagnetic, and we derive the band topology. That could never been done before. It's really the first time that we can map out band topologies inside the gap of a superconductor. And we also found out that if we build now chains in a different direction, so here in the 1 - 10 direction, we can find a ferromagnetic ground state, and you see the band topology is completely different, completely different. And even more exciting, if we build the chain now in 1 - 11 direction, this is something I did not discuss yet, we have an antiferromagnetic ground state, which we have proven with a spin polarized STM. And if we then look to the band topology, it again looks completely different. And more recently, we have shown that it is really advantageous to go towards antiferromagnetic spin chains. In principle, you can get more robust Majorana states. We have a theory paper on that soon coming up. And we can actually tune all that now really on a microscopic, meaning on an atomic length scale. So to sum up, we have successfully fabricated in a defect-free way magnetic single atom chains on clean elemental superconducting substrates. We did this first for rhenium. I have shown you results on niobium. We have a lot of results on tantalum, which has higher spin-orbit coupling. Jens Wiebe later on will give a talk on tantalum and other kind of substrates exhibiting even higher spin-orbit coupling, where the topological gap size is expected to increase. We have a clear observation of characteristic signatures of Majorana states by spatially energy and spin resolved scanning tunneling spectroscopy. We have zero energy modes with a clear energy separation from all the trivial Shiba states, and moreover, and this is a new result, a brand new result from multi-orbital systems, the spatial distribution of Majorana states shows side features which were not theoretically predicted so far. It's really a result of these experiments on the different chains. So in the future, and this is the outlook, of course, we will manipulate now these Majorana states according to theoretical proposals going back more than 10 years ago. For instance, in this paper, a tri-junction has been considered now, where based on a sequence of manipulations, you can basically exchange Majoranas at two ends and look for the theoretically predicted non-abelian quantum exchange statistics. That is, of course, the ultimate goal, to really prove this non-abelian quantum exchange statistics by these kind of experiments. Again, you need atom-manipulated systems to create such tri-junctions. Here's a tri-junction made up of iron atoms here on a superconducting rhenium substrate. We also go to more extended network structures, as you can see here, where you expect Majorana states at all the endpoints, but also on these points here. This is also very exciting. And of course, we can go really to very long chains to separate basically the Majorana states at the ends of those structures. We can also go towards circular geometries, which is also exciting according to a proposal of the Princeton group 7 years back in time here. Basically, they proposed to look for ring geometry and using in-plane magnetic fields to manipulate Majorana states. Again, we can construct such rings atom by atom. Here, a magnetic ring of iron atoms here. And this is also a direction we would like to go. And of course, in the end, we hope, based on these confirmations of the existence of these Majorana states, to realize these Majorana qubits and hopefully contribute also to this field of topological quantum computation. In the end, let me thank my co-workers involved in this activity, Ho-Won Kim, who did the pioneering work on these atom-fabricated iron chains on superconducting rhenium, which is already more than 5 years back in time. Lukas Schneider, Philipp Beck, Jens Wiebe, who did the wonderful experiments on the manganese chains on superconducting niobium. Levente Rocha, who was doing ab initio calculations for all these systems. Tore Poske, who primarily did tight binding model calculations, especially for the manganese chains on niobium. And especially I would like to thank Harald Jeschke, Dirk Mohr, and Stefan Rachel and their groups for their wonderful insight into the physics of the side features and the relationship with the multi-orbital nature of the Shiba states. I would also like to thank the funding agency, the European Research Council, in the framework of an advanced grant on atomic scale design of Majorana states and innovative real space exploration. There's still a postdoc position available if you're interested. And of course, in the end, I would like to thank you for your kind attention. Thank you.
Thank you, Professor Weissenteger. Do we have questions? There's one way in the back there, and then there's one here.
Ronald, I understand that all this is happening at about 300 millikelvin.
Yes.
How critical are these results to the temperature interval? What is the temperature interval in which all this phenomena exists?
Okay, the temperature scale is chosen according to two important parameters. Of course, the materials parameters, yeah, so typically you have to be well below the superconducting transition temperature of your substrate you are choosing. So for instance, when we did the experiments on superconducting rhenium, rhenium has a TC on the order of 1.3, 1.4 Kelvin, much lower than for niobium. Then we had to go even lower in temperatures or playing more tricks, but still there's not the same kind of possibility to resolve states inside the gap. So you have to be much lower with your temperature compared to the transition temperature of the superconductor. Then, of course, the temperature can have an influence on the magnetic ground states, of course, yeah. You have low-dimensional magnetic systems, and you might also have transitions as a function of temperature. But most important, of course, the temperature also has a drastic influence on the measurement conditions. So you might want to have the best signal to noise ratio possible. So at low temperatures, of course, we have most stable signals, and all the data I have presented today is raw data. No filtering at all to the spectroscopy results or to the Fourier transforms. Everything is raw data, and you can compare with results published in literature, say on other systems by other groups. I mean, this kind of quality of data you can only get at these extremely low temperatures. And what I also have to say, we are typically making use of superconducting probe tips where you are not limited by, say, the thermal broadening. This is also a very important point. Yeah? So in the spectroscopy results, we do not have thermal broadening here. These are the intrinsic widths which we can measure. So in terms of thermal broadening, this is not the most important point, but the most important point is really to get the signal quality as highest as possible.
We have another question in back.
Thank you.
Another one? Do you have a question? And then Ali has a question. Okay.
So there is some activity on U-Shiba Rusinov system by Felix von Oppen, by Yuval Orek, and Jason Alessia, whom you mentioned it. They also developed proposed different models just during some last 2-3 years, even during this year. So are there some correlations between your experiments and the theoretical predictions?
First of all the theoretical work, no matter if it is by von Oppen's group or by other groups like Sankara Sharma and others, they basically considered a one-band model. They basically, of course, derived these kind of predictions of these zero-energy end states. But it has, of course, been very difficult to prove experimentally up to the present time that the zero-energy modes observed by various groups, going back to the first observations of zero-energy modes by Yazdani's group in Princeton, that these are really connected to Majorana physics. Because, as I said, whenever you observe zero-energy modes, it is consistent with your theory, but it does not prove that it is a zero-energy mode. Jens Wiebe on Tuesday will show you results on similar kind of chain systems on tantalum, where you also have zero-energy states, and they are trivial. You can prove this, because a very important feature of Majorana states is that they always come in pairs. So if you do an experiment where you approach, for instance, an impurity to one end, and you modify your state at one end, it immediately has to have the same response at the other end. Otherwise, it cannot be a Majorana state. So there are a number of protocols now where you can really, with these atom manipulation experiments, prove or disprove that you have Majorana states. And this is extremely important for this field. So with our platform, we can do all this. It's much more delicate for the other kind of platform you know of. And most of the theory, of course, is more devoted to the other kind of platform, namely semiconductor nanowires, proximity coupled to superconductors, where you have, of course, other kind of problems, especially disorder-related effects, which can also give rise to low energy states. But we can exclude this disorder effect because of the perfect chains and the perfect surfaces which we can prepare in the STM chamber.
Thank you. You mentioned also some ring-shaped chain, right, in your last slides. So in principle, one can consider not circular, but ellipse or other arbitrary geometry for closed system. This should be some tool for tuning the band structure or band engineering, topological band engineering, geometry dependent band engineering. Is that attractive or prospective, or how is it realistic?
Yes, sure. I mean, this is exactly what I wanted to say when I showed you this sequence of chains in different crystallographic directions. So you all know that band engineering has been at the heart of semiconductor device technology. Once we knew how to engineer bands in semiconductor heterostructures, of course, all the possibilities came up about different kind of devices. And here we can really do band engineering on one hand, on ultimately small systems, namely atomic scale wires, and on the other hand, on energy scales which were never addressed before, namely micro EV electron scales. It's a band engineering, of course, for superconductors, not for semiconductors. And I would expect that if you do this kind of band engineering now for these in-gap states of superconductors, that you have a lot of exciting possibilities, not only to look for Majorana states, but also other kind of very interesting features of superconductors.
Ali had a question.
Thank you very much for the very excellent talk. I may have missed because I was also busy with communication. Is it possible to correlate the qubit entanglement issue, the time scale and coherence length for decoherence time? I mean, for the niobium that you worked as experimentally and theoretically, I mean.
Yeah, this is exactly what we are looking for right now to do these kind of measurements. What we have already proven is that we have really an entangled state, meaning that we always observe then exactly the same kind of response at both ends of the chain, so that we can exclude any kind of trivial explanation for the zero energy mode. So it's really kind of entangled state of these two Majoranas at both ends, and we are now combining these kind of experiments I showed you today. These are more or less static experiments now, with experiments where we couple this to microwave radiation and do also dynamic experiments on these Majorana states. This is just going to be prepared, these kind of experiments. We have basically the setup ready, and this is the next step, of course. We would like to go with these experiments. Yeah.
Just small. Okay. What would be the time scale for the coherence?
That is a very interesting question. We do not know yet.
A little more. Okay.
Because we will not trust, there are theoretical predictions, of course, yeah, but we have seen that the real systems are not as simple as described by the simple toy models. So there's much more behind. We really have to go towards realistic approaches also from the theory side, and this is exactly, of course, why we went into this direction, combining ab initio calculations with tight binding model calculations and so on. So we have seen, for instance, by just changing the distance between the atoms, or by changing the transition metal species, or the direction of the chains, yeah, you can go from non-trivial to trivial state. So, and of course, I expect that these kind of different properties will not only show up, say, in static measurements, but of course also in terms of dynamics of states and coherence times, for instance. So this is something which we really have to explore in the future experimentally.
Yeah, I have a more practical question. You know, how likely you think topological qubits or Majorana qubits in particular would be able to compete with classical, like prevailing superconducting or photonic qubits that most people are working on right now?
Yeah, the technology of superconducting qubits has already very much advanced, and of course it's improved all the time. There's a lot of manpower by the companies, of course, put into that to improve the quality of these superconducting qubits, but still the basic problem remains, yeah, to make these quantum bits more robust against quantum mechanical decoherence. And this is why so many groups have started efforts, not only theory groups, but experimental groups, to have activities in this direction. So if this really works out, then it would be a wonderful solution to this quantum mechanical decoherence problem. And this is why still this is the best way to go in principle. Yeah? The other way to go is, of course, to have a very, very large number of qubits, where most of the qubits are then in the end used for error correction, yeah? As you know, but this is not a very smart solution, I would say. Yeah? Rather than using so many qubits just for error correction, it would be a much smarter solution to go really for robust, topologically protected qubits. Yeah. So
I
this
know
is-
Microsoft is backing up, this kind of research on Majorana qubits.
Pardon?
Microsoft is backing up, this kind of
Yes,
research
sure.
on
I mean, they
Majorana
have
qubits.
activities in this field already for a long time. They have put a lot of money into
Yeah,
this.
but have
and-
they been able to, up till now, demonstrate any qubit based on Majorana particles, Majorana states?
This I didn't understand.
Have they been able to, up till now, demonstrate any, based on what Microsoft
There was
sponsored
recently a
research?
problem, as you know. I mean, they completely put their efforts on the semiconductor nanowire systems, proximity coupled to superconductors. And there was recently a claim in a Nature paper which finally had to be withdrawn. There were also a lot of problems concerning reproducibility because of the disorder effects. So the current status in that field is that still with the best quality of semiconductor nanowires, you cannot control the disorder to the atomic level. So there are always, of course, some atomic defects in these semiconductor nanowires which are charged and which are, of course, problematic for really observing clear Majorana physics. So disorder-related effects are the most important problems. And even if you would start with a perfectly grown single crystalline nanowire, the problem is that for creating these devices on the semiconductor side, you have to do lithographic processing and so on, and you induce the defects later on to a much greater extent that you have originally in the semiconductor nanowires. So far, I do not know of any device based on semiconductor nanowires where you can completely exclude disorder as a possible explanation of the observed low energy states.
Okay, so let's thank our speaker again.
Oh, yeah, thank you so much. Thank you. Thank you very much.
I propose that we come back, is 11:15 okay? Okay, 11:15. Oh my God, what happened? He tripped. There must be there's an edge there. I'd have from the University of California at Berkeley, and his title is The Dawn of the Quantum Computing Era. I didn't listen to the beard.
Thank you, Laura, for the kind introduction. And a thank you to the session chairs and the organizers, and of course, Professor Ali Gencer for bringing us all here to talk about things quantum. I was hoping in this brief 45-minute talk or so, I would try to shed light on this word technology, because somehow quantum mechanics and technology going together really talks to me about a new era in the definition of this theory. So in fact, I would like to start off with this particular image. The pointer is working. There we go. Oh, there we go. Yeah, it's on. Yeah, it's on. Okay, got it. So this is a very traditional image that you have from the 5th Solvay conference, colored after the fact, of course. And you see many of the proponents of quantum theory, and of course, you see Marie Curie, 2-time Nobel Prize winner in the front here. What was quite amazing is that at that time, if you like, this discussion was, does entanglement actually exist? In fact, or is it a mathematical artifact of a theory that you need to explain something under the world? And this continued between Einstein and Bohr. And I have to really pay homage to this book by Manjit Kumar because I love the tagline that says, you know, Einstein and Bohr and the great debate about the nature of reality. And somehow I think what's amazing is that this is now turning into an engineering resource. So the talk today really talks about the necessity still of fundamental science to understand where quantum is going and what are the new generation of science problems that will really fuel the technological revolution, and looking at where we are now and what are still outstanding challenges in the field. So to summarize, the basic premise is that our observations of the world only reflect some aspects of a much more complex hidden reality. So the quantum world below the surface is entangled. And we only have a slice with our observations of that particular complexity. Is it really true? Well, we need this underlying structure to explain basic observations, even though we cannot directly measure it. And there was a century of trying to find other theories to explain that. And really, with the era of Bell after that, I think we settled on entanglement as the answer for the moment. So we are now really entering an era where we can finally use the quantum nature of matter as an engineering resource. And this is tremendously exciting and puts together a new set of fundamental questions of how to take a theory, how to take a mathematics of entanglement to something you can buy and use. I think you know that the technology is moving forward when The Economist writes many articles on it, and in particular has the tagline, "A mind-bending technology goes mainstream." And if you like, from this BCG group report, which is very thorough, it says what happens when the if turns to when in quantum computing. So folks that are thinking about investing or where this technology is going, you can see the growth really in terms of many billions of dollars, both in the private sector and also in academia, thinking about what is the promise of quantum. And you see charts like this. What are the things that you could do if you had a quantum computer? And then I want to bring this a little bit back to reality of perhaps what we can do today and how to actually go here. The general idea is that if you can solve certain mathematics problems more efficiently using quantum mechanics, then all of this mathematics, which powers simulation in various industries, optimization of finance portfolios, machine learning, cryptography, all of these things would be accelerated. But in fact, we are quite some distance away from this. And in fact, getting a quantum technology to outperform a classical one is a very delicate task. So in fact, I will talk a little bit about that and whet your appetite about perhaps what's more realistic in the very near future and how do we actually get here. That being said, I do want to pick one of these problems in chemistry. There has been quite a lot of discussion of how to use quantum algorithms to find the ground state of complex molecules. And And one can think about then how to use that information for designing a drug, say. And that problem turns out to be actually a very hard one. If your molecule size is large, both classical and quantum resources will have to be large. And we are unable to do that for a large molecule. But there may be some interesting things that we can do along the way. So what I'd like to show you is the following. If you look at the economics of how a drug is selected these days, it takes about $2.5 billion to identify a new drug. Okay? And the way this works is that preclinical research selects 0.1% of small molecules for trial. And then 10% of these clinical trials are successful. So it's not a very high success rate proposition for looking at drug discovery. And the problem is that quantum effects and molecules evade classical simulation. So even if your quantum computer didn't solve the precise structure of the ground state, if you improve this 0.1% to 1%, that would be a 10 times improvement on a very large number. So there's a lot of things that quantum may be able to do along the way. So we, like others, have participated in trying to solve for chemical structure using quantum mechanical results, using both classical and quantum resources, but we should perhaps broaden our minds in the near term, thinking about other information that we can get from quantum-guided technologies. Just to give you a sense that there may be things along the way that you can pick up before a full quantum computer is available. In this particular section, I want to talk about the difference between 1 qubit and a quantum processor. Those two things are very different ideas. And in particular, quantum mechanics brings in the idea of your quantum system and the environment. And both of those things are critical to understand what's happening in a quantum system. So let's start with NMR. If you've gone into one of these machines to have your MRI, then typically you're looking at the polarization of hydrogen atoms. These are water molecules that are there. You apply a magnetic field to quantize the axis of your spin. And of course, a measurement in this basis will always give you up or down. Okay? You will either measure red or blue in this case. You prepare a 50-50 superposition, say in green. Half of the time you measure up, half of the time you measure down. This is typically represented on a sphere where the two poles will give you the red and blue states that are there. So with this 50-50, you get a sense that, in fact, the spin can point anywhere. However, your measurement is decimating your results to be aligned or anti-aligned with an axis. So the complexity underneath the surface is much bigger. So in NMR, we are taking advantage of this quantum property, but you're looking at it at an ensemble sense. You're not measuring typically the response of one water molecule. You're looking at the response of a piece of tissue or a tumor or something else you want to look. And we use that nomenclature of T1 and T2 to tell you about the decay of that particular quantum state. So the challenge really of quantum computing is to take this NMR, if you like, in this language, and put controls on it at the single molecule level. And in fact, these NMR type of quantum computers were used very much so in the early day, even when demonstrating factorization of numbers by Shor's algorithm. Okay? This conference has also a flavor of quantum materials. So I wanted to go ahead and contrast these fields that we term in modern day as quantum materials and quantum information science. The field of quantum materials, if you like, which has two-dimensional materials or complex three-dimensional structures, looks at quantum effects where the experimentalist is assisting or encouraging nature to assemble complex structures. We have some complex synthesis mechanism to come up with, let's say, a superconductor, whether it's YBCO or an iron-based superconductor, or a van der Waals material in 2D or the like. And this quantum coherence then is preserved by structural perfection and symmetry. You'd like to get the best possible crystal so that you can look at this emergent phenomena, which is quantum coming out of this. Typically, there are no wires in this setup. You're not addressing the individual unit cells that are there. So the effort to build a quantum processor is really a complete redesign and synthesis of quantum matter. We are picking the crystal structure that your qubit should take. How should they be connected? Nearest neighbor, tetragonal, in a ring, or what have you. And that's very different than encouraging nature to protect quantum coherence. By definition, we are going to break the symmetry of that material because you need to get signals in and out. Okay? That's a very different proposition, of course, than trying to preserve the coherence inside. And moreover, not only do you need to get information in and out, you need to change dynamically the couplings in your setup. Certain elements need to talk to other elements at a different period of time. So it's not a static problem. So you see, these two things, they share quantum in their name. And of course, there is coherence involved. But in fact, the regime, whether it's open or closed quantum system, is very different in these two cases. With that, you have the following flora of different qubit technologies, whether they go from some very microscopic technology, such as an electron in a quantum dot, or a vacancy in diamond, to a single photon, to a single ion, or circuits that have superconducting circuits that have common behavior, that's quantum, or in this beautiful talk that we heard from Professor Wiesendanger, where we can have, in fact, Majorana modes in certain semiconductor structures. I should put your pictures here now, after that beautiful talk. So what's the winner? That's the usual question the DOE will ask me, which one should we do? And the question is, it's a loaded question for the following reason. When you're building, as I said, a quantum information system, you must have wires to the outside world. So your quantum system is the qubit and the environment. And this plot is only showing you the qubit. I have said nothing about the environment. So you have the choice here of taking systems that naturally decouple from the outside environment, or systems which couple very strongly to it. So you may say, well, let's always pick the ones that decouple from the environment, because you will get maximum coherence. The problem is we are also part of the environment. Right? The environment has two pieces. It has the experimenter getting information in and out, and then it has the other people that you don't want to get the information that's there. So in these systems, if you are looking at a very open quantum system, like a simple superconducting circuit, the name of the game is to suppress all the bad actors and then get the information for yourself. If you are working with a system with topological protection, then the name of the game is to allow you to have access to the information. None of those problems are easy. So I think that point is that we have not picked a winner yet. And in fact, the real technology may involve all of these. Because after all, your computer may have a memory, your computer may have a processor, it may have links for transduction, so on and so forth. So there's a lot of fundamental science before we sort of pick on the quantum computer. So with all of those words, let me start talking about superconducting qubits. This is a zoom in of a typical superconducting device that we make. We have our own class 10 clean room. We produce superconducting wafer scale qubits in 2 days or so. So here is an example, a zoom in of a certain plaquette with qubits shown here and resonant structures linking them. The materials are niobium for the golden colored stuff. The tunnel junctions are aluminum, which is there. I'm glad you also like niobium. So the premise that brought a lot of us into this is why use a superconductor? The general idea is that you pair excitations into Cooper pairs. This allows, at least for DC transport, to be dissipation free, and you also have the Meissner effect in a big crystal. To be honest, almost none of these things are exactly relevant for superconducting chips, because in fact what's happening is that you have surfaces. And in AC properties, the surfaces and interfaces matter. Right? If you have, for example, a dielectric on top of your surface, then that will also couple inductively noise into your system. Whereas for a DC current, you could pass it, of course, in parallel. So I'll show you a few images about what's happening on that niobium surface. Right? And there's a lot of physics to be learned just by looking at surfaces and interfaces. In addition to that, we have this nonlinear elements called Josephson junctions. And what's happening in the tunnel barrier of Josephson junctions is another saga in and of itself. So I'll spend some words on that. And moreover, once you start putting in wires, then you have additional many-body noise mechanisms that are there. And what I want to end up with is to show you that if you start to learn something about the noise, you can get a lot more computing power out of your quantum computer. So with that, going into experimental data, this is the group on campus that I'm very thankful for. We'll talk about their results. The whole group can be seen on these 2 websites that are here. which include collaborators at Lawrence Berkeley Lab, the Molecular Foundry, and the National Center for Electron Microscopy. Superconducting qubits is basically an LC oscillator. So we start off with a very simple LC oscillator. This is the mechanical analog of a harmonic oscillator. Okay. In a harmonic oscillator, all the energies classically are allowed. If you quantize it, then only certain energies are allowed, but they are all equally spaced in energy, all by h bar omega. If you'd like to turn this into a quantum information system, where you can address, let's say, a certain pair of levels, we need to have nonlinearity in the system. So for that, we put in a Josephson tunnel junction into the story here. Okay? So this is an aluminum oxide, aluminum tunnel junction, which creates an unequal set of energy levels with spacing somewhere between 1 and 10 gigahertz. If you're a theorist, you can think of this as a particle in a cosine box. That's the end of the story for a Josephson qubit of this particular flavor. This type of qubit is very open to the environment. It couples to many types of defects. You can have amorphous dielectrics shown here. That's all the fuzzy stuff on top of these metallic films, and also at interfaces. You can also deviate from this nice picture of Cooper paired excitations into quasi-particle excitations that are there. And you have also very interesting things which remain yet a mystery. Noise sources which have a 1/f distribution. So flux noise, for example, is a very well-known old problem. If you make a ring and look at the flux through it, you will see fluctuations of this 1/f type. And of course, this leads to decoherence in different methodologies, which I'll talk about in a second. Okay. Let's start looking at that niobium surface, okay, in particular after we process those wires. So here is a microwave structure. This is niobium sitting on silicon. And the niobium surface here, you can see there's the niobium metal, and then there's this yellow stuff on top, which I call NBOX, telling you that we have, in fact, all the different stoichiometric combinations of niobium oxide that are there. So this is a high-resolution transmission electron microscope. If you now go ahead and do XPS on this, scattering measurements, you will see which parts are NBO, which parts are NBO2, and which parts are NB205. Okay. And they give decoherence in different ways. Some are semi-metallic, some in fact are reasonable insulators, so on and so forth. And this color map tells you that we have a lot of NB205, a particularly bad actor in this game. You can do the same with the silicon surface. Here's silicon and here's SiOX, telling you the different oxidation states of silicon that are also there. The niobium silicon substrate actually is quite good for us. You can see almost all those crystallographic planes. So that turns out to be a pretty clean interface. So the niobium silicon interface is very clean. We observe multiple oxidation states of both niobium and silicon. And as we start to peel away these layers, we can figure out which are the ones that are really messing up your coherence in the system. So in this case, we've made resonators, and we're measuring the quality factor of resonators with different etching techniques where we remove these oxide layers. So the quality factor here is expressed as a loss tangent in part per million. More loss, lower coherence. That's there. You start off with an oxide of order 5 nanometer thickness, and you start to etch it down with a particular cocktail of acids to remove this. And you can see the loss tangent is dramatically different. In fact, we were able to go from 1 million single photon Q to 10 million single photon Q at wafer scale. So just by removing a few nanometers of this NB205. What's also very interesting is that in this etch, we haven't actually passivated the surface. So you would imagine the stuff would regrow. But what grows back is different than what you prepared the first time, saying that by changing the kinetics of the chemistry, you can change which flavor of niobium oxide you get. So there's a lot of subtle surface physics that comes into actually improving the quality of these films. Moreover, this NB205 is a very interesting compound. It, of course, is paramagnetic as a crystal. However, when you put it on a surface, like the surface of niobium, it's lattice mismatched. And that lattice mismatch can actually introduce magnetism into it. So we'll actually get a little bit of a magnetic moment. And if you start to think about flux noise, you can add one more character into that list and saying, is it really the NB205 under strain which is fluctuating? don't know, but interesting question to look at, the flux knows. The typical story with a lot of these defects starts with the usual physicist model of saying that we really don't understand what are the defects. So we call them under this heading of two-level system. What is this exact two-level system? This is a matter of debate. The general idea is that you have some double well potential that can correspond to two different electronic states. Maybe it's the bonds on your surface which are rotating. Maybe it's a charge which is going from two other places. Maybe even more sophisticated things where quasi-particles, as Professor Ustinov and others have shown, really correspond to an effective two-level system. We don't know. This is sort of some very generic model. It was so generic it went away. So this is some very generic model of two-level systems that are there. And in particular, I want to pay homage to this very beautiful experiment of Professor Ustinov, who's here and will be speaking later, where these two-level systems are thought to have both an electronic component, so they couple electronically to your qubit, but if they're structural, they should also couple to the strain field. So typically, we don't have a handle on the two-level system. We're measuring electronically these superconducting circuits. But in this experiment, they literally put, figuratively, literally a screw on the problem to go ahead and add strain to the system and actually sweep the two-level system. And the spectroscopy of that is exceptionally rich, beautiful, or messy, depending on which side of the problem you want to look at. So there's a lot of two-level systems, and they even interact with each other. So again, another whole genre of physics to try to understand what are these systems, how do they interact, and in fact, how do we get rid of them or passivate them to improve these qubits which like to talk to the outside world. Then there's the junction. You see, the junction inside also has dielectric materials. In this case, we're looking at aluminum, aluminum oxide, aluminum. And if you think about the material inside, perhaps one of the reasons we have not been troubled by this yet is that it's really small. Right? These are sub-100 nanometer junctions. If you do the estimation of at what level of coherence will we be plagued by the Josephson junction, we're starting to get there. As you start to remove the oxide from the outer surfaces, the junction starts to matter. And if we have, let's say, a few hundred microseconds of coherence time today, to exceed some milliseconds, we will have to pay attention to the Josephson junction inside. So this is where it's a very long file. I've clicked, so I'm in the queue while the computer updates. And I'm supposed to make, it did it. Otherwise, I was going to make jokes until the next slide updated. So here's a high-resolution TEM of that cross-section of a Josephson junction. It's quite an exquisite picture taken by the LBL folks that work on this National Center for Electron Microscopy. You can see all the different grain edges there of the little chunks in the aluminum piece. And you can see that little sandwich layer of aluminum oxide in between. It's not flat, it's not uniform, it's not pretty, but it's worked for 50 years. And part of that is because these junctions are very spongy. You can go ahead and take out the strain by having this amorphous layer. So on average, they give you a very uniform tunnel current. If you start to look about fluctuations, that story may be very different, right, in these. Moreover, we can go ahead and take a scan. So here's a zoom in. That's the 10 nanometer scale bar there. You can now go ahead and zoom in on this barrier and look by chemical analysis or scattering analysis how much oxygen and aluminum you have as you go across some region of the barrier. And it changes a lot. So in fact, how does that play into the performance of your qubit will still be an important issue to look at. Okay. So enough about materials. What I'd like to do is tell you about how to go beyond this very simple circuit. This circuit here, again, is the Josephson junction capacitor piece. And there are really three energy scales in this circuit. There's the energy you store in the capacitance, either the linear one or the one in your junction, and the energy you store in the inductance, which is divided between the kinetic inductance of the junction and the magnetic inductance of your inductor. So that qubit that I showed you that was just an L and a C, roughly speaking, is, goes into the name of transmon. There are other qubits in this family where I can change the ratios of L and C. And they may become more or less resilient to noise that you have. That's not building in topology into your Majorana modes. That's just using parameters which are more favorable for a given setup. But you could start to build in topology into this system. the typical Josephson junction has 2 pi periodicity. You can start to look for systems that have pi periodicity, in which case you would have 2 ground state solutions as a function of the phase difference across the junction. That would allow you to protect more accurately your information from the outside world. And how do you do that? This is the original proposal by Brooks, Kitaev, Preskill for looking at something that was called the 0 pi qubit. So let me walk you through a little bit of this picture. There's a Josephson junction, there's an inductor, there's a capacitor, but then you have another rail of a Josephson junction, inductor, and capacitor. What's happening here is that you have Cooper pairs that are transiting across this junction. You have Cooper pairs that are transiting across the bottom junction. What's interesting is you can actually correlate their behavior and you make kind of an exciton, where you have Cooper pairs on the top and Cooper pairs on the bottom, right? And they track each other. And if you pick this capacitor and inductor correctly, they will not go from the top layer to the bottom layer. So effectively, you've now created a circuit where you are not looking at the transport of Cooper pairs, but the transport of pairs of Cooper pairs. And you can do the same with fluxons, where you have not one fluxon, but pairs of fluxons. This device, of course, has 4 terminals, so it's not exactly your 2-terminal qubit, so you just fold it together, connecting 2 of the phases, and you get a 0 pi qubit. Okay. So just to show you, if you want to increase the complexity of the number of junctions you use, you can start to get things which are more protected. And there's an entire zoo of circuits to look at, and this is an active area of research. Okay. So in the last 10 minutes of the talk, I want to talk about noise. Professor Wiesendanger showed us this nice plot of quantum volume, saying how big is your Hilbert space. You can think about it this way. If you have 10 qubits, you program something in 1, by the time you get to 10, number 1 may forget. Right? So you have not created that full size of Hilbert space that you need. So we have to think about what noise is really present, right? And what can we do about this noise for more intelligent solutions at error correction or noise mitigation. Okay. So we can have a long discussion of the mathematics of noise, but I will try to use my arm as the olive branch, if you like, to make this a bit easier. So typically for the experts, you write out an error channel in terms of polymatrix, so you figure out where the errors are, whether they're errors in the x rotation, y rotation, or z rotation of your qubit. But here's a very simple way to look about it. If you have a 2-level system that you can parameterize on the surface of a sphere, that's basically represented by a vector like my arm here. Okay? If that vector jitters, so you see I'm jittering my arm like this, then if you average all of those together, it appears as if the average length decreases. Right? So in fact, I'm going ahead jittering this around and the length decreases. That's called depolarizing noise. And what I've done is I've introduced an error channel equally along x, y, and z. Okay? So the statistical average of that is a vector which is smaller. You can have a particular noise where you do this only in the xy plane. That's typically dephasing because you're messing around with the angle on the plane. And then you have this type of noise which is particularly nasty. Right? And only recently I think we've become very aware of this. The dephasing also causes this kind of perturbation, but only along x and y, because it's not the z which is changing. This error is called a coherent error. So I have, for example, my hand, and I try to make it point this way, but I mess up, it points this way. Okay, so I have an angular deviation. Well, you may say that's not really an error, right? It means I just missed the target. It's not as if I've shrunk the block vector, and that's absolutely right. So for a long time, we thought we were dominated by T1 and T2, which is this random fluctuation that reduce your noise. But in fact, it turns out you have a lot of this noise. This noise is actually much worse for running a quantum circuit than this one, for the following reason. If you have random fluctuations, you average away, and they scale as square root of n, the number of fluctuations. If you have an angle, it just concatenates, right? And your arrow points very far away from your original state. And if you could stop that noise or change it, you can run much more complex quantum algorithms. And that's what I want to show you in the last few minutes of the talk. Oops. So what's the difference? Coherent errors, they really represent, if you like, imperfect unitary operations. You would like to do a rotation, but you kind of mess up. You get the angle wrong, you get the axis wrong, so on and so forth. They maintain quantum coherence. It's not as if you've lost your quantum state. It's just a different quantum state than the one you wanted. They can be constructive or destructive. Maybe you get lucky, and somehow those angles add up in a way that they cancel. Okay. So very difficult to predict, and they have a quadratic impact on accuracy. Stochastic interactions with a noisy environment, such as pure dephasing, they do not maintain quantum coherence. So your vector is shrinking. Information is lost to the bath. You cannot get that back. Okay. So you may think that's really bad, but in fact, they only have a linear impact in their scaling. Okay. So the real question is, which one do you have? How do you check, in your quantum processor? So that story starts with this technique called randomized benchmarking. Okay. Randomized benchmarking says you prepare a state, run it through some set of gates, undo them, and see what you get. So let me go ahead and sort of demonstrate with my hand again. I start with this state, okay? I want to rotate 90, 90, 90, 90, 90, right? And come back to this state. So that's the sequence. If I have a little bit of noise, I miss, and I'm just a little bit off, right? And the amount that I'm off by tells me the error. That's the idea of randomized benchmarking. You go through all the gates and see how far you are off on average. Okay. So you repeat this, you fit a decay to this, and you get a total error rate. However, this only tells you about this kind of stochastic error because you're averaging the rates. You're not really figuring out whether you have this misrotation or just some stochastic noise. It doesn't tell you that. What you can do is at the end of this randomized benchmarking sequence, measure the length of your block vector. And that will tell you not only how much have you deviated, but how much has the vector shrunk. So that gives you a sense of what's the balance between these two errors. So if you look at here, for 1 qubit gates, the total error rate is 10 to the minus 3. That's what you were indicating on your plot, right? And the coherent error rate is almost the dominant error in there. So that's a significant source of error. It's not the stochastic noise that's there. And if you run 2 qubit gates on pairs of qubits, the same story. The overall error is bigger, but it's dominated by this kind of coherent error. So how do you get rid of this, or how do you turn some of this coherent error into stochastic error? Let's go back to this picture. I wanted to hit this point here, but every time I do it, I miss. Right? That was the picture I gave you. So on average, it looks like this. The vector is shrunk. The idea is, can I now go ahead and prepare an algorithm where I add some degree of randomization to stop the accumulation of errors? So in this notation, you have 5 qubits, say. They're going to run these particular gates, no matter what they are, X gates, Hadamard gates, etc. And what I'm going to do is I'm going to add random rotations in between. So what this does, it stops the accumulation of this coherent error. They're no longer correlated as you go through. And you may ask, well, this is going to make the circuit more complicated. Actually, it doesn't, because I can recompile those into the original rotations. So before I showed you a circuit 90, 90, 90, now I'll do 92, 93, 87. So adding that little randomization kills the coherent error, or should kill it. And in fact, this is experimental data showing you that we really are dominated by these coherent errors. Right? And in fact, if I now randomize even 10 times, this is the error budget which is there. The yellow is the coherent error, the yellow is the stochastic error, the blue is the coherent error. And you can see the original budget had coherent error much higher than the stochastic one, but after randomizing, I can take that coherent error to 0. And in fact, make it dominated by stochastic noise. I can do that for actually any 2 qubit gates if you want, not just the one that I've shown here. So it's generally a useful technique. So the final piece of this is, can I run an algorithm that I couldn't run before by using this randomization? And the answer is definitely yes. So let me show you that in the last few minutes, and then stop for questions. This is a popular algorithm which has come out. It's called the quantum imaginary time evolution algorithm. So the general idea is, as we know in quantum mechanics, if you have a state, you evolve it as a function of eigenstates that have some simple time dependence e to the minus iet over h bar. Right? So those are the eigenvalues. They cause your state to move forward in time. How do you find the e sub m? That's the hard problem, right? The spectrum of eigenvalues that are there. If you go ahead and turn time to imaginary time, this looks strange, but it works. Right? If you turn this time to imaginary time, That exponential then becomes a decaying one. Right? And in fact, depending on the size of your eigenvalue, you will decay either faster or slower. And in fact, the ground state is the one that will decay the slowest. And that's the smallest exponential that's there. So if you classically, you do a simulation, you just wait and see what the computer returns after a long period of time. That's the ground state. Quantum mechanically, you have a problem because this evolution is not unitary. So you cannot map it directly onto a quantum computer. So the best you can do is break it up into little chunks, and that in the field is known as a Trotter expansion. So you just think of little unitary chunks for doing this. And you can go ahead and see if you can obtain the ground state. So here in a snapshot, we've actually solved the 3-qubit transverse Fields Ising model for where the coefficients between this H and J are 1. That's the hard limit of this particular Hamiltonian. The blue curve, the green curve, excuse me, represents no error mitigation, no randomization, etc. And what's plotted here is the average energy error and the error in the estimation of the state. So here I'm measuring the eigenvalue, here I'm measuring the eigenstate. And you see this line here, this is of order 1. So the average energy error is of order 1. You will really get it wrong, right? We can't actually run that algorithm. And the same with the state. But after you go ahead and turn these coherent errors into stochastic ones, you can see I can bring it down to almost 10 minus 3 for chemical accuracy. Just by changing the noise in the system. I haven't done anything with the qubit. I'm just saying that I don't want to accumulate all these errors when I'm running 50 C0 gates or 40 C0 gates, which would give me a trash answer after running 50 operations. Pick a very different problem. You can now do a simulation of nuclear collisions, where I go ahead and think about two nuclei interacting with the following Feynman diagrams that have a spin-independent and spin-dependent piece. So that evolution, again, same story. You can write as some kind of Hamiltonian here that has two pieces, and you try to estimate one of them, okay, by this quantum methodology. And here's the circuit. It's got a lot of stuff. It's got each unit cell has 3 C0s, a bunch of rotations, so on and so forth. You run it without error mitigation, no hope to actually get any answer at the end. So here the scattering cross-section of the 4 states that you should get in a nuclear deuteron scattering problem. And what you see here are the lines, in fact, are the simple exact calculation for this quantum system. The dots represent what we get out of the quantum computer. Original data, no mitigation, way off from what you predict, and this is the error. And as you start to randomize it and then adjust the length of your state, etc., this is the quality of data that you get at the end, right? Just by adjusting the noise in your quantum simulation. So again, showing you it's quite important to understand the type of noise and many-body noise you have to do not only error mitigation, but as you were mentioning, to really think about how to correct in a fault-tolerant manner errors and how to characterize them. So in my last slide, I think I want to leave you yet again with a philosophical outlook. So where are we in quantum computing? I would compare that to a journey through the Alps. And these are some photographs I took of Mont Blanc last time there before COVID. So the first processors, we were planning the route. The summit is somewhere over there. You see all these people looking there saying, how the hell do I bridge this gap? Right? That's sort of what we're thinking also with quantum computing. How do I bridge that gap? Okay, so start to develop tools, control quanta, and then you get closer. There's always clouds. You don't always see the rock face. Sometimes they clear up. You start to see the rock face, which is there. And if you like, this is the first quantum systems to exceed classical resources. We start to get a sense that you could do something. And then the real advantage will be to actually reach the summit, where you can make a quantum computer do something, right, that a classical computer cannot. And that's the development of error management, robust devices, error correction, impactful algorithms. But the thought I want to leave you with is it the end of the story? If you fixed the vacuum tube, would you know what the transistor would turn into and what metaverse or Facebook would look like 40 years later? Probably not. And if you cross to the other side of the Alps, that's the Italian town of Cormeyer on the backside. So you have no idea that that's what's on there on the backside. So what I want to leave you with is maybe the best of quantum still yet to come, figuring out what you can do with this technology. And to get there, we really need to think about new modalities for robust encoding of information so that you can access it and hide it on demand. Development of systems level engineering, not just one qubit, but in fact, how does a many-body system interact? And engineering which is targeted for quantum-specific solutions, for wiring, for data transfer, etc. And then also to rethink about the right algorithms for the hardware you come up with. So let me stop there and take your questions, and thank you for your attention.
Thank you, Professor. course, thank you for the excellent presentation. If I may ask, what is the main source of the, I'm here, the coherent errors? I mean, XYZ axis errors, they could be due to, gate measurement errors or, gate operation errors. But what is the major source of the crosstalk between the qubits?
Crosstalk comes in two flavors. There's classical crosstalk and quantum crosstalk. So the classical crosstalk is that you want to control one qubit, but since your wavelength is bigger, you are not in the you're in the near field regime of your microwaves. So in fact, through coupling, through dielectrics, etc., you will excite some other qubits. And that happens in some n-body fashion. And in fact, we can decompose that into all the n-body correlators, like condensed matter physics, and figure out where's the two-body correlator, three-body correlator. So that's what happens on the classical crosstalk.
Yeah.
The quantum crosstalk, even more subtle, right? Because in fact, these are dipoles, so you will always have a dipolar coupling, right? A ZZ coupling that's there. So you can kill that dipolar coupling in many ways. You can try to come up with not just a capacitor coupling it, but a capacitor and inductor, which has the opposite sign. So crosstalk comes in all different flavors, and that's what gives you many-body errors typically that are there. And going in 3 dimensions also helps with that.
Yeah. Photonic qubits, I think, in that respect, right? Crosstalk, they wouldn't have crosstalk or kind of errors. They would have only XYZ measurement errors, right? It seems.
Right. So from the point of view of crosstalk, they're better, but then they're difficulty there from the point of view of talk, right? Then they don't talk to each other. So you can choke off the complete channel, but then they have no.
And there are some ways, to have like CNOT gates, right? In between.
You can do cluster states. You can do cluster states. You can feed forward. You can bring in the nonlinearity from the measurement, right? That's there, and then your measurement will have crosstalk. So it's a challenging problem to get an extant array of quantum entanglement to be controlled on demand without looking at it.
Thank you. Any questions?
First of all, thank you for a marvelous talk.
Dankeschön.
I have a question. Do you have an understanding at a microscopic level why the aluminum-based Josephson tunnel junction perform better than the niobium-based tunnel junctions? It would be a natural choice also for the tunnel junctions to use niobium. Do you understand why there is a difference, say, in the performance, and what makes the niobium-based junctions worse?
So understand is a strong word, so I will share some thoughts on that particular subject. Typically, niobium junctions that are made still use aluminum oxide. So when you make niobium tunnel junctions, you grow a very thin layer of aluminum that's proximatized by the niobium, then put aluminum oxide, and then grow the niobium counterelectrode. Those junctions can be made to have high coherence. The Lincoln Labs folks have done that. So that's maybe the first answer. They can perform as well. If you want to make a junction purely of niobium with the niobium oxide, it's a surface chemistry problem in all of these things. Whether you use rhenium or aluminum rhenium or van der Waals materials as your thing, or boron nitride, or any of these other materials, it's the dissipation of that material, the interfacial transparency, and the stiffness. And that's typically one of the biggest problems in epitaxially grown junctions. You grow a very thin layer, the transparency is very high, right? So if you have even one channel go bad, then your junction is short, right? So that's one problem that's there, especially as you cool it down, because it will be lattice mismatch in typically all of these substrates. The second challenge then, of course, is do you want it to behave properly on average or each element? Right? So in this particular case, this is in this Landau-Buetiker formula, the case of many channels with poor transparency. So on average, it seems to work. If you want to go to the limit of either a wire or a point contact or something that has high transparency, then you have to deal with this channel fluctuation problem.
Okay, thank you.
Okay, we had another question right there.
Okay, I guess it's me. I have 2 questions. One is that I guess for the beautiful algorithm at the end, somehow the algorithm is known. There is some sort of a compiler or something that adds these other gates. Is it kind of theoretically known how good that can be? Because you're trying to get an inverse, but there is no inverse. Yes. So, but is there like an approximate theory to say how close can we get?
Yes, it's a very good question, right? Of things that how close to the, if you sort of have this kind of quantum approximation to things that are classical. There is a good theory for this. Turns out I think you can get, at least in that particular algorithm, you can get to better than 10 minus 3, which is good enough for operational purposes. But it depends on the structure of the interaction that you want to look at. So So if you have, for example, a many-body Hamiltonian with many levels of interaction, it's not so obvious, right? So it depends on how you want to fracture that circuit. That's the first question. You have two. Right?
Okay, yeah. The second one is when we talked about niobium 2, oxygen 5.
Yeah.
What is the participation ratio? Does it matter really? Or what level we are looking at?
So that picture, if I go back to it, see if I do this and hold it down, how fast it goes. Not very fast. So if you look at it, we're talking about 3 nanometers on a 5 nanometer oxide layer on top. So that's basically the amount. Oops.
Yeah, but from microwave perspective, how much
it
are
matters
they
a lot.
contributing?
In fact, it's dominant because the point is you want to create a circuit of loss 10 minus 6 and you put a material of loss 10 minus 2. So it is the dominant.
But is it participating enough? I guess that's
Yeah.
okay.
Absolutely, because what's happening here, you can use this one. The electric field is concentrated right there on the top. So in fact, it is maximally participating in that. And what's participating even more is the silicon here because it's between the electrodes.
Yeah,
So
yeah.
absolutely.
Thank you.
Question here.
Any other questions? There's one over there. Okay.
When I was a little in kindergarten, the aunties, as we call them, had a very neat way of suppressing our random fluctuations. And this was whenever we went anywhere, they told us to hold hands. Okay, so my question is, can you somehow have 2 qubits, one monitoring the other, a sort of coupled state that would then tell you if they are drifting?
Yes, it's a very good question. So in fact, it's this entire subject of how to encode information in more robust states that are there. So in this case, if you have a dimer, right, they would actually go ahead and either, you can use them as one as a sensor of the other, or one to co-scatter. Yes, so both of these things are being done at the moment. One of the things we do is cheating a little bit, but maybe useful. We hold hands in a different way. You can have this transmon with 3 levels, right, and use the 3rd level as a sensor. So you're holding hands with yourself. So yes, so you can try to correlate these and also try to correct for them, and you can do continuous error correction, which I didn't talk about today, but that's something with continuous quantum monitoring you can undo. So yes, all of these things I think are important, either autonomous or with feedback. So autonomous meaning you hold hands but don't look. Feedback, you hold hands and measure and then do something.
Okay, Professor Gencer.
Thank you very much for the nice review and the current achievements you have already. Very simple and short question. What is the current state of prototypes by IBM, Google, and they're using aluminum oxide junctions? What would be the advantage of this and disadvantage? Have you had any chance to make a comparison?
Sure. So the question, of course, to restate it is how do you compare, for example, this architecture or other architectures within the superconducting field? The point is, I think that there are many good solutions that are out there, and all of them are some distance away from the final product. So if you take this problem of transmons, right, then we need to make really perfect surfaces, interface qubits, wires, so on and so forth. And that is really the approach that much of industry is taking. They're all typically working with transmon qubits. It is a very engineerable approach. You agree on the structure and go ahead and I want to improve the quality, and you have lots of benchmarks and metrics. So what I was taking is perhaps more of a professorial approach, saying that maybe we want to change the target, right, and look at some other targets that are there. And it's not obvious which one will be better. So I think there are all approaches which are working in parallel. We already had one comment on error correction and the difficulty of it. So all the commercial entities are doing surface code error correction, typically, which will require many, many 100,000 qubits for encoding. So whether it's easier to come up with a better code or a better qubit remains to be seen. That was the most political answer, Professor Gencer, I could give you about the state of the field between all entities working in it. Tonight with the Turkish night, I give you the real answer.
Any more? No. Okay.
Thank you again. Thank you. Teşekkür ederiz.
Hopefully see you next time.
Good. Thank you so much. Take a picture.
Should I announce the next speaker? Okay, Okay, sure, okay. Thank you, Irfan, that was great. We'll talk later. So our next speaker is Paul Kornsrad from Eindhoven University of Technology in the Netherlands, and the title of his talk is Atomic Scale Microscopy of Self-Assembled Dots Grown by Droplet Epitaxy.
Good morning. I would like to thank the organizers, first of all, for the kind invitation to speak here. It's an honor to be at this meeting and also taking care of me in a proper way. We have seen, why is this not working? Yeah. We have not yet seen the beautiful city of Bodrum. Maybe you have, but I haven't. But it's a beautiful city. And it's also a city with a very long history. So it's not only beautiful to see what's on the surface here, but also we would like to know what's underneath the surface to learn the rich history and how everything actually came together here. So it is important to do archaeology. And archaeology you can do in two ways. Of course, you have to dig a pit to go underground, and then you can look at the side wall of the pit that you have dug, and by that learn what's in the ground. Or you recover every element that you pick up while you dig the pit, and you make a 3D reconstruction of what was in this pit. Today I'm going to show you two techniques that I've used, but especially a sidewall techniques, to do what I call, sorry for that, whoops, atomic scale archaeology. So I'm going to look at what's underneath the gross surface of my structures to learn about the material. And as we have seen, this can be very important for the applications that we have in mind, that we really need to know many details about these structures. And as an example, I want to start here, but that's just for starters, with this well-known Stransky-Krasnov quantum dots. And you can, for instance, think about first growing gallium arsenide, then depositing a thin layer of indium arsenide. You form the so-called wetting layer, which is about 2 monolayers thick. And if you then continue with the growth of indium arsenide, due to the strain-induced mismatch between indium arsenide and gallium arsenide, we start to form three-dimensional structures on the surface that can be further overgrown with material. And this is an AFM image of the quantum dots, the SK quantum dots, before overgrowth. Already we can learn a lot of things about these quantum dots by looking at these AFM images. How many of these nanostructures do we have? What is their size, their shape? But actually, more importantly, I would like to know what these quantum dots look like after they have been overgrown with further material. Do they keep their shape after capping? Can we also look inside the dots? Can we see if there is any composition profile? What is their size after capping? So we really need to know a lot more as just what we can obtain from an AFM image. And for that, I'm using cross-section STM. The technique works as follows. I ask one of my friends in the world who is making good material to send me a piece of that, and in Eindhoven we clamp a piece of that material in a holder, we place it in vacuum, and under ultra-high vacuum conditions we cleave the material, and that we approach with an STM tip, and by that we can make images of the cross-section through all the layers that were deposited on the wafer. And we can look at the nanostructures that are inside. This is an example of a cross-sectional STM measurement on indium arsenide Stransky-Krasnov quantum dots in gallium arsenide. We can see the wetting layer here that is formed before we get dot formation, and we can see beautiful quantum dots in this measurement. These dots gave rise to luminescence at something like 1.15 electron volts, and the people wanted to have the luminescence as a different region, so they annealed the sample, and indeed we see a nice shift of the luminescence. But in my microscopy technique, I also can see now beautifully how the indium atoms have diffused through the material and what the size and the shape of the dot after the annealing is. In this presentation, I want to focus on dots that have been grown by droplet epitaxy. And that's a more advanced technique as what I just described to you. And in the case, for instance, of gallium arsenide quantum dots in aluminium gallium arsenide, the technique works as follows. First, you grow your aluminium gallium arsenide at standard growth conditions. We cool down the surface to something like 200 degrees centigrade. We remove the arsenic flux. That is very important. Then we deposit pure gallium. And there is enough gallium that actually droplets of gallium will form on the surface. Then we open up the arsenic flux again, and then we will crystallize these gallium droplets and to form gallium arsenide. And after that, you can do an overgrowth. This is an example of AFM measurements that were performed on droplet dots that were grown under different arsenic pressures and different growth temperatures. And you can immediately see that the height profiles and the size and the shape of these dots strongly depend on the arsenic pressure that we use during the crystallization of the dots or the growth temperature that was used during the crystallization. So you have a lot of freedom in making these structures. So why droplet dots instead of SK dots? Well, there is a way more freedom in control over size, shape, and composition. Turns out that you can even make rings using these droplet dots and even more complicated structures. In principle, you have a possibility to grow the dots completely strain-free, which can be an advantage for some optical properties. There's little to no wetting layer formation in this process. And most importantly, they have interesting aspects for the creation of entangled photons. And I think that's very appropriate for this meeting here where we talk about quantum related properties and materials. And we have worked in an ITM network on looking at these droplet quantum dots and how they can be used for entangled photons. And I want to measure especially also the cooperation with Toshiba, who is making real-world systems that actually produce entangled photons. This is the outline of my talk. I already have given you a short introduction. I'll talk a bit about now composition control in and near quantum dots. Then I'll show you how we can control the height of these quantum dots and how that affects the emission wavelengths and the PL line widths. I'll show you how local etching can actually occur under the quantum dots and how it can affect fine structure splitting. And I'll end with some conclusions. That was too fast. Here we see one of the very first STM images that we took of a droplet quantum dot. This is a gallium arsenide droplet quantum dot and aluminium gallium arsenide. The aluminium gallium arsenide has this kind of speckled contrast that is due to the local variation in aluminium and gallium concentrations. Where it's brighter, we have a more gallium arsenide-like composition. When it's dark, it's more an aluminum arsenide-like composition. Well, here is my self-assembled dot. We see a little bit of the wetting layer, very weak. I can measure the lattice constant along this line, so going from the barrier material into the dot material into the barrier material. This is the height contour that we take with our STM tip. If I measure the distance between the atomic planes, you can see that the lattice constant is exactly everywhere the same. So indeed, these dots are strain-free, as I promised that would be possible. And this is very different from the indium arsenide, gallium arsenide SK dots. You actually make these dots because of the strain mismatch, so these dots will always be internally strained. I'm going. Again, I show here a little bit of the wetting layer. You see it's very weak, so indeed these droplet dots produce hardly any wetting layers. This is also very important if you look at the luminescence from the quantum dots, because the luminescence can couple to the wetting layer, and that is seen as a disadvantage. This is a bit annoying now. It's too slow, I think. What we also noticed is that there is an area above the dot that seemed to be very aluminium rich. You can see it's very dark, and dark means that there is more aluminium in that area. This is a general thing. These are dots that were grown. The previous dots were grown in Japan at NIMS. These are dots now grown in Milano. Here we see the gallium arsenide droplet dots. There is again such an area where we have an enhancement of the aluminium concentration. That effect seems to depend on how much gallium we actually deposit, so how big the quantum dots are. If you go from 1.5 monolayers of gallium to 3 and to 5, we see that this enrichment of aluminium above the dots is enhanced. With atom probe tomography, the technique that we can use to make a 3D analysis of where all the elements are, we can see that indeed this aluminium-rich area is everywhere above the dots. So this is the indium isodensity contour. So here is my gallium contour. Here is my gallium arsenide quantum dot. This is the aluminium contour, and here we see the aluminium-rich areas. And you can see that indeed this aluminium-rich area overhangs like a little cloud over this hill that is the quantum dot. And remind, please, this is in the order of 20 nanometers. You also can look at the profiles that we can take here right through the center. We can look at the arsenic counts, that's 50%. Well, that should be the case. Then gallium goes to 50%, so inside the dot, indeed, we have pure gallium arsenide. And above the dot itself, we see that the gallium concentration drops, the aluminium concentration increases. So here we have the aluminium-rich area that is shown by this blue cloud. What is the process that is responsible for this aluminium enrichment above the dots? If you have formed the dots and you start to overgrow the material, the surface wants to flatten out. So there is mass transport of atoms that arrive in the area here above the dot that will go to the sides in order to level the structure. Now, gallium atoms are more mobile as the aluminium atoms, and that leads to this net enrichment of aluminium above the quantum dots. Can we suppress this effect? Yes, we can, and for that we use double capping with flashing together. So here is my substrate on which I've grown the dot. I do a first capping, but the first capping has a height that is smaller than the height of the quantum dots. Then I do a flash, that means I raise the temperature and I evaporate everything off from the surface. I get a flat surface here, and then I can do an overgrowth with a second capping, and then we have a structure like that. Did it work? Well, here is the dot grown in the standard fashion. We see the aluminium-rich area above the dot. Here we have done this 2 nanometer cap. The first capping layer was 2 nanometers thick. Then we do the flash. Indeed, all the aluminium enrichment is gone. But you also can see that the top of the dot is rather flat. And we have a height, if you would measure it, is exactly 2 nanometers. We also can do it with 4 nanometers. And that way you see that you also have now a way to control the height of the dots. And that brings me to height control of quantum dots that you can obtain by this double capping and flashing method. Here are again a few quantum dots that we grow. This is a 1.5 monolayer gallium deposition. And here we have a 5 monolayer deposition. But we can see that we can control the height by the capping that we do in the material. And indeed, we see that there is a nice control how we can limit the height of the quantum dots. Without this double capping method, we already noticed that you can control the height of the dots also by how much gallium that you deposit, or by controlling the temperature and the arsenic flux during crystallization. And this is work that we did together with the colleagues in Milano. And I already showed you this image there. We see that the quantum dot height and the profile actually is strongly dependent on the arsenic pressure during crystallization, or on the growth temperature during crystallization. And I can characterize these profiles with the facet angle, so that's the angle of this facet that we see over here. That strongly depends on temperature and arsenic pressure. And the aspect ratio, that's the height versus width. And if we look at the aspect ratio now as function of these parameters, we see there is a clear dependence, both in the pressure series, the arsenic pressure, or in the temperature series. The colleagues in Milano were able then to model this process, and the modeling of the process is based on two crystallization effects that are important in this work. Here we start with the surface of gallium arsenide. We have the gallium droplet over here, and now we introduce the arsenic to crystallize the dots. It turns out that the crystallization first starts at this liquid-solid interface. Here we have the gallium liquid on top of the solid gallium arsenide surface. Arsenic atoms that come in give rise to crystallization in this area. So from there it will grow and expand. But also we have gallium atoms that actually can still diffuse, for instance as function of temperature, but also as function of the arsenic pressure, to areas outside this crystallization area, and by that broaden the dots. And these two processes were modeled, and with that they were able to come with a universal relation for the facet angle and the aspect ratio as function of crystallization temperature and arsenic pressure. And you see that nicely can be described over here. So there is a good understanding of which processes are involved in this gallium arsenide crystallization process. Again now with the colleagues at NIMS in Japan, we looked at gallium arsenide quantum dots in aluminium gallium arsenide. In this time, the height of the dots was controlled by depositing more gallium. And here we see the height of the dots as we measured it with cross-section STM. There is a nice height relation depending on the amount of gallium that has been deposited. And there is a base length also which is more or less constant, where you can see that this base length is more or less constant, but the height can be varied very nicely with the amount of gallium that is used. By the way, different from before was that there was an annealing step after the dot formation process, and that actually gives rise to the shape that we see here. If you then look at the PL measurements for these dots, on the left I show you the macro PL, and the macro PL shows a clear shift of the PL luminescence as function of the amount of gallium that has been deposited. And then in the micro PL, this broad peak actually breaks apart into individual peaks that are related to individual dots in my micro PL spot. You can measure the widths of these PL lines, but already from this graph you can see that the widths of the lines here for the 7.5 monolayer dots, the higher dots, the width is much higher as for the dots which are not as high. So here we have the line width of the quantum dots as a function of emission energy that is directly related to the height of the dots or how much gallium that we deposit. And for the higher dots, the line width becomes smaller. Why is that? Well, the idea is as follows. Here is my quantum dot, and in the quantum dot I have my exciton consisting of an electron and a hole being trapped in the dot. And if I have a dot which is very high, I can polarize the exciton very easily. I can pull the electron and the hole apart very easily. That's not so simple when the dot is not so high. So the Stark effect that you have, the detuning of the luminescence, is bigger when you have a higher dot as when you have a lower dot. And now the cause for the fluctuations that we see are in fact charges on the surface that change their charge state. By that there is an oscillating electrical field, and through the Stark field that couples to the detuning of the exciton and giving rise to the broadening of the peak. So if you want to have droplet dots that show long coherence or a long lifetime, it's important to grow quantum dots with a low height, or of course try to avoid these fluctuating impurities on the top of the surface. That's the other way to go. There was another surprising effect that we saw when we were looking at these droplet quantum dots, and that was the effect of local etching that I would like to describe to you right now. This is again a gallium arsenide droplet dot in aluminium gallium arsenide. This is the surface on which the the gallium droplet was formed and which was subsequently crystallized. But you see that underneath the dot there is a gallium arsenide rich region. And the reason for that is that the gallium droplet can actually etch into the underlying aluminium gallium arsenide. This is a process that was described by colleagues from Hamburg. And here we see this effect of local etching. The indium droplet liquefies the gallium droplet, why do I say that all the time? The gallium droplet liquefies the aluminium gallium arsenide underneath. By that, gallium and arsenic atoms get picked up and go into the dot. If you look closely in the gallium arsenide dots, we can see individual dark features. And those are individual aluminium atoms. These aluminium atoms have been brought into the dot by this local etching which pulls up aluminium atoms in the etching process. And by that is contaminating your pure dot. A beautiful example is also shown over here in these dots from Milano. A gallium arsenide, almost pure dot here, but sometimes these dots start to etch into the substrate. We see here now that there is a concave bottom, and we see lots of aluminium atoms inside the quantum dot. So there's intermixing and etching often go together. With that knowledge, we were actually, we came into contact with the group in Cambridge, Toshiba, in the network, and they were working on indium arsenide, indium phosphide droplet quantum dots, which were grown in Sheffield. John Heffernan is here as one of the growers that was involved in that. And the nice thing for these indium arsenide, indium phosphide droplet quantum dots was that they could actually tune them to the wavelengths for communication of 1.55 microns. And they use these quantum dots for the production of entangled photons. The process is as follows. Indium droplet formation occurred at 400 degrees centigrade. Crystallization was about 500 degrees. And there was a capping with 30 nanometers of indium phosphide, followed by even more indium phosphide. What they noticed in these quantum dots is that the fine structure splitting is very small. And let me take you through that a little bit. If you want to create entangled photons, you have to create a bi-exciton state in your dot. So we fill the dot with 2 excitons. And then actually when the photons come out in a cascade manner, you have 2 paths for the recombination. And depending on the asymmetry of the dot, so whether it's a square or an elongated square, there can be some splitting, some polarization splitting of this intermediate state. The more symmetric that you make the dot, the smaller this asymmetric splitting will be, and the better entanglement of the photons that you will have that you create in the 2 steps. So it's very important for photon entanglement that you have a symmetric dot where this fine structure splitting that we see here, or polarization splitting, is as small as possible. This is the work from the people from Sheffield and Cambridge, and they looked at SK dots. And the SK dots, they have a rather large fine structure splitting, as you can see along the axis here. This is the emission wavelengths. They have a rather large fine structure splitting. Also here in the histogram you can see it. But then when you go to droplet dots, either from indium arsenide on indium phosphide, or from gallium arsenide on indium arsenide on gallium arsenide, we see that the fine structure splitting is way smaller, but the advantage of the indium arsenide dots in indium phosphide is that they emit at 1.55 micron. With our cross-section STM technique, we could beautifully resolve their dots, and already from this you can see that they look rather pure in indium arsenide. So in order to prove that better, we looked at the lattice constant profile over this line here, so measuring the distance between the atomic planes. And we made an estimation of what the profile should be, the lattice constant profile. profile. That's the simulation here in red, and the measurement is shown in dark. And the simulation assumes that the dot consists of pure indium arsenide. So I think we see that indeed it's possible to grow pure indium arsenide quantum dots on indium phosphide in this technique. A bit unfortunate was that we saw this edge pit formation very often. Something like 60% of the dots showed an edge pit underneath. And, well, the size and the position of the edge pit was very different and differed from dot to dot. It was also interesting that we saw that if you have a bigger edge pit, that the dots seem to be smaller. Of course, that's related to the availability of the indium that you have in the material. We were worried that this edge pit actually also has an effect on the fine structure splitting. And if you break this symmetry by pulling the electron and the hole laterally apart by this edge pit, that actually would increase your fine structure splitting. So we looked at, and this is a modeling we did with the group of Michael Flatte in Iowa. We looked at quantum dots with an edge pit underneath, and first we had an edge pit right under the center of the dot, and we increased the size, and we saw that that actually reduces the fine structure splitting. So that's good. That's nice. But when the edge pit moves to the side, then actually increases the fine structure splitting, and that is bad. And because at the moment we have no control over where we actually get this edge pit, it's better to prevent the formation of edge pit than to use it to your advantage. So for that, we worked with the team in Sheffield on looking at dots where we could possibly prevent this edge pit formation. The dots where we saw the edge pit formation were grown below 500 degrees centigrade. And by going a little bit higher in temperature, we actually could remove the edge pit very successfully. But it came at a price. And the price was that now there was a lot of etching next to the quantum dots. You can see already here there is some kind of steep edge, where here we have the pure indium phosphide, but here's the intermixed wetting layer, and actually our dots stand on a kind of terrace. There's trench formation around the dots. I've put circles around it here. Here you again can see these trenches that form around the dot if you grow at 500 degrees centigrade. Something you also do not like and would like to prevent. And with further work, we showed with the people in Sheffield that you actually, this is the processes that we have. Below 500 degrees centigrade, we have the local etching underneath the dots, giving rise to these edge pits, whereas for growth above the 500 degrees centigrade, the indium phosphide surface becomes unstable. Indium atoms can move towards the dot, towards the droplet. Phosphorus atoms can escape into vacuum, and that actually gives rise to this etching of the material next to the dot. Both processes can be prevented, and for that you only have to grow a indium gallium arsenide layer underneath. Presently we're still looking at how thin this indium gallium arsenide layer might be to prevent it, but actually that turns out to be a very effective way to suppress the etching underneath the dots or next to the dot. Before I go to my conclusions, I would like to acknowledge the work of many people involved in this work. It's work that has been carried out over many years, but especially my PhD students here in red contributed a lot to that. And of course, my partners here in theory, Michael Flatte and Craig Pryor, the group in Sheffield who grow the indium arsenide, indium phosphide dots, the team at Toshiba who supported us. Some of the early gallium arsenide, aluminum gallium arsenide quantum dots came from NIMS in Japan, and then some of the later work we did with the Milano team in the European network. Let me finish by showing you what's learned. I think we have shown there are various modes for shape and size control of droplet dots, and especially we can control the emission wavelengths. And I think for communication it's very important that we can operate these quantum dots at 1.55 micron. We have observed unexpected and unique effects such as aluminium enrichment above dots. I've shown you etching below, next to and underneath the dot. I've shown intermixing in droplet dots, but it also showed you how we can actually control all these effects, and that we can make now good quality, clean quantum dots. We also have learned how size and shape of the dots affect the line widths in PL emission, and if we talk about entangled photons, that will improve our coherence lifetime if we have a narrower line width. And we have also shown how you actually can affect anisotropic splitting by edge bits, and how that can be detrimental for entangled photons. So we can actually improve entanglement by reducing this edge bit formation. And with that, I would like to thank you for your attention.
Thank you very much for a great talk. We have a question right here.
Thank you very much for your nice presentation and for your persistency. I remember that you have been doing this cross-sectional STM over a long time, and I admire the recent achievements. My question contains two elements. First of all, the same process of local epitaxy produces drilling, and if you continue this process, you may have quantum rings in the same way.
Yep.
Where are you interested in investigating the structures of another topology? And second question, what are requirements for statistics of samples? How many dots you need in order to get statistically representative results of cross-sectional STM? Thank you.
Well, answer to the first question, our interest was not in rings this time. Although I know that droplet epitaxy is very suited to make beautiful quantum rings or even multiple ring samples. They have shown that you can make nested rings. We were not interested in that at the moment. Concerning statistics, well, when we get the samples, we are very much determined by how many quantum dots per square nanometer or per square micron we have in the sample. We like to see as many as possible dots. Typically, we look at 50 to 100 dots in order to build our statistics.
Thank you.
We have a question up here, and then Herman. Yeah.
Did you also try to probe the confined electronic states and their spatial distribution in these buried dots by scanning time spectroscopy?
Yeah, we tried, but not very successful. So people have shown that it's possible. With SK dots, I think there's beautiful examples of teams that have done it. We have not tried it on these samples. We did one go. We're not too happy with it. Didn't see the need at the moment to go forward with that. So this is why I did not push that any deeper. But yes, it's possible, and it's very nice.
Thank you.
Thank you, very nice. When you talk about pressure and temperature effects on the growth of these structures,
yeah.
Can you control the interface sharpness and the cooling rates so that would give you access to control structural order and segregation, for example?
Let me try to answer your question. I don't know whether I have the right picture for that. No, then I have to go into my reserve slides, which is a bit different. I can show you that afterwards. But in principle, yes. And especially you can see that in the wetting layer. I mean, in the wetting layer, in the case of the indium arsenide, indium phosphide structures, this is an exchange process where phosphorus goes out, arsenic goes in, so then you make indium arsenide in between the quantum dots due to exchange. We do see these layers, they do form, and in the case of SK dots, you really need that wetting layer, so there that wetting layer is much more important than in the case with the droplet dots. I can show you that. But also we see the segregation of indium out of these wetting layers. There's typically an exponential tail of the indium distribution in the growth direction for these wetting layers. But that's something we have done many, many times before. We have not done that experiment, but it's a good suggestion to do. Thank you. Yeah.
Well, if we don't have any more questions, let's thank our speaker.
All right. very much and appreciate it.
The session is over for a lunch break, and any announcements? No? Okay. Enjoy lunch. See you later. Bye-bye.
microphone.
Organization announcement. What is the question? You want to know? Have you
I
made
have
the
no
computer
question. He
or
wants it.
what is the computer
No.
size? Okay. Double, what you want to know?
They ask about excursion. When you'll give instructions on excursion? Tomorrow, right?
Well, I think it looks like the weather forecast for Wednesday looks fine. I think it's going to be boat tour to Bodrum, and you will be able to swim according to forecast. So we need to know the exact number of people attending. We have enough capacity, so no problem. And that's the gift to our guests from the organization, so no need to pay anything. Everybody is happy to swim or just go around the boat and drink beer or anything else to drink. And so it's an enjoyment, so everybody is welcome to sign up and no fee needed. Okay? If this is the case.
Good, thank you.
And you can chair the session, I will be happy to sit over there.
So we start formally with the session. Today we have a special guest star from Switzerland. My dear friend Carlo Trugenberger from Geneva. They speak different languages in Geneva. We're 50 kilometers away, but he'll pardon me that. And he is going to give us a talk on magnetic monopoles and quantum materials, super insulation and the pseudo-gap state, and much more. The stage is yours, Carlo.
Thank you very much. First, lots of thanks to Ali and all the organizers for this opportunity. It's a great pleasure to be here. So I'll try to compete with afternoon siesta by telling you about some exotic states which are possible in quantum materials. So why not magnetic monopoles in electromagnetism? At the classical level, only the equations of motions, the Maxwell equations, are relevant. And there is absolutely no problem in adding, I have to find here, in adding a magnetic current with a magnetic charge to the homogeneous Maxwell equations. F dual is the dual electromagnetic tensor which exchanges electric and magnetic field. And originally the founding fathers did not include magnetic monopoles simply because they never observed ones. So fast forward to the 30s, Dirac, he asked the question just after the development of quantum mechanics, he asked the question, what about monopoles in quantum mechanics? And of course, in quantum mechanics, the equations of motions are no more enough to describe the system. You need to formulate a local action, local in terms of the fields. So when you want to formulate a local action for electromagnetism, you have to include a gauge potential A. You cannot formulate a local action only in terms, in terms of the electromagnetic fields. And this, naively at first sight, can cause a lot of problems because you have strong singularities. However, Dirac showed that if his famous quantization condition is satisfied, the product of magnetic and electric charge is an integer multiple of 2 pi. There is still no problem, and you can have quantum magnetic monopoles. A magnetic monopoles looks like this. There is an infinitely thin and long solenoid bringing in magnetic flux from infinity. And this magnetic flux flows out radially symmetric at the location of the magnetic monopole. And Dirac showed that if this quantization condition is satisfied, this solenoid, this infinitely solenoid, is nothing else than an unobservable coordinate singularity. And today it goes under the name of a Dirac string. So if it's here and you don't like it here because you have some physics going on here, by a just gauge transformation, coordinate transformation, you can bring it wherever you want. So it's no physical, and physical is only the endpoint of the magnetic monopole. Only problem is that the presence of this magnetic string, this Dirac string, forces the possible gauge functions, lambda, here, to be periodic under integer shifts of 2 pi. This is familiar to you in vortex physics. To have a vortex, you need the gauge functions to be circles, compactifier on a circle. And this means that the gauge group that you have is not the group of real numbers, but it's the compact U1 gauge group. U1 is homotopically equivalent to a circle, S1, and a circle and R are locally the same, but not globally. And the difference in the global behavior is just the presence of magnetic monopoles, which are the singularities at the endpoints of the Dirac strings. Singularities, as usual, are no good in physics. They have to be hidden. There are 2 ways to do that. The first was originally proposed by Toft and Polyakov, is to hide the singularities by obtaining the compact U1 gauge group by spontaneous symmetry breaking from a very larger compact gauge groups. For example, the grand unified gauge groups SU5 or SO10. And then you have a magnetic monopole which has a core in which the grand unified X and Y bosons are excited, a core in which you see the electroweak W and Z, quarks, and so on, and only at the very, very largest distance you see only the magnetic field. No more singularity because spontaneous symmetry breaking resolves the singularity within this course. Only problem is such magnetic monopoles are extremely heavy, 10 to the 16 giga-electron volt, and they could have been produced only in the Big Bang, and they've never been observed despite 40 years of search. However, there is another way to hide the singularities, and this was pointed out originally by Polyakov, is to formulate the theory on a lattice. If you formulate the theory on a lattice, you can put the monopole and the Dirac strings in between the lattice points. So in the physical lattice, you don't see anything anymore. The singularities are hidden away among the lattice. This has led us, Cristina Diamantini, Valery Vinokur, who are in the audience, and myself, to propose that much lighter monopoles could be realized in quantum materials, and especially quantum materials which are granular in structure. A granular quantum material is essentially a lattice. And again, the monopoles can be hidden among the granules, and we see the effect, and we can see the effect of these monopoles on the granules. This is the new proposals that we made 4 years ago, and let's focus on this one. So, quantum matter. Quantum matter, charged quantum matter is what I will consider always. Is generically described by an action which has a matter part, the coupling of the current to the electromagnetism, and the usual Maxwell term. So formally, at finite temperature, the integrals here have to be defined. The time integral has to be defined on Euclidean time, compactified on a circle of radius 1 over the temperature. But to be simple, for simplicity, today I will just consider 0 temperature. So I have just an integral over Euclidean 4 space. You can now formally integrate out the matter degrees of freedom to obtain what is called an effective action for the gauge field alone. This is the same term here. And then you have quantum corrections that come from the integration of the matter fields. If the matter fields are quadratic, then of course this is trivial to do by Gaussian integration. If they are not quadratic, then you have to do the usual loop expansion in perturbation theory. The behavior of the system is then described by the induced current, which is called the electromagnetic response, which is the functional derivative of the effective action with respect to the gauge field. Here an example of this formalism, superconductors. For superconductors, the effective action here is just a mass term for the photon, A mu, A mu. By functionally deriving with respect to the A, one gets the induced current, which is linearly proportional to the gauge field. And by taking time derivatives and the rot, you get the usual, the familiar London equations. So this was just an example. So now let's focus on insulators. What is the effective actions for insulators? The effective action, zero temperature for insulator, is just the same Maxwell term we are used to, just with a different coupling, a renormalized charge affecting coupling, and with a velocity of light which is now determined by the dielectric constant and the magnetic permeability of the system. Suppose now that we have a granular structure, an emergent structure. Then the system looks like this. You have islands which are separated by a typical ultraviolet cutoff L. Then, of course, this action has to be formulated in a discrete way. So we sum over the island places with multiplying the Maxwell term by the cutoff to the force. And of course, there are two ways to do that. Once you have emergent granularity, you can discretize the action, the effective action naively, or you can take, and this corresponds to having a non-compact gauge group R, or you can take the compact gauge group U1, which means that the actual electromagnetic fields E and B are periodic under shifts of 2 pi. You see that by developing the cosine here, the first order term is the same, but the two actions are very different globally. Indeed, you can formulate the compact action in Villain form instead of cosine. This you're probably very familiar. You introduce dynamical integer fields on the plaquettes of your lattice, this m mu nu, and then you sum over f mu nu over a mu and m mu nu, and you see that by this combination, the periodicity of this combination is guaranteed by these integers. So this is the Villain form of the compact action. Now comes the important point. These guys here satisfy the usual Bianchi identity or homogeneous Maxwell equation. This means the divergence of B is equal to 0 essentially. But this integer that appear here because of the compact nature of the gauge group there is absolutely no requirement that they satisfy that the divergence has to be 0. And this means that the overall magnetic field formed from this combination can have monopoles of strength 2 pi over E square effective. So you see that when you have emergent granularity, magnetic monopole in the effective action appear naturally in quantum matter. Actually, one should eventually ask why not. Fine. So let's now focus on some concrete example of granular materials, quantum materials. Here is the first one, just to introduce the subject, which you are surely familiar with, is Josephson junction chains or granular quantum wires. So here is the wire. This is space. These are the granules of superconducting islands. Each is characterized by a particular phase of the order parameter there. On the vertical direction here, I depict Euclidean time. So this is pictures of the wire taken at different instant of time. And now what can happen is tunneling events, which go under the name of quantum phase slips. And these are events in which one particular phase from one moment of time to the other makes a 2 pi flips. This is a tunneling event. In field theory, it's called an instanton. And the effect of these instantons is well known. It's to induce the resistance in the superconducting metal, in the one-dimensional superconductor, which becomes essentially a metal. They induce an ohmic relation between charge and potential. Okay, so this is a first example of a granular material. We will not be interested mainly in one dimension, but rather in two dimensions. So let's consider the natural generalization of this. This is Josephson junction arrays or granular superconducting films. Here we have the same physics. Now on the plane, the arrangement of the droplets of superconductor is now two-dimensional. Each is still characterized by a phase of the order parameter, but we have now the possibility of new configurations. Suppose you have 4 addition droplets here in which the phases are arranged like that. Then the phase here makes a circulation of 2 pi, which means in the middle of this arrangement of superconducting droplets, you have a vortex. But this is not an Abel-Koser vortex. This is a Josephson-type vortex. You see, it has only gauge structure if you want. There is no normal state. Okay? There is no normal state because it forms in a granular material and not in a homogeneous material. And because of this, dissipation becomes a subdominant effect. This can be verified experimentally. There is a very, very high degree of duality between charges residing on the islands and this type of Josephson vortices residing in the middle of the islands. And one thing that is almost always forgotten in the literature on this subject is that once you have this type of vortices, you have mutual statistics with the charges. If a vortex goes around the charge on an island, it acquires an Aharonov Kasher phase. If a charge goes around the vortex, it acquires an Aharonov Bohm phase. And this cannot be neglected. They have a huge effect. Okay? This is why what I'm talking about now has been always almost missed in the literature. So it is actually the competition between the charges on these islands and the vortices in the middle which drives the famed superconductor to insulator transition. 3 phases have been observed. The superconductor is when global phase coherence is established. All the phases point in the same direction. There are no vortices. There are 2 other phases in the system, the Bose metal, when the bulk is completely frozen by this mutual statistics interaction, and there is conduction only by edge modes. And then there is the superinsulator, which will be the focus of the next slides, in which you have a proliferation of vortices. Both these 2 new phases of matter have been first proposed and predicted by myself, Cristina Diamantini, and Pasquale Sodano back in '96. So we had a one-dimensional chain. We had instantons, phase slips. Are there things like this in 2 dimensions? Yes, there are. Suppose you have here the granular material or the Josephson junction array, and suppose you have a vortex circulating as I just pictured in the slide before. So a vortex 2 pi sitting here in this plaquette. Now, here again, I have in the vertical direction the Euclidean time, and we have now a possible configuration in which this vortex here does not exist anymore on this horizontal plaquette in the next time because all the magnetic flux flows out in the vertical plaquettes. Okay? So the vortex sits here for infinite time. It's just static. Infinite time means static here. And at a certain instant of time, it just flows out horizontally and there is no more vortex. So this is a tunneling event between 2 topological sectors, 1 vortex, 0 vortex. And the flux goes out in Euclidean on the vertical Euclidean plaquettes. So if you now look exactly what this event is, this static vortex that goes down to infinity because it's static is nothing else than a Dirac string. And the event which is in the middle here is a magnetic monopole. It is actually a non-relativistic magnetic monopole because the flow is only on the plane. There is no flow up and here, but it's still a magnetic monopole. So the instantons in 2 dimensions, if you want the analog of phase slips in 2 dimensions, are magnetic monopoles. What about 3 dimensions? In 3 dimensions, this Josephson vortice is living between the droplet of the granular material, become 1-dimensional extended object. And of course, there is now nothing preventing these 1-dimensional vortices, Josephson vortices, to be open at their endpoints. And the 2 endpoints are simply monopole, anti-monopole pairs. And now 2 possible configurations exist. If the vortex, these Josephson vortices have tension, then the typical configurations are small dipoles. So no magnetic monopoles, monopoles are suppressed, you just have dipoles in the system. However, if these Josephson type vortices become tensionless, then there is no energy price to pay if you pinch this vortex here, you bring it to infinity, and you bring it back to the anti-monopole. So these lines become Dirac strings, and you have a Coulomb gas of magnetic monopoles. These magnetic monopoles can then Bose condense, and by boson condensing, they induce a completely new state of matter, which I will focus on in the next slides. What happens in a condensate of magnetic monopoles? So suppose now that you have, okay, so I will give here a heuristic argument to show you what happens. This can be backed up by very rigorous computations. I don't want to present here rigorous computations because they're quite involved, but I want to give you the feeling of what happens. So suppose, for the sake of simplicity, that you have here monopole currents that come either out of the plane or in the plane. So out of the plane, let's say O, and in the plane X. And now put some anti-charge probe in the plane. So the electric field lines between them will be typically in this region. Now you have an electric field like this, and you have a monopole current perpendicular to the plane. You have a dual Lorentz force. The dual Lorentz force will push down these currents and will push up these currents. That means the dual Lorentz force will polarize the magnetic monopole gas. So that all the out-of-plane currents are above the line joining the anti-charge probe, and all the currents in the plane, into the plane, are below. Now comes the dual Ampere law. The dual Ampere's law tells you that these magnetic monopole currents are surrounded by electric fields. Exactly like a usual current is surrounded by a magnetic field, here a monopole current is surrounded by electric fields. Any place in the plane, this magnetic field will cancel out from all the monopoles. However, if you take this line between charge and anti-charge, here instead they all sum up. So what this gas of monopoles is making is to creating an electric string, an electric flux tube between charges and holes. This electric field, this electric flux tube between electric poles in a magnetic condensate is the exact dual of what you're very familiar with, the Abrikosov flux tube between magnetic poles in a charge condensate. So this state here is which is called superinsulator, is an exact dual of a superconductor. The only difference is that electric field lines can end on poles, contrary to magnetic field lines. So the endpoints here, the electric can reside in the interior of the sample. So we have configuration with charges, anti-charges, or charges holes, which are joined by an electric flux tube. And these are nothing else than the electric equivalent of strong interaction pions. This is the phenomenon of confinement. Indeed, in this phase of matter, Cooper pairs play the same role as quarks do in hadron physics. They are joined by a flux tube and electric string, which amounts to a linear potential with string tension sigma. So no U1 charge is observable for scales larger than the scale of the pion, which is 1 over the square root of sigma. And it means that in large enough samples, this phase will show an infinite resistance, strictly infinite resistance, even at finite temperature. And this is what distinguishes from a normal insulator. There is a phase transition. At finite temperature, we still have an infinite resistance. This is why it's called superinsulator, and it's a dual superconductor. Duality goes farther than this. Actually, like in a superconductor, we have two critical magnetic fields for penetration. We have a Meissner and mixed state. We have the same thing here. We have two critical voltages, VC1, VC2. If you apply voltages smaller than VC1, only neutral pions can be excited. No current passes. This is the electrical Meissner state. If you apply a voltage between the two critical voltages, the string is stretched and reaches the sample boundaries. Here, current starts to pass. You have electric flux penetration. This is the mixed state of the superinsulator. Finally, if you apply large enough voltages, the whole state of matter is destroyed. Superinsulators have been observed by many groups in several materials. I show here the typical granular structure in a titanium nitrate film. So this is the structure of the superconducting gap. So you clearly see various granules, red where you have high gap, blue where you have zero gap. In the same sample, correspondingly, hyperactivated resistance has been measured. So here you see the sheet resistance as a function, sheet resistance in logarithmic scale as a function of 1 over the temperature, so that the straight line corresponds to the usual activated behavior, Arrhenius activated behavior. You see here a clear deviation. This is called hyperactivation, and it can be shown that this scaling, that these curves here scale to a Brzezinski-Kosterlitz-Thoulez phase transition, which diverges at the finite temperature. And this means below this temperature, the resistance becomes strictly infinite. In the IV curves, so current as a function of voltage, we see two kinks, which corresponds to the Meissner state and the mixed state. So here you see, for example, the red curve, the first king, the second king, or here in the red curve, very clear, this is VC1, VC2. So this is perfect confirmation of the existence of a Meissner and a mixed state. Finally, another very interesting phenomenon, the monopole gas not only creates a linear interaction between charges and holes, it also screens the Coulomb interactions on very, very short scales. So we can have this situation here, which is the linear potential, the string between charges and hole is stout. This is the one that gives you the hyperactivated behavior I just showed. But we can have a situation in which the string is loose, so the charge and anti-charge are very near, sufficiently near that the linear interaction is not felt, but neither is the Coulomb interaction because it's screened on even smaller distances. So on these distances here, charges and anti-charges, charges and holes in condensed matter language are essentially free. This is the phenomenon which is called in field theory asymptotic freedom. It means that, and it's realized also in strong interaction ions, the quarks inside the pion are free. And here the Cooper pairs inside these electric pions are free. In an experiment now, okay, so sorry. Strong interaction pions are very small because the interaction is very strong, and there is no possibility of looking inside. But the electric interaction is more weak, so one could imagine that the size of these pions is large enough so that one could measure the inside by taking small samples. And indeed, this is the case. Here you see that if you take large samples, you see again the hyperactivated behavior much stronger than the usual activated behavior. But if you take a smaller sample, if you go down to 0.2 millimeters, you have a metallic saturation, and this means you are inside the scale, the string scale, and you see asymptotic freedom. You see just free charges. The interaction potential between charges and holes can also be measured directly by dynamical relaxation. You will hear a lot about this if you go to Alexei Mironov talk. So I don't want to spoil all the details of the experiment, but here the theory part. So what you do, you measure the delay for current passage as a function of an applied voltage. Actually, I scale it with the difference of applied voltage minus the threshold. Again, you see here, take the red sample, for example, you see clear here two different scalings, and this corresponds again to the Meissner and mixed state. The jump corresponding to a scaling exponent minus 1/2. It's for all samples, you see it's minus 1/2. Corresponds to jumps to voltages which jump from the Meissner to the mixed state. The jumps from the Meissner state to the normal state corresponds to minus 3/4. Now, suppose you have this linear potential which corresponds to an attractive force, a constant attractive force, charge times the string tension, which is the threshold divided by the sample length. And now you apply a repulsive interaction with a constant voltage V, and so the force is V divided by the sample length. So the acceleration in the center of mass is the reduced mass times the total force, which is this minus this, V minus V is critical, the threshold. And high school physics tells you that the separation is then a squared power of the time. And by reversing this, you get immediately the minus 1/2 critical exponent. So this measure here is a direct measure of a linear potential between charges and holes in the superinsulating states. Granularity is not confined to 2 dimensions. The same physics has been detected recently in 3-dimensional superconductors, and most importantly, the underdope regime of high TC cuprates is granular. In 3 dimensions, then we have the additional possibility of an even more exotic phenomenon. By a topological effect, there exist excitations called dyons, which carry both magnetic and electric charge. And so we have proposed, here is the new proposal, that, again, the pseudogap state, this is the typical phase structure of high TC material cuprates, that the pseudogap state here is actually a condensate of dyons, and that the superconducting dome here is a mixture of a usual charge condensate and the dion condensates, coexisting mixture. Now, if you take this seriously, you can go through the physics, and it turns out that the existence of magnetic monopoles of magnetic charge solves essentially the entire mysteries of the pseudogap state. I'll give you some examples without going into details. So magnetic charge in the pseudogap state turns, this important point is magnetic monopoles induce statistical transmutation of Cooper pairs. If you bring a Cooper pair near magnetic monopoles, it becomes a fermion. In a pseudo-gap state, the charges, it turns out, are symmetry-protected boundary fermionic Cooper pairs. These live on a percolation network of edge states, and since they're fermions and symmetry-protected, they immediately constitute a perfect Fermi liquid, and you have immediately explained the T-square resistance measured in the pseudogap state. Of course, magnetic charge immediately leads to the observed magnetic-electric pair effect. Magnetic charge very simply explains nematicity of what we heard this morning. Suppose you have the insulating state of a sub-high TC cuprate. It is on the square, on one plane, it is a perfect square antiferromagnet. Of course, then you would expect this famous C4 symmetry, but imagine now that the charge carriers carry not only charge, but magnetic charge. Because it's an antiferromagnet, you have equal spins only on the diagonal, so C4 is immediately broken down to C2. So nematicity is very easily explained. It turns out that magnetic charge can easily explain also the T resistance when an applied magnetic field is applied. Maybe this is a little bit more complicated. If somebody is interested, I can explain it just later of the seminar. And magnetic charge immediately also explains why Cooper pairs cannot be split in the pseudogap, and so the observation of Cooper pairs in the pseudogap state. I want to conclude with one particularly important slide about the role of disorder. It turns out that the only role of disorder in the superconducting insulating transition is to tune the strength of the Coulomb interactions. All the phases which are observed, the nature of the phases which are observed around the superconductor to insulator transition do not depend on disorder. So disorder is irrelevant in the renormalization group since it does not influence the nature of the quantum phases. And one thing which is crucial is that all the phenomena which are usually associated with strong disorder, many body localization, etc., like breaking of thermalization, breaking of ergodicity, simply follow from linear confinement. There is no need of disorder. Confinement explains all these phenomena. So let me conclude. This is the takeaway for today. Magnetic monopoles appear very naturally in granular superconductors. A Bose condensate or a plasma in 2 dimensions of magnetic monopoles lead to a new state of matter. Superinsulators, which has been detected in titanium nitrate, niobium titanium nitrate, indium oxide, and niobium silicon films. Disorder is not relevant for the nature of the phases around this superconductor to insulator transition. Finally, a condensate of dions, particles, excitations carrying both magnetic and electric charge, could explain the entire physics of the pseudogap state. For references, details, anybody who's interested, I refer to the recent book I wrote for World Scientific about all this stuff. I will conclude here. Thank you very much.
Okay. Thank you, Carl, for the very nice presentation. I went in and out, but I think I have captured some essence of it. Any question? Yes, Vladimir, please.
Carlo, thank you very much for your nice presentation. And in what concerns theory, it speaks for itself. My question is about a couple of slides, your first slides, which concern experiments which confirmed this phenomenon. I think it was in...
this was the first experimental slide.
Yes, yeah. Could you kindly provide a little bit more details? There are no references to these experiments. And second, as far as I understand from the spirit of your theory, there should be really absolute insulator, but in this experiment there is some inclination at this point of the characteristics in both.
You mean here?
In both. For example, here, what are the physical reasons of this deviation from absolutely vertical jump? There are probably still some elements in this place. Thank you.
So first of all, to answer, this is a picture
Recording in
taken,
progress.
From the experiment of Tatiana Baturina Valeri and Christoph Strunk and collaborators. As a reference, I'm sorry that I didn't give enough references. So, as I said, this is logarithmic scales. So this line here would correspond to a perfectly activated insulating behavior. Now, here you have deviations. Now you can fit these deviation curves. And it turns out, it's not marked here, it turns out they are perfectly fit by the Berezinski-Kosterlitz-Taules formula. If they are fit to the Berezinski-Kosterlitz-Taules formula, it means that there is a finite temperature here at which this curve is strictly infinite. This means that they do go to infinity at a finite temperature. Below this temperature, you have infinite resistance. And the important point is that it's a finite temperature. It's not zero like in a normal insulator. They diverge at a finite temperature. Mm-hmm. And this is the scaling here, BKT scaling, is quite impressive.
Okay, but this, what we see, it's apart from Berezinski-Kosterlitz-Taules.
These curves here are BKT. These are BKT curves.
Yeah.
So they diverge at a finite temperature.
Okay, so it's a combination of two effects, in fact.
Well, it's part, so if you take this plasma of monopoles and you raise the temperature, what happens? And there is a phase transition, which is BKT. So the monopoles get confined, so no more monopoles in a usual phase transition. So you make a transition from a superinsulating state below this transition to a normal insulator above. And these are these curves here.
And this was observed in the experiment?
This was observed in the experiment.
Thank you.
Okay, yes, please.
Just to make sure that I understand. So is your model for the granular superconducting film quantum XY model? 2 plus 1 XY model, is that your model or something else?
Absolutely not. It is a 2 plus 1 gauge theory.
Sorry, 2 plus 1?
Gauge theory, topological gauge theory.
So 2 plus 1 XY model is dual to the Higgs scale electrodynamics.
It's not a Higgs model, it's a topological gauge theory, which is very different.
Do you have any slide I don't actually know what the model is.
No, I don't have slides, but you can go to the talk of Cristina Diamantini tomorrow and you will hear all the details about that. Okay? So the statement is exactly the XY model alone is not sufficient to describe all the phenomena around the seat. You need gauge fields.
I mean, my comment is that there are gauge fields in the dual theory of XY model, but that is still not your model, right? Okay.
No.
I think we're just coming to the, well, Chris, maybe later on, yes?
Yeah, so it looked like a really fascinating scenario. I have a completely different view on pseudo-Gaussian cuprates, but I still find it very interesting. My question is slightly related to the previous one. So to get some microscopic modeling for this, would it be sufficient to start from 2D Hubbard, or what would we need? 3-band or even more?
Okay. I didn't have time to go into that. We have a microscopic model, which is very different from the ones you are addressing. The microscopic model we have for pairing leads to a localized pairing and is due to effective magnetic field given by deformations in the materials. So curvature, for example, in material is equivalent to magnetic fields for itinerant electrons, and the spin defects, hedgehogs, and the monopoles at the end are also seen as magnetic gauge fields by itinerant electrons. And so these effective pseudomonopoles are able to bind electrons. And this is our microscopic materials. So in these high TC cuprates, it would be rather the spin hedgehogs that would bind electrons. In graphite, it would be rather curvature defects.
I think we can have just a very short question. I saw a raising hand, but okay. At the back, yes.
Okay, I want to ask you a question about the universality of your results from the quantitative point of view, because all effects are sitting on the small distances on the granularity and so on. And does it mean that to the answer should enter not only the size of the granule, but for example its capacitance or something else which is related to the precise form of the physics at the small scales? Because in your action you put only the distance, the size of the granular, yeah, but if you put it to the zero, you obtain the zero result. So does it mean that you should, what about the universality of the results you presented?
So you should not put to zero this size. It's not a randomization group, it's a physical size. The actual system decouples into droplets it's emergent, by its own will. And so the scale L is a physical scale which is chosen by the system. It can be different in different materials, so there is no universality.
Okay.
Okay, I think we're running out of time, and let's thank the speaker.
I'll leave it here.
Thank you, Carlo. Very
Get
nice
a diploma.
presentation. Yeah. This is less than a diploma, but I think you can keep that as memory.
Thank you so much.
Okay, very nice.
Thank you.
Okay. Now we're moving to a new session by Professor Toussaint Park. Is it correct? Okay, we have a break for 5 minutes. Yes. Geldi mi? Ha, bağlantı kurdu. Tamam.
So we will have a free talks, free presentations. And the first presentation, the keynote presenter is Tuson Park, Professor Tuson Park from Sungkyukwon University, which is just SKKU University from South Korea. Professor Tuson Park is famous for his work with 115 compounds, but not only. He also rediscovered or discovered superconductivity in yttrium under high pressure. Am I correct? I think that's correct. This is a very recent story. We met with Professor Park 15 years ago. Now Tuson Park is professor at that university, exactly. So the title of the talk is Pseudogap and Kondo hybridization in the heavy fermion superconductor cerium cobalt indium 5. And I think, okay, we can start. Tuson, time is yours.
Is it good? Okay. Thank you, Chairman, for the very nice, lengthy introduction. Today, I will discuss pseudogap and Kondo hybridization, and then the possible interplay between them in the prototypical heavy fermion compound, so-called cerium cobalt indium 5. So most of the work that I present has been performed by my student Harim and Hong. So Harim is going to graduate soon, so you need very motivated and bright young postdoctor, then I highly recommend him. He is very wonderful. And then I also acknowledge my fruitful collaboration with Professor Shin Lu from Zhejiang University. Okay, so I think you already heard about enough on pseudogap from the previous plenary talk, so I will not discuss it much. I'll just briefly comment on it. So as you heard that the pseudogap, which encompasses the superconducting state, is an enigmatic quantum phase, which has been considered as crucial to understanding unconventional superconductivity in high-tensor cuprate. Observation of the pseudogap in iron-based pnictide, which is another family of unconventional superconductors, has raised very important questions, such as, is pseudogap an ubiquitous phase in unconventional superconductors? Or does it arise owing to the preformed Cooper pairs or other competing interactions? In order to address these outstanding questions, we have studied the prototypical heavy fermion compound, namely 115 compound. This compound has been reported to have a pseudogap-like phase, and also the energy scale relevant to this system is a milli-electron volt, meaning that it's highly controllable via many control parameters. So, for example, in a heavy fermion compound, cerium cobalt indium 5, Vladimir Sidorov and Los Alamos group reported electrical resistivity as a function of temperature. Here, y-axis is rho minus rho 0 divided by temperature power n. And then what he pointed out, noticed is that at right above the spring transition temperature, there is a deviation from the high temperature scaling, and then he noted possibility as a pseudogap. And then at pressures much higher, then what he notified is that this pseudogap-like phase transitioned to so-called fermion liquid behavior, and he proposed phase diagram like this one. So dome of superconductivity centered around 1.5 GPa, and then pseudogap-like suppression, then of lambda formal liquid behavior. In STS measurement, also there was evidence. For example, this the differential conductance, this is bias energy, bias voltage. Then at base temperature around 245 millikelvin, then there is sharp suppression dip due to splitting energy, and there is additional feature at a wider energy range. And when you increase the temperature to 1.7 Kelvin and then 5.3 Kelvin, even 7.2 Kelvin, which is higher than TC of 2.3 Kelvin, you can still see, even though the superconducting feature is disappeared, there is still a gap-like feature survives. So they attribute it as a pseudogap. And then when applied magnetic field, what they found was that this superconducting gap feature completely suppressed. However, the pseudo-like feature still survives. And recently, Shrestha et al. In Laura Green's group, they reported planar tunneling spectroscopy. This is the conductance as a function of sample bias voltage. At very low temperature, you can see like a V-shape, like suppression due to superconducting gap in the conductance. And with the increasing temperature, then this gap feature is becomes smaller and smaller. What's remarkable is that this 2.3 Kelvin is where TC is, but at 2.5 Kelvin and 4 Kelvin, you can still see the gap-like feature. And then ascribed to the pseudogap that has been reported in the STS measurement. So when they plotted it, the gap size as a function of temperature, then what they found was that 0.8 millielectron volt gap size is suppressed with increasing temperature as expected. However, as mentioned, at around TC, it does not go to 0 as expected, but rather they have finite value, okay? And then gradually suppressed and extrapolated to 0 at around 5 Kelvin, which they like assign it as a pseudogap temperature. And then they use this gradual crossover as an evidence for preformed Cooper pairs as an origin of a pseudogap. However, if you studied fermion compound, then you know that there are a lot of competing phases around. For example, this is the cadmium, the negative, which is hole doped, and tin doping, which is positive. The electron dropped to the sodium cobalt indium 5. Then you can see that this the coherence temperature is gradually increased, but the superconductivity shows a dome shape centering around the pure compound, and the antiferromagnetism is in nearby with a very slight amount of cadmium doping, indicating that it's difficult to make a definitive conclusion based on this, or ruling out the other possibility of competing order as an origin of pseudogap. So then Story, he pointed out that in order to distinguish between different scenarios, that you just, it's not enough to just focus on one system configuration, but rather you have to follow the whole phase, like for example, not just the one doping concentration, but rather like use control parameter and see the whole phase diagram. So for example, if the T star is precursor pairing, then you can see that T star ends at the point where TC go to 0. On the other hand, if you T star is the competing order, then you can see that the end point finish within the superconducting state. If it is well, the system is more complicated. Like you have both competing order and the precursor pairing, then it's supposed to be more complicated, but yet it should finish at when the TC go to 0. So in order to probe the evolution of the pseudogap phase and the squinting phase, then we used so-called point contact spectroscopy, which can directly probe squinting gap and pseudogap, and then under pressure. So this technique takes advantage of so-called underactive reflection spectroscopy, where one electron comes in and then it reflected on the surface of superconducting superconductor, and then making the Cooper pairs in superconductor, meaning that the differential conductance is doubled within this superconducting gap. In an ideal case where there is no contact barrier on the interface. However, if there is an interface on the interface contact barrier, then you can see that now it partially pick up the tunneling. So that's why you have like U-shaped suppletion and then the two-peak like feature in the differential conductance of point contact spectroscopy. So experimentally, we used two types of pressure cell to do point contact measurement under pressure. The first is a piston type cylinder cell, which we used below 2.5 GPa. And then we also used so-called diamond amber cell, which you can measure ideally up to megabar range. Okay, so this is differential conductance as a function of a bias voltage of silicon cobalt indium 5 at ambient pressure in the superconducting state. What you see is that there is a broad background from the final resonance and then enhancement at zero bias due to underactive reflection. So if you, in order to amplify this underactive reflection feature, we divide this conductance by using the funnel. Then what you see is that you have nice two-peak structure that you expect from the superconducting underactive reflection. And then here, the red line is fitting by using BTK, modified BTK model with a gap size about 0.587 millielectron volt. So, I mean, I think we think that the PCS that we observe is intrinsic property and has some meaning. And then we started to do some more quantitative analysis on at other temperatures. So this is the prototypical resistivity behavior as a function of temperature. So basically, you have two rhythms. One, so-called high temperature incoherent rhythm, where and showing the logarithmic divergence, and the low temperature so-called coherent rhythm, which shows suppression because of the Kondo singlet forms a lattice. So this is differential conductance as a function of the bias voltage at high temperature. So the purple line is at 300 Kelvin, which is pretty much flat, well, as expected, because it follows the ohmic behavior. And then with decreasing temperature, then you can see that this, the conductance curve shows a symmetry between a negative bias voltage and positive bias voltage. And we note that the coherence temperature, which shows a peak is around 45 Kelvin, and then the temperature where you start to see the symmetry is higher than 45 Kelvin. So this is temperature dependence. And then in order to quantitatively analyze this differential conductance, we use so-called final resonance model in the Kondo lattice system. And then this conductance curve consists of two parts. The first term is so-called background conductance, the second term is interference term that gives rise to this symmetry. And then the funnel parameter is complex number with Q1, the so-called funnel parameter. And the second term, the complex number is directed tunneling into the CF coupled state. And epsilon sub 0 is so-called resonance energy. So in order to fit these data set, we fixed the background conductance and funnel parameter and the resonance energy, and then even though we fixed them, it explains the data pretty well. So this is the data set at 1.0 GPa, and then well, the overall feature is pretty similar to ambient pressure. As you can see, symmetry becomes stronger with decreasing temperature, and then you can see at base temperature on top of the background, then you have under reflection. So this is the data from 0 to 1, 1.52, 1.8, and 2.34 GPa. So and then those solid lines are the fittings. And these very nice agreements suggested that those funnel resonance model in the control lattice system explains the temperature dependence as well as the pressure dependence pretty well. And the other thing is that in all pressure range that we studied, the funnel resonance or symmetry exists even at temperatures far above transport coherence temperature. And then also at the 1.5 Kelvin that we reached, the zero bias, and then at a little bit higher than the TC, you may see some of the dip appears, which we will discuss later. How many minutes? 10 minutes. Okay, I think I'm going too slow. Okay, so some of the feeding parameters that we use. This is contact resistance as a function of pressure. Initially it drops, and then pretty much is consistent. And then this condor resonance energy and the funnel parameter, they are kind of, well, almost flat, gradually increase with increasing pressure as expected, because when you apply pressure, then you increase hybridization. And then the background conductance and inverse of these contact resistance, they are pretty much consistent. Okay, so in order to quantify the funnel symmetry, we used so-called 10 millivolt criterion. So what we did is compare between minus 10 millivolt value and plus 10 millivolt, and then took the ratio. And then, as you can see, and then the x-axis is the normalized temperature by T, so-called T saturation temperature. T saturation temperature is where you do not see this asymmetry. So you can see that at different pressures, that at high temperature region, then they scaled pretty well together. And with decreasing temperature, then you can see that the deviation temperature from this ambient pressure data, you can see that they increases. And then here the dotted line is the based on so-called two-fold model, where it consists of two terms. One is the increase of effective mass, and the other one is so-called autoparameter of the fraction of condor liquid. And you can see that it nicely captures the evolution of the asymmetry as a function of temperature. So in order to make sure that this is not just our arbitrariness of selecting the criterion, what we did was that we used 60 millivolt and 2 millivolt. And all of them, even though they differ quite a lot, then they show scaling behavior and then deviation at low temperature. So I think this is pretty consistent result. Okay, so and the inset shows the saturation temperature, the red dot. So at ambient pressure 150 Kelvin to 180 Kelvin at high temperature. So note that this temperature is much higher than the so-called coherence temperature. And then this type of, has been already reported in Alpes measurement, where they obtained the itinerant for weight. They started not at coherence temperature, but at a much higher temperature. So, which in some sense consistent with our result that the asymmetry comes from the itinerancy of reflection. Okay, so this is now go back to the conductance at low temperature. As you can see that this is 1.5 Kelvin. This feature is the undefinite deflection. 3 Kelvin, I think I want to point out this part where you see this is normal state. You see a slight dip at 0 bias. Okay, thank you. And then this is just amplification of the data at 3 Kelvin. And then after normalizing the funnel, then what you see is that you can see clear a dip develop at 0 bias. And then you can see that the data is actually well above the experimental error bar. So with the increasing temperature, you can see that the dips is suppressed, right? And then at temperatures higher than around 8 Kelvin, it's kind of difficult to observe this feature. And then this is the data near the TC. So these are the dip, right? And the TC is around 2.25 Kelvin. Then slight suppression, 2.25 to 2.24 Kelvin, 2.36 Kelvin. Then you see enhancement near 0 bias, right? So enhancement at 0 bias is due to NDF deflection, due to sphericity gap, right? That's what you see. The dip switches to NDF deflection. At higher pressure, you can see similar feature, and then you can see that this feature is pretty similar to what you observe in high-tissue cuprate. In high-tissue cuprate, that this is STS, like measuring tunneling. So you do not see NDF reflection enhancement, but rather you see enhanced suppression and also the coherence peak. Okay, so this is the temperature evolution of pseudo gap. Like at ambient pressure, then you can see this is the color contour plot, T as a function of bias voltage. Then you can see that instead of gap is a suppressed increasing temperature, but rather is pretty much insensitive. And then with the increasing pressure, you can see that the size of the gap is enhanced, the pseudo gap is enhanced, and then the TG also enhanced. And you can see the similar trend, the size of the gap increases, but it's more or less filling with the increasing temperature, and the pseudo gap temperature is increased with the pressure. And this is comparison between the temperature evolution and magnetic field evolution. Magnetic field evolution, what you see, unlike temperature, which does not change its gap size, rather on the magnetic field, the gap size is suppressed as well as the dip is suppressed. So at 1 point GPa, we can see the similar suppression of the gap size of the magnetic field, and then you can see a similar trend. So, okay, so since I don't think I have much time, I'm just going to summarize it. Here, we have established a so-called quadriparticle scattering spectroscopy, cobalt-105 under extreme conditions, and then which the high temperature asymmetry is well explained by the final resonance. And then here, we can see that this dome of spinactivity shows a dome shape around center around 1.5 GPa, and the pseudo gap is increases, indicating that pseudo-gap that we observe is not pertinent to preformed Cooper pairs, but rather, as you can see, these are we are working on this topic, which means that is it universal to have fermion compound or not? So with that, I'd like to thank you for your attention.
Thank you, Toussaint. We have time for 2 questions, I believe. Professor Green.
I'm sorry I didn't make it through your entire talk, but I'm so nervous about mine, I had to run back and forth. So yeah, we have a lot of those, we were the ones that did the phaneresonance to begin with, and we did all that stuff. But I also wanted to point out, are you aware of our work that shows that the increasing magnetic field shows that we have a field-induced gap, and that it can be accounted for by Kondo scattering, which is causing the pairing in a composite pairing model? So,
yeah.
okay.
So in our case, we mainly focused on the high temperature normal state regime. So unfortunately, I think we did not. So this is
increase in magnetic field. So
right. This is the 3 Kelvin, right? At 3 Kelvin, then. So our field is pretty small, I think, compared with US, where you go to superconducting state and apply magnetic field, and then I think you see some feature.
We also do that in what you would call the pseudo-gap state, which was shown by STM by 2 other groups.
Right.
In our groups, they're just preformed pairs.
Right, so that was actually introduction, that including
Okay.
your work too.
Okay. Yeah, I missed the beginning.
Yeah.
So could you have any, did you look at the pressure-induced, you looked also just above TC at 3 degrees, right?
Yeah.
Okay, very good, thanks.
Yeah.
Okay, there is another question.
Toussaint, when we did that back in, I think, 2009 or so, we got the opening of the pseudogap at about 3.3 Kelvin, in line with the measurements at Los Alamos.
Mm-hmm.
Now, you reported also LoRa's data, and these data were a little bit higher. So
yeah, 5 Kelvin.
Yeah. Do you have an idea on what this temperature depends on? Is that a surface condition, or any idea what, or does it depend on the measurement you actually do?
I think this, depending on even a tunneling measurement or STS measurement, I think it varies. For example, in the Ali Azdani's paper, even at around 8 Kelvin, they still see pseudogap feature, right? So my guess is, well, I do not have any good argument, but as you pointed out, it may depend on what surface you are looking at, and also conditions of your contact in my case. So those may play a role. That's my guess. So, and also, if you look at this part, see, it's kind of very blurry, right? And then, which point you put a T sub z, so at this moment, I don't think I can give you a very good answer.
Okay, the last question belongs to me.
Okay.
Can you go to the last slide?
Okay.
So I like the statement, which is the next one. Yeah. So a new type of pseudogap that is universal to heavy fermion compounds. So I guess you work also with the other system. Can you tell a few words?
Right, so I think the question is, Kondo hybridization, you have the denomination gap to heavy fermion compound, right? That's pretty much, what we know already. So if it's relevant to Kondo hybridization, right, then why not in other systems? Why just is unique to silicon cobalt indium file, right? So I think that we think that we might see something new. So what we did was that we did some sister compound, and then I think what we see is that at a very high pressure where you already suppress conductivity, like this is 5 GPA, 13 GPA, you see some type of circuit-like feature that you already see. So at this, well, it's still under progress. What we say is that maybe we see now cobalt-115, rhodium-115. I think then maybe this is indeed new, like novel type of a pseudo gap that may be like ubiquitous to heavy fermion compound. That's my guess.
Okay. So finally, let me give you this certificate. This is to certify that Tucson Park has participated in our conference and presented a paper titled as keynote speaker presentation. Let's thank the speaker again.
Okay, thank you.
So next talk is an invited talk. The speaker is Professor Woo-Seok Choi. The talk is for 30 minutes, and I'll try to give you a reminder after 20 minutes. Is that okay? Yeah.
Yeah, sorry. Yeah. Thank you very much, Chairman, for the introduction, and also I thank the organizers for putting this wonderful workshop together. And I'm also from Sungkyunkwan University. As the previous speaker, although I'll be talking a little bit different. And I'm sorry I have to leave tomorrow, so I think my session is on Thursday or something like that, so I was shifted here. But hopefully I will entertain you a little bit with this new concept of chiral phonons. So you might have heard about this chiral phonons, which is rather a new concept. I myself didn't know about this 5 years ago. And I'm working on mostly about oxide superlattices, and today I will show you that in this strontium ruthenate-based superlattices, you can propose that this chiral phonon mediates this exotic exchange interaction, interlay exchange interaction. So this is the transmission electron microscope image of one of our samples. Basically, this is not a superlattice. So the bright layers are the strontium ruthenate layer, and these dark layers are strontium titanic layers. So basically, you control the thickness of the strontium ruthenate from 2, 4, 6, 8 unit cells, where the 1 unit cell of this layer is 0.4 nanometers. So you have very good control of this system using pulse laser epitaxy. So this work was primarily done by my former student, Seung-Kyo Jang, who is now a postdoc in our group for now. But he did most of the work. He went to Germany, he went to US to measure different aspects of his own samples. So he made all the superlative samples. And here are some of the publications. And today I will talk mostly about this Science Advance paper that came out earlier this year. So this is the guy who did the work. So this is the contents of my talk. So I will start introducing you about the concept of chiral phonon. What are they, and what aspect do they have? And I will talk a little bit about the system, because I'm basically a film grower. And then I will talk 3 different aspects of this. First, magnetization, apparently, and then the spiral spin state, atomical resolution of this spiral spin state, and then about this chiral phonon and Zeeman effect. Then I will summarize. So these are some basic ideas on, I should say, transverse waves, right? So you have just 2 different waves with 2 different polarizations, I should say. So you can have vertical polarization and horizontal polarization. And this is well established in photon, I should say. So you have a photon is considered as a transverse wave, although this is quantized transverse wave. You can have orthogonal polarizations, and they can be superposed. And if you have no phase difference, they are still linear polarization, but with some phase difference between these two waves, you can create this circular polarization, or introduce chirality to this system. And this is why you have a spin-1 system for your photons. They are spin-1 bosons. They don't have any longitudinal modes. That's why they don't have spin-0. But basically, this is how you can make the photons interact with the magnetic field or magnetic moment. It turns out that phonons are not very different. Of course, they have mass, so that they are different. But you can, in three-dimensional space, you have two different polarization. They are orthogonal. And if you have two different polarization, then you can actually introduce a phase difference between the two. And this transverse acoustic or transverse optical mode can become a superposition with a phase difference. Then you can actually visualize this rotation motion of this polarization, of this ionic motion actually. And this is actually called as chiral phonon. So basically, construction of this chiral phonon is not difficult. It's very easy actually. So if you have just transverse waves, then you can make chirality to it in 3D space. But the question now is, if you have something like that, will it interact with the magnetic field, or will it create a magnetic moment inside the solid? Okay, so that is the questions that we are having, and people have been looking into it. So this is one example. This is actually a theory work back in 2014. So what this paper says is angular momentum of phonons and the Einstein-de Haas effect. So basically, Einstein-de Haas effect is the connection between the angular momentum and the magnetic moment in macroscopic scale, right? So, and this microscopic object of phonon, if they have the chirality or angular momentum in this, in their term, this angular momentum can effectively create this magnetic behavior, magnetic-like behavior, right? So this is the basically, you just write the microscopic picture of your angular momentum of phonons. This is the displacement, and you have velocity vector, and you get the angular momentum, right? So, and they do show, at least theoretically, they can have some Einstein-de Haas effect. So again, emergence of this microscopic phonon chirality to the larger scale macroscopic angular momentum. More recently, Spalding proposed this orbital magnetic moments of phonons. So I hope this is also not very difficult. So if you assume a ionic motion, so this is for the ionic crystals. If the ionic motions have the circular motion, because they have charge, the circular motion will create this magnetic moment. Okay, so depending on the anion and cation, you have different magnetic moment. But basically, if you have a circularly polarized phonon, the circularly polarized phonons can carry orbital magnetic moments, and then this will interact with other magnetic moments or fields. Okay, so so people are more discussing about this new type of phonons, new polarization phonons, and try to link this with the magnetic behavior of the materials. So actually it turns out there are many different studies. So these are some of the studies that we could find in the references. There are lots of different phenomena and lots of different systems. And there are some of oxide systems and also in 2D materials. So what I feel is that there isn't any particular criteria of having this chiral phonon. So they are more universal in 3D or even in 2D lattices, and but you didn't look for it in the past. So now people are more interested in this. So in our group, in this talk actually, we are looking into strontium luthenate, strontium titanium superlattice, which I have shown you in the first slide of the electron microscope image, and I'll be talking about this static. So most of these were dynamic observation of this phonon. But this talk will focus on the static interlayer exchange interaction. All right, so what we are going to talk about is something like this, I think. So these arrows should be here, basically. So we have this system. So ferromagnetic metallic layer and non-magnetic insulating layer. So this non-magnetic insulating layer is sandwiched by this ferromagnetic layer. And we want to see any crosstalk between this ferromagnetic layer. So depending on this thickness of this non-magnetic insulating layer, the spin orientation between the up and down layer, upper and lower layer, will change. Okay, so that's the key idea. And we propose that this chiral phonon inside this non-magnetic insulating layer will convey the information of the spins from one layer to the other. Okay, so to do that, we need high-quality synthetic heterostructures, and that's why we turn into these oxide systems. So we have been working on this strontium ruthenate, strontium titanate system for a while now, and we have been able to propose different ideas like dimensional crossover and this phase instability within this dimensional crossover. Or we looked into the structure of this microscopic structure of this system, where this octahedral tilt pattern can be transferred, or it can be tunneled through this insulating layer. But anyway, so if you're interested more, you can talk to me later, or we can discuss it later. But basically, we have very good superlattices. So this was the first image that I showed you, and this is more larger scale, focused image. And this was done by, this TM was done by Professor Young-Min Kim in our university. So you can see that 6 layers of strontium ruthenate separated by, in this case, 6 layers of strontium titanate. This is 4 unicell, and this is 2 unicell. And you can see slight intermixing, I should say, of this ruthenate layer because probably of this step structure of the substrate. But basically, you have very good high-quality superlattices grown by Persley's epitaxy. So this also signifies the superlattice structure. So previously, this was not a superlattice. This was a heterostructure that we made to present the high quality, but this is actually superlattice structures. And you can see this beautiful, beautiful superlattice peaks appearing all over, as expected. Okay, and we can also work on this phonon dispersion modulation. If you have this nice superlattices, so you can create zone-folded acoustic phonon, and you can engineer this phonon wavelength. And for example, you have this folding, zone folding for your superlattice systems. You can have additional peaks appearing for your phonon, and this is called as a zone folded acoustic phonons. And here you can see with different types of superlattices, you can actually see from Raman spectroscopy this evolution of this phonon peak depending on the superstructures, even for the oxide systems. Okay, so now we look into the magnetic behavior of the superlattice. So this is conventional magnetic behavior of the I should say, ferromagnetic layer. So strontium ruthenate is a ferromagnet, 113. So you have a TC of 150 Kelvin or something like that. And you can see the increase of the magnetization. And you can see also the magnetic hysteresis loop as expected for the strontium ruthenate. But now if you make a superlattice, so in this case, this is 6 unicell layers of SRO. This is 4 unicell layers of STO. So you separate your SRO layers with this STO layers and repeat it for 10 times, then you can see some clipping of this hysteresis loop. Okay, so at high temperature, you have just single loop, but at lower temperature, you start to see this double loop-like behavior. So this caught to my eyes and to the experiment. And also you can see similar temperature where this clipping starts, you can see drop of this magnetization. So there's some kind of antiferromagnetic-like behavior at this low temperature, and this was the of curiosity. And furthermore, if you look into the STO thickness dependence, so you fix the SRO thickness and change the SRO, you fix the SRO thickness and change the STO thickness, so you change the separation between the layers, then you see some kind of oscillation-like behavior. So if you follow this lowest temperature magnetization, this is 6.2, 6.4 goes up, 6.6 goes down, but 6.8 goes up again. So this is a kind of puzzle to us at the first time. So first time, if you see something like this data, you see something is wrong. So either this experiment is wrong or the sample is wrong. So there can be many things that can go wrong. But this is the data. But Seung-kyo was quite persistent to do the same experiment for different sets. So now you have the second set. You see more or less the same, at least qualitative behavior of this oscillation. And it turns out he made more than 350 samples, superlative samples, and he made more than 40 in-plane measurement. And you see this type of oscillation everywhere. Okay? So as a function of, again, if you look into this, you fix the strontium rusenate layer. Previously, this was the sample. And you change the STO thickness layer, then you see this oscillation. But if you go for 8 unit cell of SRO, you still see this oscillation. 4 unit cell of SRO, you still see this oscillation. So if something like this comes up, then you have to believe this type of oscillation is real. Okay? So at low temperature, you have some magnetic ground state that oscillates with the thickness of the interspacing layer. Okay? Okay, so what's going on? Okay, so there was the question. So we can approach something like this. So we start with now changing the number of layers. So here you have 2 strontium rusenate layer. The repetition is only 2. Now you have very suppressed magnetization, meaning that something like this might be happening. So you have the opposite direction of antiferromagnetic. This is, by the way, called synthetic antiferromagnetic ground state. On the other hand, if you have third layer, one more layer, then you have a boost of this magnetization, and you can expect something like this. And 4, you should again expect something dropping, but if you go for 5th layer, it doesn't match anymore, so it should go up again, but it doesn't go up as much as you expected, so it doesn't work. But now, if you rotate this a little bit and make the vector sum of this magnetization, and then you can have something like this situation, then you can, to some extent, account for this type of magnetization. So that was our idea. Of course, we need some reference layer. Probably that's where the symmetry breaks at the interface between the substrate or the surface. But basically, you can at least explain this type of experimental data. Okay? So you can do all sorts of things. You can just add, again, this vectorial sum of these different layers, and then you can, to some extent, match this type of Z dependence. So this, again, repetition number dependence, and also the Y dependence, which is the STO thickness dependence. So, and based on this, we were to some extent trying to see how this kind of rotation, in this case this is 160 degrees rotation from one layer to the other strontium rusenate layer, and then we wanted to actually see this. And to do that, we have a tool that actually gives you, this is the polarized neutron reflectivity data done in spallation neutron source in Oak Ridge National Lab. And here you have polarization of your neutron for up and down neutrons, and you can write this. This is based on simulation, actually, but what you see is the best fit results from this type of 160-degree rotation of your spins, depending on the layer number of our superlattices. So we have 2 different experiments that corresponds to the same magnetic ground state in our superlattices. Okay, so what's the possible origin? So we first looked into the RKKY interaction because, well, there are many different origins actually that can explain the magnetic interaction between the heterostructures, super exchange, dipole-dipole interaction to start with, orange peel model, and but there aren't any that discusses the spacer layer thickness dependence, okay, except for the RKKY, of course. So RKKY actually gives you the oscillation. So there are cosine term and sine term in this. And there are oscillation of the J value, which is the exchange coupling or exchange integral. And it changes sign as you have the thickness between these two localized spins. But for the RKKY interaction to work with, you need an itinerant electrons, and your spacer layer should be metallic. And which is not the case here. The STO layer, actually, you can measure this junction transport. And SRO system is, of course, again, metallic, but you can see this huge resistivity increase, which is the resistivity value is that of the wood, actually. And you can see that this is actually the insulating, coming from the insulating behavior of the STO. So across this insulating layer, RKKY interaction cannot work well. Okay? And so that's why we think there are chiral phonons actually mediating this. One indirect evidence is that you have a wavelength of this phonon coming from the phonon velocity of SRO S5000, which is about 3 nanometers. And this is roughly in the order of the rotation period that we observe in this oscillation of the magnetization. Unfortunately, we don't have any microscopic picture for this type of chiron phonon-mediated exchange interaction. Actually, this is a very new idea that has not been proposed in anywhere. So we hope that there can be some theory working with this. We have but other evidence that can discuss this origin as of chiral phonon. So if you look back into the phonon modes of this strontium ruthenate, there are two different phonon modes. One is called AG5, the other is B2G4. And they have the phonon wavelengths of 350 and 391 wave number. Okay? But they are in bulk or orthorhombic lattice. And if you have this in tetragonal structure within the superlattices, they should become degenerate. So basically, these two are the same modes. One is oscillating left and right. The other is oscillating up and down. So they both can be pardon? 10 minutes? Okay, so they are orthogonal polarization modes. And if you introduce somehow a phase difference between these two, you can actually create this type of chiral phonon that I have introduced in the first slides. Okay, so if you look just this behavior, then you would see only one phonon again, because this is calculated for the orthorhombic lattice. If you have tetragonal lattice, this should have the same wave number. And that's what we see at higher temperature. So this is the confocal Raman spectroscopy data that we took for our superlattice samples. By the way, oxide thin films are very difficult, very challenging to measure the Raman spectroscopy. And this was only possible because of the confocal tool that we could have access in Germany. So at high temperature, you only see only one peak that's coming again from this both of this polarization. But as you go lower in temperature, and you can see 10 Kelvin or 50 Kelvin data, you can actually see that there are two peaks. And if you look this behavior, you more or less see the splitting of this peak at about 130 Kelvin. So what we think is this is the reminiscence of phonon Zeeman effect, because there isn't any structural transition across this ferromagnetic transition temperature. So there's only magnetic ordering below 130 Kelvin, and there's no way that this phonons can be separated by this. But what you actually see is that below 130 Kelvin, there is a ferromagnetic ordering, and there's an internal molecular field that actually acts as a magnetic field applied to these phonons. Okay? And if a magnetic field is applied, and you can actually see that these type of chiral phonons can emerge, and depending on the polarization, they can have energy, additional energy or lesser energy from their original state. Okay? So that's what we think, that we have actually observed this phonon Zeeman effect in our samples, and that corroborates with the existence of chiral phonon, and that can make this magnetic oscillation and magnetic interlayer exchange interaction in our samples. Okay, so this is a summary. So we think this is the manifestation of the chiral phonons in our synthetic system. So this is the first static manifestation of the chiral phonons. And this chiral phonon acting as the unconventional interlayer exchange interaction. And realization of this novel system, synthetic system, can become a playground for many different topics in physics. Okay, so additional thoughts can be any links to the topological states, because there are topological systems that actually exhibit this chiral phonon behavior. And also because 214 system is a superconductivity, and as everybody knows, phonon is an essential part of this superconductivity, and also magnetism is also a part. We can might think some correlation between this superconductivity and also this phonon behavior. With that, I thank you for your attention.
Strontium resonate films, single films, have a magnetic anisotropy pointing out of the plane, so, and it's temperature dependent. Are you saying that this is changing for thinner films or for the heterostructures, that your magnetic anisotropy puts your moment exactly in the plane?
Yes, very good question, and I'm sorry that I didn't explain it fully. So this picture should be actually a conical structure. As you said, strontium resonate has out of plane as the z-axis, magnetic z-axis, and you have a bunch of portions of magnetism along the out of plane. What I'm showing today here is only in-plane data. So all the data are in plane, and along the out of plane, you don't see this oscillation. Yeah, they are almost the same, actually. So only the in-plane, so again, in-plane is smaller than the out of plane direction, and there you see this type of oscillation.
Thanks.
Okay, thank you.
Is this something you want to comment more about? Or?
Viscosity split?
Yeah. You listed the effects of chiral phonons, and on the list you mentioned about this homogeneous viscous split in very simple. But if it's not your field. So
yeah, I'm not sure about that. So yeah, I'm sorry. Yeah.
Okay, so we go to the next talk.
Thank you.
So the next talk is by Professor Green. What? Don't you give the certificate to him? Oh, yeah, yeah. So there's actually this certificate that I forgot to give him, so I'll deliver it to him now. Yes. Yeah. No, this is okay.
Are we on? Okay. Hi, hello again. This will be blissfully short. I'm further and further away from my laboratory, and I'm used to, whenever you go to a March meeting, you hear the students always say, the March meeting came a little early this year. Well, every talk I'm doing on technical stuff is coming a little early. But this is a collaboration with my longtime partner in this work, Juan Q. Park, and Arijit Gupta, graduate student. And we do this at the National High Magnetic Field Laboratory in Florida State University. I always do that. It's upside down. Okay. So I'll do an outline, a little bit of explaining. I don't have any fantastic conclusions. I've done a lot of work in thin film growth and proximity effects since the 80s, and it's just hard stuff, and it takes a long time. So I'll start out by telling you a little bit about Andreev reflection, if you don't know about it, and the superconducting proximity effect, what planar tunneling is. A very, very, very short introduction, because most of you know most of you know more about samarium hexaboride than planar tunneling, probably. I'll show some of our tunneling results so you can see what the density of states of samarium hexaboride is in a planar tunneling junction. We grow YB6 and SMB6 thin films, bilayers, and we make tunnel junctions on them. So that was what R.G. Gupta accomplished, and these are really hero experiments. I'll show you tunneling conductance of YB6, samarium hexaboride tunnel junctions, and in looking for the proximity effect, I'll repeat this in a few more slides, you can keep the normal metal, in this case, it's like a samarium hexaboride is a normal metal, even though it's a topological insulator. And you can change the thickness. I'm sorry, I have that backwards. You can keep the superconductor the same thickness and change the thickness of the normal metal or a topological insulator. And if you see consistent effects of, as you increase the normal metal thickness, TC should go down. We see intriguing evidence, but it's really not enough to write home to mom about. So our conclusions are good films, good bilayers, good tunnel junctions, no conclusive results on the superconducting proximity effect. So these couple slides are a background. So Andreev reflection, when I first started looking at proximity effects like hundreds of years ago, we didn't realize that Andreev reflection is the microscopic explanation for the superconducting proximity effect. So what you have is in this case, this is not a topological insulator. All we have something like niobium copper. We have a normal metal and a superconductor and their interface, a clean interface we're assuming here. So Andreev reflection is basically if you inject an electron into the superconductor, it retroreflects in the same angle as a hole, and it's all taken up by Cooper pair going into the superconductor. I'm going to show, if that sounds fantastic to you, what I'll do is I'll show you this next slide here, which basically says that when you think of Andreev reflection, you have an electron coming in at the Fermi energy. So here, if you look at this picture here, there's the Fermi energy up here, and here's nominally a dispersion of a free electron or in a Fermi liquid or whatever. And remember, the Fermi energy in simple metals is like volts, okay? 2 volts, 5 volts, depending on the metal. If you're looking at a superconducting gap, that's on the order of a few millivolts, okay? So what we're saying here, if we go, this is my explanation thing. What we're saying here is that why would you have an electron that can't enter into a superconductor, right? You have something like I'm going to keep doing this every time I use these things. So you have this very, very high energy electron, then it can't go into the superconductor, and the superconductor says, no, 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 you're going to retroreflect as a whole. Why does it do that? Because it's quantum mechanics, right? This is like a freight train seeing a cardboard box and it's being reflected by the cardboard box, okay? It's like, so the reason for that is that if you try to inject it, this is the only, if you go look at the original paper by Andreev, which wasn't for transport, it was for heat exchange, but the original paper is simply a boundary value problem. How do you have this electron Cooper pair interface, and you want to inject an electron? The boundary value question says, in order to conserve charge, energy, and momentum, this is the only process. And I'm always saying when I introduce students to this, if beta decay doesn't bother you, this shouldn't. It's a simple particle conversion process. In any case, going back to here, so this graph at the bottom here is very interesting. So what happens when you have this Andreev reflection is that this electron gets injected into here, and before it grabs another electron to make a Cooper pair, which you have to have in the superconductor, right? In a superconductor gap, there's no quasi-particles there if you have a good gap. So what happens is at this interface here, at a certain coherence length of this normal metal, and that does exist, we can talk about that another time, you actually end up breaking some pairs, so you have a decrease in the number of Cooper pairs that you find on the normal metal side. So this is simply a plot of psi star psi, which was Landau showed us was the probability of finding Cooper pairs. I mean, Gorkov was the one that proved that. And then on the normal metal side, when the electron goes in and bounces off and a hole gets sent out, what happens, it picks up the coherence. It goes into the superconductor, picks up the coherence. So for a small distance inside the superconductor, inside the normal metal, you have picked up some of the coherence, and so you have a little bit of superconductivity. So the idea of a Cooper pair linking from a superconductor to a normal metal isn't really the case. It's really a clean Andreev reflection. You can calculate all this stuff. It's actually pretty cool. So, going right along here and moving along. So, how can you measure the superconducting proximity effect? So I've been doing this for a few years, and it's hard stuff. But what you can do is, if you have, looking at this picture at the bottom, if you have a thin film superconductor that's about the thickness of the coherence length. So I'm just going to walk up to here because this isn't. So you make this thin film superconductor that's only this thick, okay? And then if you make the normal metal thicker and thicker and thicker, the equations show you that you will have more and more Andreev reflection that will break more and more pairs in the superconductor. So you will reduce the TC of the superconductor. That's a very hard measurement. That's a really hard measurement. I've tried that for many years in many different kinds of materials, and I gave up because the numbers are very small. The better way to do it, the easier way to do it, and this has been done by a lot of people in different ways, is that you grow a normal metal. You grow the normal metal and a superconductor, and on top of the normal metal, you grow a tunnel junction. And you see that as the normal metal gets thicker and thicker, there will be a density of states induced in the superconductor. A density of states from the superconductor induced into the normal metal, and that should decrease as the normal metal gets thicker and thicker. Because I wish I had more pictures here, but I was doing this too quickly. Because if you can imagine, if you're measuring the gap in this material and the normal metal gets thicker and thicker and thicker, then the gap will be more and more decreased because there's less of penetration of the Cooper pairs or the coherence in the normal metal. So that's what we're attempting to do. So I guess I did do this years and years ago. I just wanted to point this out. I said they're tough experiments. In the 1980s, I grew cerium copper-6 heavy fermions on top of niobium and showed an interesting results about proximity effects. But we'll go on now. We're not going to talk about that here. So moving right along, and I'm going the wrong way again. I'll keep doing that. OK, so this is the kind of thing that the student puts in here, which is, this is the nominal motivation of this experiment. I'm not sure this is the motivation of this experiment because I'm not sure about Mariana fermions, but that's my own prejudice. But the whole idea was Liang Fu and Charlie Kane came out with this really beautiful theory a bunch of years ago. And they thought that you could create a topological superconductor by putting a topological insulator on top of a trivial superconductor. And so that's what we're trying to do and see what we get there. So, oh my gosh, what happened there? So that's the problem of going from a Mac to a PC. Okay, so what we have here is a very, very short introduction to planar tunneling. And I was going to say, maybe I won't go into all this, but I'll just use the words. You can't read this, okay? You've probably all seen this before. If you have a planar tunnel junction, it's flat, and you have like a superconductor, insulator, and normal metal. And the normal metal density of states looks like the Fermi liquid up there. The superconducting, we've seen that many, many times. One thing is and this is a take-home point that I'd like you to have here, is that there's something that was written in I forget now, Harrison's theorem. Was it the 70s? I don't remember. But people were wondering why you see a superconducting gap like that when you're tunneling. If you think about it, if you write down the tunneling equations, which are simply the Fermi golden rule, the most beautiful equation that's ever existed, what you have is in that tunnel equation, you have the Fermi velocity times the density of states. You have dE by dk multiplied by dk by dE. You should completely divide out the density of states. I'm going to say that again. When you write down the standard one-dimensional Fermi liquid tunneling equations, you should always get Ohm's law. Why? Because I'm going to repeat it, you multiply the Fermi velocity times the density of states, and they divide out. And then people were wondering, why do you see a superconducting gap? Very simple. A superconductor is not a Fermi insulator. So just like I said in my talk yesterday afternoon, right, that in a simple Fermi liquid, the Fermi velocity, the density of states, all these properties are determined by the lattice and what's in it. When you have electron-electron correlations, like in a simple superconductor, that doesn't work anymore. So what a tunnel junction measures, what a planar tunnel junction measures, is non-Fermi density of states, okay? So if you want to take that home, I wish I had time to write all this up. So will this work here? Okay, so let's look and see. This is some old work that we did a while ago, which was tunneling into samarium hexaboride. And and we got the crystals outside, and I don't have the names in front of me right now because it was in 2016, which was, I think it was before the pandemic, so it was 600 years ago or something. So anyhow, we polished the samarium hexaboride, learn how to make good tunnel junctions, and put lead on the top. What you do is you tunnel into that, and you look at, this is the thing that I've been doing for 100 years also, is that you look at the quality of the lead tunneling, okay? So if we look at this here in the center picture, what we see in red is the lead superconducting samarium hexaboride tunnel junction. And you can see that you see something like, that looks like a lead gap in the center, and you study that, and you work on these until the quality of that lead gap looks really good, because we know what a good lead density of states looks like. And then you drive the lead normal, and that gives you confidence that your tunnel junction is good. So this is, standard if you want to look at a non-Fermi liquid material, you don't know whether you have a good tunnel junction or not, and the measure is to put a known superconductor as a counter electrode, drive it normal. Okay? In the early days with high TC, we drove it normal with temperature. In this case, it's very easy. You can drive it normal with the kilogauss, right? That drives the lead normal. So in the blue curves there, again, this is old work. In the blue curves there, that's when we put on about a kilogauss a field, 0.1 Tesla, drove the lead normal. So what we have there is the density of states of the samarium hexaboride. This is not flat, okay? There's no superconductivity there, but it's not a Fermi liquid because planar tunneling measures non-Fermi liquid behavior because of what I just explained before. So what we did is study this in a lot of detail, and I'm not going to go into all this, but you can fit this just as you would expect to 2 Dirac cones. That was predicted what it should look like. And then these other bumps are having to do with the topological surface states interacting with the spin exciton, but I really don't want to go into that now, so let's just move on to our thin films and proximity effects. So what we do in these materials, oops, backwards again, is we grow the thin film growth and transport measurements. These are just for quality. So everything is sputtered. The samarium hexaboride and the yttrium hexaboride are both studied, are both sputtered, magnetron sputtering. And what we do, since the boron it gets undercompensated, you have to add boron. That's something that we learned a long time ago, is that there's certain rules about sputtering, and alloys are very different than compounds. So whatever your target is not necessarily what you get on your substrate. If it is, it's an alloy, but that's not true if it's a compound. So a bunch of playing around. These are the parameters. We co-sputter samarium hexaboride and boron. We co-sputter boron, yttrium hexaboride and yttrium, and we get very good films. And in all of what we're doing, the data I'm going to show you, and it won't take very long, the YB6 thicknesses is 1,000 angstroms, and we change the samarium hexaboride thickness, goes to 25, 35, 75, 100 angstroms. And we'll just show you some nice data now. So what we have here is the quality of the YB6 thin films, and we see that the TC is 5.71. The literature quotes about that. It actually quotes a little bit longer. But there's a paper that says, when I've done this before in niobium, you can put a certain strain on certain kinds of superconductors and increase TC a little bit. But it looks pretty good. And the other thing is that it's strongly coupled. If we do the HC2 experiments, we get that HC2 is strong coupling. So we get HC2 about 1.43 Tesla. Okay, so they're good films. Now this is the this is the bilayer and tunnel junction. So on a magnesium oxide substrate, you go thin film. In this case, and all the ones I'm going to report you, they're, RG probably grew 500 films now, but I'm just going to show you 4 sets of bilayers. YB6, and on top of that, you go the samarium hexaboride, and on top of that, to make the tunnel junction, there's 2 ways to do it. They're both comparable. One way is to in situ plasma oxidize the surface, and the other one is to add just a little bit of, this works a little bit better, you sputter down just a little bit of boron, so you get a boron oxide, BOX, we don't know what the oxide is, the interface. And then we can get pretty reproducible tunnel junctions. So what we have here is YB6 silver tunnel junctions. So this is showing the superconducting density of states for YB6. Okay, so we've got the superconductor we've measured it several ways, and this is the density of states. Now we fit all of these things to 2 models. The first one we fit that it's like the industry standard is the BTK, Blonder-Tinkham-Clapbook model. And that tells you what the tunnel junction is. It tells you how strong the barrier is. It tells you, the gap and things like that, how much scattering there is in the junction. And we get pretty reasonable results, and the gap is about 4 millielectron volts. Okay? And then I'll just keep doing that. Now here's an example of, I'm not showing you all the data on this junction. I just want to show and get this over with. But here's some temperature dependence. It looks good. Okay? It looks like you'd expect for a superconducting density stage of the YB6. It's got a small but finite barrier. And it's an agreement using the BDR. What the BDR is the Brinkman, Dines, and Rao. This is another industry standard that if you want to figure out what your tunnel barrier looks like, you fit it to a parabolic background. If all your information is down in the millivolt if you want to find the density of states. But when you get out to the high energies, you better see a parabolic background. Okay, until you get to very high energies, then it goes exponential, but that's another story. So the fact that we get this beautiful parabolic background, that red line in the middle is the fit, means these are pretty darn good tunnel junctions. And in each of those, you can see the thickness is like about 20 angstroms in all of them, and the height is like 1 to 3 EV, 1 to 4 EV. So, that's pretty reproducible when it comes to planar tunnel junctions. The exact value isn't so important, but if it went from 1 to 600 EV, that would be a problem. So this is pretty reproducible for fabricated tunnel junctions. So here's one, that was 25 angstroms. So the data that I showed you here and on the previous slide was 1,000 angstroms of YB6, 25 angstroms of samarium hexaboride, and we see that we can see tunneling, the temperature dependence of the tunneling, and a nice background that is a good tunnel junction. When we go to 35 angstroms, I'm doing this again. When we go to 35 angstroms, it's a messier tunnel junction. RG measured these many, many times. These are some of the best junctions, of course. That's what you show when you're at a conference or in a paper. But it's pretty reproducible that at 35 angstroms, the superconductivity looks a little weaker. The gap is smaller, and and then going on, and then we can see it still looks like a good tunnel junction. Over up to, a couple hundred millivolts, you still have a parabolic tunneling conductance. So it's a good, strong tunnel junction. Moving right along, we go to 75 angstroms. By 75, so this is, I should have more pictures here, I apologize. You have the superconductor, YB6, your samarium hexaboride that's now grown from 25, 35, now it's 75 angstroms. You're tunneling into there, and you don't see the superconductivity of the YB6 under the SMB6. I hope I'm not 10 more minutes. I hope I'm 4 more minutes. But so this, if you can remember in your head what the tunneling into the samarium hexaboride single crystals were that I showed you earlier on, it had these 2 Dirac cone shapes. This is what it looks like. It's a little blurred, but it's a thin film. But it still looks like it's samarium hexaboride. Now we're going to go to the, do you think I went the wrong way again? I wonder if I'll never stop doing that. So even in this case, where we don't see any superconductivity, Oh, let me go back and make another statement. Remember I told you that if you wanted the quality, this is something I figured out by using lead tunneling into YBCO in the 80s, okay, was that if you do enough of these, right, you do the lead tunneling and you drive the lead normal and you measure all the density of states of the new material, in this case, samarium hexaboride. You do this enough times, the quality of the density of states of the samarium hexaboride is no weaker a tunnel junction diagnostic anymore. We know what this looks like. So this looks like all the tunneling is samarium hexaboride. So even though we don't see lead, we still know that that is what the samarium hexaboride density of states in that energy range is supposed to look like. And so moving right along, then the 75 angstroms. Now we go to 100 angstroms. So this is the tunneling 100 angstroms. Again, the other one was not as clear. This looks almost like the bulk samarium hexaboride tunneling. Okay, so where are we now? And that again with this, we have a parabolic tunnel junction up to more than a couple hundred millivolts. So these are good tunnel junctions. We're not done. So this is our summary. This is my last slide. I have another slide, but I'm going to let the slide slide. So we have great, high-quality planar tunnel junctions. Okay, great films, great bilayers, great tunnel junctions. We have data on 25 and 35, and when there's a thinner film of so we tunnel into the superconductor YB6, and we see the tunneling density states. We put a little thin film of 25 angstrom of the samarium hexaboride on the top, and we still see the superconducting density states of the YB6. You make it a little thicker, now 35 angstroms, it's a little weaker. You jump to 75 angstroms and 100 angstroms of the thickness of the topological insulator, and we don't see the tunneling density of states of the YB6 anymore. So this is sort of what you would expect if there was a proximity effect for niobium copper or something like that. But all we can say is that we're going to keep working on this and see what we can find. Do I ever think I'm going to see a Myron, a fermion? Again, I would love to challenge anybody, but I don't see what the difference is between a Myron, a fermion, and an Andreev bound state, but that's my thought. So these are my non-conclusions, and I'm happy to answer any questions if I'm able to. Thank you very much. We'll sit up here at the next, and we'll make up, okay?
It's a beautiful data set. Well, I have a question about the samarium hexaboride thin films. I mean, you guys have done like a wonderful growth, from 2.5 nanometer to all the way to 100 nanometer, right? So my question is that, were you able to characterize the quality of thin film? Like, for instance, 2.5 nanometer compared with 100 nanometer thin film. Is the quality different?
Of the samarium hexaboride?
Yeah, samarium hexaboride. And is it?
Yeah.
And is it like a single crystalline quality thin film or polycrystalline thin film?
They're polycrystalline. They're oriented. I don't remember all the data because I haven't turned a knob in my laboratory in years, and you'll have to ask Arajit. So when I was throwing this talk together, I was looking for the data. There are data that exists, and as it gets a little thicker, the samarium hexaboride gets better. But it's also getting good X-ray diffraction on a 25 angstrom film. We just don't have it. So we've done some EDAX on them, and we get the ratios is about right. But as far as the crystallinity, we haven't really looked at that. We just don't have, it would be nice to. Maybe you can help us.
Thank you.
But that's the perfect question. Thank you.
May you say something about the interdiffusion at the interface, because you sputter at a high temperature? So maybe this influence also the proximity, right?
Absolutely, and we can't rule that out yet. I would like to rule that out. I think it would be difficult. I'm not quite sure how to rule that out. I don't always like to worry about that but doing something like, grazing angle, X-ray diffraction is one. That's really hard. And the other one that I would love to do is, what's that? Rutherford backscattering, right? And you can compare, but comparing Samaritan, they're close in Z, but if you do Rutherford backscattering at a sharp angle, you might be able to separate those. And the other thing to do would be Auger, right? To dig through the Auger. But we don't know that yet. That's definitely an open question.
So you don't know any direct proof about the interface, right? Between in your bilayer. Okay.
No, we don't.
Okay. Yeah.
We don't.
Okay.
But we have good films and good junctions. And we don't, and like I said, I can't tell you if there's a superconducting proximity effect because there could be diffusion, absolutely.
Any other questions?
And actually, I expect diffusion from my other work in growing rare earths, so, to be honest.
Yeah, this is a follow-up. Basically, I was going to ask you the same, but what we do with some of these very thin layers when we modify them is to make a fib cut so that we can look at the interface.
Oh, yeah.
Essentially, and then you have not...
No, we just started doing it. I don't have the person power in my laboratory. I mean, so when I was doing this, when I was in the lab, I never slept. I was working, and I found ways to do this, with my films in my teeth, running into other laboratories. I don't do that anymore. So if it's just going to be slower, I don't have the funding I used to have, so I have one student, and Dr. Park is working with him, and it's a small operation. So I'm happy that we can grow nice films. Life's good. Arajit even won an award at a local conference. So
maybe we can talk about it.
Okay. Yeah, sure. I mean, any progress. There's a whole mosaic of physics. If you can fill out something, you're good.
So I understand very much how difficult to sterilize this thin film, so I really understand the joy when somebody... So, but now I have a question about so supposedly one can realize perfect junctions, right? And the theory in this superconductor topological insulators speaks about these Majorana fermions, right? So even in the... So there is something that the theory doesn't take in account. So in some sense that even if you create a perfect material, right, you don't see what the theory predicts. So at the end, is the theory not considering something? So basically, what is your opinion about this? So in some sense, the theory cannot, so even if the experimentalists realize the best possible structures, right? Okay. And we make not complex superconducting architectures or just basically a tunnel junction, right? And we cannot still prove or disprove the theory. So, or we are not good as experimentalists, because this is a field that is going on from, let's say, already quite some time. And, or the theory has some flaw. So what did the two? I mean, we should be able to give an answer to this at some point. So what is your opinion?
So give an answer to what? To whether there's a proximity effect or to whether there's Majorana fermions?
If we have not yet realized a perfect junction to prove the theory, or because it's an experimental problem, or the theory doesn't take into consideration something. And
well, isn't that the fun? Okay, so when I was trying to learn how to tunnel into high TC junctions, right, I was reminded by a colleague of mine that it took people almost 30 years to make reliable tunnel junctions in niobium, right? This is hard stuff, and just like we have all these different questions in non-Fermi liquids, we're going to work it out. And but I have to tell you, I do. If I start seeing zero bias modes in these things, zero energy modes, I know what to do with them. I've discovered many zero bias anomalies, and I've studied them my whole life, and so when I get there, I will be able to do the analysis to see if the theory is right or wrong. So, but I can't yet. We don't know.
Because these zero bias anomalies appears also in the junction of the cuprates. For example, if you put a C.
Yeah, well, that's me, right? I mean, people see zero bias anomalies, but it took a few years of work to determine how they would do to Andreev bound states, and when they showed up and when they didn't show up, okay? And, it was a lot of work, a lot of reproducibility, when they showed up and when they didn't show up. Seeing a zero bias anomaly in a nominally 110 oriented YBCO film, okay, doesn't prove it's an Andreev bound state. It's the field dependence, it's the angle of the field dependence, it's a huge amount of things like that. And so those are the kind of things that if we get this thing reproducible, we know our interfaces, we'll nail it. Maybe I should take a sabbatical and go into the lab. So that's a really great question. And I have to say, it kind of gets on my nerves when someone shows us. And I get in trouble because I start picking apart the data and saying, you see a zero bias anomaly, and you know, that's great, but what have you proved? So all I can do is, that is a great statement, and as long as you don't overclaim. Okay? If you're going to say that you saw a Myron fermion, if you're going to say you saw a room temperature superconductor, those are extraordinary claims. And if they're right, they will have extraordinary proof. And that's the goal. And so I just completely agree with all the questions here. They're great. So, uh-oh. Can I disagree with yours already? No.
Laura, making these thin films is certainly a challenge, and I appreciate that. But I have a question with respect to your thinnest film from a completely different perspective. If I recall correctly, from a parallel resistor model, the layer or the thickness of the layer of the surface states was estimated to about 6 nanometers or so.
You mean of the conducting surface stage of the SMB6?
Yeah.
Okay.
So your thinnest films are thinner than that.
Yeah.
So your SMB6 is no longer an insulator. If you go to the thicker films, then you basically you have in between the insulating bark. Don't you see that transition somewhere or somehow?
Not yet. You know, we don't have the analysis to say that, the fact that we, if we get, so we've thought about that, but I'm really scared to make a claim. So when you're down to 25 angstroms thick, is there any insulator left in the center? Is that why we see, okay? And I will just, and that has to be worked out, okay? But that also tells you that if you see the YB6 underneath, that's pretty cool, okay? You're at least seeing some gap that's going through. And then as you get thicker, you have to look at that transition. And what's the big problem here? We have 25, 35, 75. Where's our 45, 50, 55? That all has to be done. So I have to pay Arajit more. So those are really, really good questions.
Let me ask you the last question.
No.
What would be the experimental evidence for marijuana fermions in this kind of systems?
Well, it would be a zero bias mode, right? But that's nominally what it would be. But
that will appear as a P, right, in the
yeah,
middle of?
Yeah.
Okay. Thank you very much for a very interesting talk. And I must not forget to present you with this wonderful
I get another
certificate
picture.
for your talk.
Oh, thank you very much. Appreciate it. Thank you. I got another one. Oh, boy. Okay. So I hope we made up some time. Maybe not. next session here, and we have, I've got to find this now, we have Dr. Eric Young, Korea University Department of Physics in South Korea. The title is New Disordered Anion Phase of Doped Graphene Zigzag Nanoribbon.
Thank you. Yeah, so that was title of my talk. So I'll first give you a very broad overview of the subject, and then I'll argue that the when our fractional charges are anions, they are semions. They are exactly between fermions and bosons. Then I'll argue that these semions give rise to spin charge separation and edge magnetic domains. Then I'll show you that this system, this zigzag nanoribbon, is a topologically ordered insulator. I'll show you that the topological entanglement entropy is finite and universal, independent of disorder and on-site repulsion. Then I'll show you a second evidence for topological ordered state. I'll show you that the entanglement spectrum is identical to the edge spectrum of the system. These two are hallmark properties of topological ordered insulators. And then I'll talk about some possible experiments to measure fractional charges. And I should say that this is not some kind of academical exercise that a theorist has cooked up. Recently, it has been possible to make atomically precise graphene zigzag nanoribbons. There are a couple of papers in Nature. My work was based on Hartree-Fock and density matrix renormalization group in the matrix product representation. But this is not going to be a technical talk, so I'll skip all the mathematical derivations. So what is a zigzag nanoribbon? I have drawn here zigzag nanoribbon. These boundary carbon atoms constitute zigzag edge sites. And at the opposite boundary, you also have carbon atoms. Now, if you use periodic boundary conditions on the left and right edges, you can transform this planar structure into a cylinder. And at cylinder edges, you have zigzag edges. Now, if you use Hubbard model and calculate the site magnetization, then you find that the left edge is ferromagnetically polarized, and the right zigzag edge is also ferromagnetically polarized. But those two edge magnetic polarizations are antiferromagnetically coupled. Now, in the absence of disorder, this system is symmetrically protected topological phase. This is because of the chiral symmetry guarantees the existence of edge states. What do I mean by chiral symmetry? It means that if you exchange black and white carbon atoms, you basically have the same lattice structure. Now, what is the role of disorder in this system? It turns out that disorder is a very singular perturbation. Ooh, why? understand why doesn't it go to the next? Doesn't work? It's stop. Okay, thank you. So this is the button that I should, yeah. Yeah, that's what I did, so. Okay, yeah. So let me move on to the next slide. So, we know several topological ordered insulators. The best known one is superconductor, and also we know integer quantum Hall states and fractional quantum Hall states. They are all topological ordered insulators. And there's also chiral spin liquids. That is a topological ordered insulator. Now, it's not easy to find a new topologically ordered insulator because there is no symmetry that helps you to find such an insulator. So you have to basically use trial and error method. Now, also one knows that one-dimensional gap-filled systems cannot have topological order. This is shown mathematically. The system that I'm considering here is quasi-one-dimensional zigzag ribbon with disorder. So there is a loophole to escape from this theorem. And also, this quasi-one-dimensional zigzag nanoribbon with disorder is a Mott-Anderson insulator with a soft gap, and it is topologically ordered. That's what I'm going to argue in this talk. So the basic physics is the interplay between Mott physics and Anderson localization. And I'll use a Hubbard model to argue this. Okay, now I'm going to show you two slides that are very crucial in my talk. The rest of my talk are just elaborations of these two slides. So let me compare the properties of disordered zigzag nanoribbon and Laughlin states. There are similarities and differences. Disordered zigzag nanoribbon, the ground state has twofold degeneracy, and Laughlin state has n-fold degeneracy, where m is an odd integer. Now, disordered zigzag nanoribbon has 1/2 fractional charge, but the Laughlin state has 1/m fractional charge. Now, suppose you add extra electrons to the undoped system. Then, in the disordered zigzag ribbon case, you get distorted edge spin density wave. In the Laughlin states, you get the so-called hierarchical quantum Hall states. Well, what about edge excitations? In the ribbon case, they are exponentially suppressed. In the Laughlin state, you have gapless chiral excitations. What about the gap? In disordered ribbon, the gap is exponentially suppressed, so you have a soft gap. In the Laughlin state, you have a hard gap. And the most important difference between these two systems is that edge modes are non-propagating in the ribbon system. And the edge modes are non-chiral. Okay? Oops. Yeah, this is the next important slide of my talk. So here I have drawn the phase diagram of zigzag nanonibbon. The z-axis represents disorder strength, and this y-axis represents on-site repulsion, and this x-axis represents doping. Now, in the inside this yellow volume, fractional charges are well defined, and there are long-range correlations between left and right zigzag edges. Now, in this blurred region, you have fewer fractional charges, and there is no longer long-range correlations. And topological entanglement entropy fluctuates. It's not well defined. So I'll call this region quasi-topologically ordered. Yeah, so now these three figures are just slides of this three-dimensional phase diagram. Yeah, TO means topological order, QTO means quasi-topologically ordered, and NFC means no fractional charges. Yeah. Now, why are there these phases where you have strong fluctuations of topological entanglement entropy? It's basically the effect of Anderson localization. I'll explain in detail about this. So these are basic summary of topological order zigzag nanoribbons. What follows are just elaborations of these statements. So let me explain to you the basic properties of disordered zigzag nanoribbons. Let's first consider non-interacting in the absence of disorder. We can do simple type binding calculation. The results are shown here with the dashed lines. We see that there are many degenerate states near energy zero. They represent edge modes. These modes are localized on zigzag edges. Okay. Now let's turn on on-site repulsion. Then mud gap is produced, as I've shown here, and the edge modes are now split like this way. So edge modes are here and here. Okay. Now I have shown here probability densities of edge modes. One is localized on the left zigzag edge, and the other one is localized on the right zigzag edge, like this. Now, what happens if I introduce disorder? You get this kind of bonding and anti-bonding states. So they appear to be split. So their charges appear to be split in half. And this is the graphic, more careful graphic picture of the split gap edge states. Now, you may wonder whether this is a true charge fractionalization. It isn't, because, for example, in double quantum world, you have also bonding and anti-bonding states, and you do not call them fractional charges. Okay? I'll explain later why this cannot be a true charge fractionalization. Now, this is what happens when you put disorder, right? So as I said, you produce gap edge states. There is one more important feature, namely that there is a spin splitting, right? So that's why you get Mott-Anderson insulator. You have to have spin split gap states. Okay, and in the weak disorder regime, you can see the digital states of gap edge states here. And you have soft gap in the middle, okay? Like this. Now, it's very important that you have a soft gap in the middle. That protects you, that protects fractional charges against quantum fluctuations. If you close this gap, then quantum fluctuations will kill charge fractionalization. I'll explain this to you later. Oops. Okay, now let's suppose that there are true charge fractionalization. What are the effects of it? Now, there is spin charge separation and domain walls in the zigzag edges. Now, let me explain this. Now, suppose you consider this magnetic domain here. Why is this magnetic domain related to the presence, related to fractional charges? I'll explain that here. These pictures show edge occupation numbers for spin up and spin down. Now suppose you move 1/2 electron from left edge to the right edge. Now, it costs a lot of energy because the density is no longer uniform, it's non-uniform. So energetically it's costly. So what you can do is you can move fractional charges from right edge to the left edge. Then density is more or less uniform. But then spin is no longer uniform. If you add these two densities, you will see there is a bump here. So transfer of fractional charges are very important. Now, what about spin charge separation? Why do fractional charges lead to spin charge separation? Again, let's imagine that the 1/2 electron moves from left edge to the right edge, like this. And then 1/2 charge moves from right edge to the left edge. Then the resulting spin density looks like this. It's 0 in this spot. So spin is 0, but charge is not 0. And that's what you see here and here. So you have an object that's spin 0 with charge E. This is spin charge separation. Now this is very similar to what's happening in polyacetylene. This is experimental evidence for presence of spin charge separation in polyacetylene. You dope polyacetylene, then you measure conductivity and also spin susceptibility. But strange thing happens here in this low doped region. Conductivity increases, but spin susceptibility is 0. So that means spin and charge act independently of each other. And something similar is happening in the disordered zigzag and nanoribbon. Now, fractional charge anions, they are semions. Now, suppose you exchange 2 electrons, and in this case, it's equivalent to double exchange of 2 fractional charges. So that means this is 1 electron. This is another electron. Each of them consists of 2 fractional charges. Now, you exchange first these 2 fractional charges, and then you exchange these 2 fractional charges. The result is that you have exchanged 2 electrons. And each exchange of 2 fractional charges gives unusual statistical phase. So this is an anion. Okay, now this is some technical matter, but here this picture shows that the topological entanglement entropy is universal. It's independent of disorder strength and on-site repulsion. You can see that it's almost constant. This is for the lower curve is for smaller system, so there is finite size effect. If you make system larger, fluctuations have decreased. Okay? And the other thing is you could also calculate the entanglement entropy spectrum, and it should be similar to the edge excitation density of states. You can see that it's a Gaussian. This DOS is Gaussian, and also the edge spectrum is Gaussian. These are 2 hallmarks, hallmark evidence for a topologically ordered system. Okay, so as I said in the beginning, it's not all theoretical exercise. This has a real experimental chance to be observed. And I propose this experiment. You dope ribbon, and you do tunneling experiment, like this. This is normal matter, and this is a disordered ribbon. According to our work, if an electron tunnels into the zigzag ribbon, it should divide into 2 fractional charges. If you calculate the tunneling density of states, you have a peak in the middle. And if I blow up, it looks like this. Now, is this good evidence for existence of fractional charges? Not quite. I mean, there may be some other reasons for this middle peak. So what I propose is you measure the peak value as function of a doping level. And in this case, you see that it shows very strong nonlinear behavior. And I don't know any other system in condensed matter system that shows this kind of nonlinear behavior as function of doping level. What's happening is if you put too much electrons, if you dope it too much, then fractional charges no longer exist. So I believe that this is very strong. This would be a very strong evidence for the existence of fractional charges. Now, if I plot probability density of a state in this peak, you see that the peak is split into 2. And there is essentially very little overlap between these 2 peaks. If they overlap, then fractional quantization is destroyed. Okay, now, this is some interesting physics. Let's see. Here, you see that the fractional states are quite degenerate. So quantum fluctuation may destroy fractional charges, but I argue that that's not the case. That's because of Anderson localization effect. What is Anderson localization effect? I don't think many people realize this. Of course, experts in Anderson localization know about this. What this is saying is that suppose you have Anderson localization and two states are nearly degenerate. Then, because of localization effect, they must be physically separated. That's what I'm showing here. These two states have very close energy, but you can see that they are physically separated. So quantum fluctuations cannot destroy fractional charges in this case. Now, in double Weld case, you also have nearly degenerate states, namely bonding and anti-bonding states. But here, you see that bonding and anti-bonding states overlap each other very much. They are, hardly distinguishable. So in that case, fractional charge is not well defined. But in disordered zigzag E1, because of Anderson localization, they are physically separated. Yeah, and this picture shows that if you dope the system, you get distorted edge spin density wave. This is the left edge. This is side spins for the left edge, and this is for right zigzag edge. You can see that you can see spin density waves, very distorted spin density waves. And the other important thing is that left edge and right edge are long-range correlated. Where there are modulations in the left edge, if you have modulations in the left edge, you have also modulations in the right edge. And these two edges are separated. And so they must be long-range correlated. Okay? Of course, you have to have long-range correlations in the topological order system. This just confirms that. Yeah, this is my summary. I basically explained this picture in the beginning, so I will not repeat it here. And let me just show you the next slide. I wrote a graduate textbook on topological order zigzag nanoribbon, and I expect it to be published at the end of this year or in the beginning of next year. This book first explains other topological order insulators, superconductors, P-wave superconductors, integer quantum Hall effect, and fractional quantum Hall effect, and spin liquids and anomalous quantum Hall effect. Now, after these, I explain topological order zigzag nanoribbons. Okay, thank you very much.
Thank you very much. This paper is open for questions and discussion.
I guess this was not
Well,
easy subject.
Yeah, well, I'm trying to think of a question because it's a little over my head, but.
Okay.
But so let me thank you very much, and I can't wait till your textbook comes out because I have a lot to learn. So Dr. Yang, thank you very much for your talk.
Thank you very much.
And, we appreciate it. Okay, I'm going to get off the stage. Is Tucson's going to chair the rest of the couple? Are you here? Oh, there you are.
Okay, so my name is Tucson Park, and co-chair of the session with Laura. And the second talk of this session is by Professor Tomasz Klimczuk from Gdańsk University of Technology, one of my good friends. And he's going to talk about synthesis and superconductivity in novel non-central symmetric boride. Please.
Thank you, Tucson. Thank you very much for inviting me here. It's my great pleasure. I promised my sons that I will give them best regards because it's live streaming. So let me start. The title of the talk is Synthesis and Superconductivity in Novel Compounds. My obsessions are new superconductors, but I love everything what is new. So let me start with the outline. I will start with the introduction. Then there will be part about the synthesis, then the crystallographic. Sorry for the typo, physical properties, and I will finish with the summary. So I am quite often asked, how do we search for new compounds? How do we find new superconductors? And here is the matrix. I will show you a few examples. All the examples come from my laboratory, from Gdańsk University of Technology. So what we do, first of all, we check the database. There are 4 strategies that are shown here. So depending what is known or unknown in the system. So you can see that there is a structure type, chemical compound, and physical property. So if everything is known, you can ask me, what are you looking for in such a case? But actually there is a lot of things to be done, and I will show you in a minute. Then another strategy is if the structure type and chemical compound are known and the physical properties are unknown, the next one is as shown, and finally, you know nothing. So Paul Canfield used to say unknown, unknown, or known, unknown, and so on. So it's pretty much the same. You know this person for sure, at least you know the story about him. I am too young and still old, but I have never had a chance to meet Bernd Matthias, of course, but he was a superconductor hunter during 1950s, 1960s, and here is his paper. 1 page, just 1 page physical review paper. 8 superconductors reported in the same paper. No figures, no superconducting properties. That's exactly what I am showing here. Everything is known, but we were interested in just because there was no superconducting properties for calcium bismuth 2. Calcium bismuth 2, and besides, Tc seems to be strange, 1.7 Kelvin. And another thing is that there was a theory paper published in this scientific reports, and theorists expected Tc as high as 5.16, so it's way higher than 1.7 in Bernd Matthias' paper. And my student who is sitting here, now he's not my student, he's already a PhD and DSc candidate, grew crystals. And as you can see, calcium bismuth 3 looks like that. Of course, it's strange because calcium bismuth 3 is supposed to form in a cubic phase, so it's not a cube. And besides, another point which is strange is that the fact that we are way above the Long-Petit law. So we checked the EDS, and it appeared it's not calcium bismuth 3, it's calcium bismuth 2. But still, it's a superconductor with Tc 2.2. It's a very interesting superconductor because the bismuth forms the square lattice, and because it's a 2-dimensional superconductor. The paper was published. I think it's like 5 years ago or so. Another 3 examples of this strategy, everything is known, is lithium bismuth, cerium iridium free, thorium iridium free. So there are a lot of things you can be done with a strange strategy that everything is known. Another example, but now we have a second strategy. So structure type is known, chemical compound is known, and paper is already published in a PNAS, Proceedings of National Academy of Science, and the title is Structure of Super Hard Tungsten Tetraboride. The paper was published by UCLA group, and fortunately to us, they have not measured the low temperature magnetic susceptibility, and we found it's a superconductor, so the title is Superconductivity in the Super Hard Boride WB 4.2. Okay, then I think, I'm sorry, okay. Another example could be lithium palladium to germanium and lithium palladium to silicon, but actually Dr. Michał Winiarski is going to give a talk about this tomorrow at 5 p.m. in Hall 2, so I just skip it. The strategy number 3, structure type is known. So we know the structure type, and we replace 1 or 2 atoms, or 3 atoms. This is a paper from 1997. 1997 from Bell Lab. Bob Cava published a paper about lanthanum-3, copper-4, phosphorus-4, O2. And a few years later, when all these iron arsenides were published or studied, I went back to this paper and I found that possibly copper can be replaced by nickel. And we made lanthanum-3 nickel-4 P4O2 with TC 2.2 Kelvin. Okay, TC is low still, but anyway, that's another example, another material in this big family of the iron oxy arsenides or iron arsenides, nickel arsenides, and so on and so on. Now, I smoothly go to the titled compound, and still, this is the same strategy. So the structure type is known, but we want to do something else. So niobium iridium-3, the gold-copper-free crystal structure type, this compound has been studied. There is no superconductivity, fine, and we ask ourselves, it's possible to put a small atom like boron inside this octahedra, And my former student melted several samples, and here is the X-ray diffraction pattern. So what you see here is the mass. There are a lot of reflections. Too many reflections to say that the sample is pure, of course. But nevertheless, we found that there is a main phase. The main phase is a cubic phase, which is shifted, fine, which is shifted, which is actually very good, because the lattice parameter is larger. But there are extra reflections, and most important is the fact that there is a superconductivity at 7 Kelvin. So question is, what does superconducting this system? As you can imagine, this is a rather expensive experiment because of the iridium, but nevertheless we decided that we want to make more and more samples, and what we call it, it's just the, going through the phase diagram. So the first point is here, okay, this is my first point. Second point was here, and another point was here. This point is 113 or 131 if you wish. That one was 122, and another one was 479. And what you do, you compare the X-ray diffraction patterns, and also, and actually that's actually even more important, you compare magnetization. This is the normalized magnetization. You see it's EMU per gram. And you can clearly see that the strongest signal is here. So is it 479? Maybe. And here is the X-ray diffraction of this 479. You see that those impurity peaks now are much more, much higher, and the main phase, which was the cubic phase, is actually gone, almost completely. It's almost completely gone. We tested more and more samples, and this is the fourth strategy. Nothing is more known. And here it's a first conclusion. or actually the first question. Do we have the same crystal structure which we observed for rhodium-based compounds, 1, 2, 2, niobium, rhodium, 2b2? That paper was published 4 years ago, and this is the chiral crystal structure, non-centrosymmetric, fine, the same composition as this sample, so we thought maybe it's the same crystal structure, but it appeared that it's not the same crystal structure. From the very beginning, we knew it's not the same crystal structure, and without the help of Wei Wei Xie and her student, we couldn't move to another point, to another level. Without the help of the crystallographers, we couldn't find, or we couldn't refine this crystal structure. So the first proposed model was C2 over C, which is the space group 15. They confirmed stoichiometry, 1 to 2. They confirmed it's a monoclinic stoichiometry, but centrosymmetric. And actually, we didn't like it. We didn't like for 2 reasons. And the first reason is that we already observed very high upper critical field. For the centrosymmetric, just the typical BCS superconductors, you cannot go above the Pauli limit, which was actually our case. And second thing is that when you get the crystallographic table, what you do, you try the Rietveld analysis of your powder X-ray diffraction, and it didn't work. So we asked for the other model, and another model which came to us was the model in which the space group is even lower. It's number 9. So monoclinic, still monoclinic, and non-centrosymmetric. And that one, as you can see, worked out. So it works like that. Without the crystallographers, you cannot go to the next level. But what you do, when you get the crystallographic table, you have to go back to your powder X-ray diffraction and try Rietveld analysis. And Karolina Górnicka did this, and you can see it's pretty much what you expect. There are some impurities, small impurities, but this is confirmation of the crystal structure. How does it work? How does it look like? Well, it's complicated. It's very complicated. So I'm not going to details, but the most important point here is that we have the boron-boron dimers. Boron-boron dimers, you see that the distance between boron atoms is only 1.7 angstrom. And even more, the boron-boron dimers, they are aligned different directions. So this is the system we worked on with iridium. And you can ask me, is there any link between this 1-2-2 system and that 1-1-2-2 system with rhodium? And there is a link. The link is that we have a different stacking. Here is XY, here is XYZ. Okay, so either 2 stacking layers or 3. And that one is non-centrosymmetric, monoclinic crystal structure. That one is chiral, trigonal, of course, non-centrosymmetric crystal structure. Both are superconductors, and they have a very similar superconducting properties. Now, let's go to physics. So first is resistivity. And you can see that there is a clear transition. Great. So there is a transition to superconducting state. Then we have, we plotted upper critical field as a temperature. And of course, we finished at 9 Tesla. I will show you more points in a minute. Nevertheless, the upper critical field you can obtain from WH theories like it's about what? About 16 Tesla, which is way above the Pauli limit. For the tantalum compound, it is 14 Tesla. Here is almost 9 Tesla, so it's above Pauli limit. Magnetic susceptibility. Magnetic susceptibility shows the Meissner fraction. The transition here is very sharp. For the tantalum sample, it's not so sharp. Now we have better samples. And what is striking here is when you plot lower critical field as the temperature, in this feed, usually you just take you just take 2, okay, n equal to 2. But in this case, we must have like close to 4. It's 3.8. How much time do I have? For tantalum, iridium 2, boron 2, the power law is 2.5, so it's close to 2, but in this case it is almost 4. We don't know what is the reason of that. Actually, we observed that such a high value of n only in 2 cases, and that's one of the case. Heat capacity. Heat capacity data is shown here, so you can see Cp over T as a function of the temperature. So there is a clear anomaly, and in case of niobium-based sample, clear anomaly in case of tantalum sample. When you apply magnetic field, you can at least suppress superconductivity, not perfectly suppressed, but still you can get gamma value, which is 4.9. In this case, it's 5.2. So we can say there is no much difference between the gamma. And the Debye temperature is 274 and 230. So the Debye temperature is lower in case of tantalum-based compound, which of course is what you expect, because tantalum is heavier than niobium. But most important, and actually the most interesting feature is here. So you can see the data in a superconducting state. It's a zero field measurement, and well, still the TC is 7 Kelvin, so you can try fitting the data using different models, and you can see 2 models. One is just a single gap, and the other is just the power law. Fine. So as you can see, the power law looks pretty good. Actually, looks very good. And in 2019, so 3 years ago, tungsten-free aluminum 2 carbide was published in a Physical Review B, and there is also the power law. Okay, there is also the power law fit proposed by the authors. And well, I thought maybe that's what it should be. But the same data, okay, the same fits. So the blue one and the red one. And what I will do, I will change the linear scale to logarithmic scale. And big surprise, the power law doesn't work. Not at all. But you cannot see it. You cannot see it when you plot it as a linear scale. So you have to be very careful if you see that the power law works, the power law fit of the heat capacity works for your compound. It's good to plot it as a logarithmic, in logarithmic scale. Okay, so is it just single gap superconductor? We checked the other option, which is just S plus S wave, so 2 gaps. And the 2 gaps, here you see the 2 gap model, seems to be much, much better. But Zach Fisk a few years ago and Joe Thompson told me the same thing. You can add another gap and your fit will be even better, which is of course true. So it's not a proof that I have multi-gap superconductor. We proposed it's a multi-gap superconductor based on the density of states calculations and so on and so on. But I am not convinced it's a 2-gap superconductor, especially because 3 weeks ago we published a paper in PhysRev B showing the muon spectroscopy that actually 1 gap is much better fit. Okay, let me go back to this picture. 2 gaps, 2.42 millielectron volts, 9.1 millielectron volt, the same values taken for the fit, and this is that line. It doesn't work. It doesn't work at all. So most likely, niobium iridium 2B2 is a single gap superconductor, unfortunately. However, oh, by the way, here is also the high magnetic field data collected in Tallahassee. So you can see that it's a linear, actually, behavior up to pretty much 16, 17 Tesla to the very low temperature, 0.32 Kelvin. Okay, so comparison of those 4 superconductors comes in this slide. So you have niobium, iridium 2, boron 2, tantalum, iridium 2, boron 2, and the same but with rhodium. TC is lower for the iridium compounds, 7.2, 7.6, 5.1, 5.8, and so on. So upper critical field is always above the Pauli limit. As you can see, 16 Tesla, 13 Tesla, 15 Tesla, 10 Tesla, 18, 14, 11, or almost 12, and almost 11. The anomaly of the heat capacity, so the heat capacity jump is like almost free, strongly suggesting strong coupling superconductivity. For the tantalum iridium 2B2 is pretty low, it's the lowest one, but still above the BCS expectation. Here is 1.6, 1.56. I am summarizing what I'm going to say. Why are the non-centrosymmetric superconductors important? And is the lack of center symmetry enough to be excited about them? Well, it is not enough. It is not enough. You need also the spin-orbit coupling effect, which should be strong to observe interesting physics. And there are not many. Actually, there are only 2 models or systems in which you can tune spin-orbit coupling. This is the first one. And this is the oldest one. Lithium 2, palladium 1 minus X, platinum X free, and boron. So replacing palladium by platinum, you just make the spin-orbit coupling stronger, and you, at least we hope, or they hope, that this spin-orbit coupling will introduce the spin triplet superconductivity. There are some controversy, but I am not going to details. Another system, rather recent system, is molybdenum or tungsten free aluminum 2 carbide. And again, tungsten is much heavier, so spin-orbit coupling should be stronger. Molybdenum is much lighter, and you expect that the effect will be much stronger, as I said. So far, as far as I know, there is no studies published, with the solid solution of the compounds. So we have 2 systems, and this is another one. Those 4 new superconductors, Bob Cava and also my lab reported or just discovered. Niobium rhodium 2 B2, tantalum rhodium 2 B2, that's the chiral structure. Niobium iridium 2 B2, tantalum iridium 2 B2. This is a monoclinic superconductivity, monoclinic crystal structure type. For niobium rhodium 2 B2, the group from Warwick University from the UK, they already published the paper showing that there is a single or maybe multi-gap, that's the conclusion, tested by, as I said, by muon spectroscopy. A few weeks ago, the Barhan Das published a paper showing that in niobium iridium 2 B2 there is a single gap superconductivity. Tantalum rhodium 2 B2 was tested again by Warwick group, and they found multi-gap superconductivity proved by muon spectroscopy, and we don't know about this one. We are waiting. Maybe soon we will be able to tell you about tantalum iridium 2 B2. But when you take a look on this picture, you realize that that one is actually the heaviest one, right? Because you go from niobium to tantalum, and you go from rhodium to iridium. So all the elements that are important for the superconductivity are there. And we hope that one will be also multi-gap superconductor. Okay, so almost the last one, the acknowledgements. I would like to thank Karolina Górnicka, who was responsible for this project, Michał Winiarski, who is part of my team. We also worked together with Shintaro Ishibata from Osaka University, Bob Kawa, Princeton, and Wei Xie. Now she's at Michigan State University. We have also a big support from theorist Professor Bartek Windlocha from AGH University. And let me finish with this one. I guess there are no participants from Ukraine on here, but not many people actually. But let me say that if you do not read it, it means that we are with you. We do support the Ukrainians. We are looking for students from Ukraine, PhD students from Ukraine, and I strongly suggest that you do the same, because it's really bad time for them. Thank you very much for your attention.
Okay, thank you for nice talk and being on time. So this talk is open to questions. I think there is already one over there.
Here. You were expecting something online.
I'm trying to go back to this.
Okay. Many thanks for a nice talk. I fully agree with your conclusions, because we have been studying also some non-center symmetric superconductors, and we unfortunately found that it's a necessary condition for finding something interesting, but not sufficient. So sometimes we find, but just to further to comment on your results, there is also an advice, perhaps, that we have seen that we have done experiments with exactly as you did, with changing heavier and heavier elements, and we didn't find any effect. Why? Because we realized a posteriori, which means later, that by DFT calculations, these were not influencing mostly the Fermi level. So you should check before who is the major player in the Fermi level. This is a good advice, I think, because sometimes one expects something and finds something else. Now, a very general remark or question. Have you considered, because you showed how you try to find interesting materials, have you considered this, how it's called, new machine learning? They are developing a lot of strategies to find what might be interesting. Have you considered also this? Or?
Yes, of course. And many, many times. And I also got a lot of emails from theorists that must be a superconductor. But believe it or not, none of them was true. But the other way, when you find a superconductor and then you send the information to the theorists, there is always the reply, of course it's supposed to be a superconductor.
Okay, so any other question over there?
About your measurements, penetration depth measurements, you said that you had only one gap. Do you have some ideas about the symmetry of the other parameter in the material?
I'm afraid that I can just send you this paper so you can check details of the muon spectroscopy. I will be happy to do it.
Okay, just another thing about your critical field measurements. Do you have some ideas about the direction of the field, about the crystallographic planes or something like that?
Well, I would love to grow crystals, and we tried a lot of times. But the problem is that this is so complicated system that you cannot grow the crystals, so far, at least so far. And unfortunately, it is also expensive because of the iridium. So we are trying, but so far, what we can get polycrystalline samples, and believe or not, it was also very difficult. There is a very, how to say, not so wide or very, very, the temperature region in which that compound actually can be formed is very low, okay? Because, well, you see, it's just 1, 2, 2. So I'm pretty sure that many years ago, before I was born even, people tried to arc melt it. But you cannot control temperature of that sample during that process. Now we know that the samples cannot be obtained by just simple arc melting. And that's why we found them. We just made them using the solid method. Okay.
Okay, so any other question? Then I have a very quick question. So one time you showed upper-critical field as a function of temperature, and then also the one that you measured at high magnetic field.
Yes.
So it looks like it shows linear behavior all the way to 0 Kelvin. I think that's very unusual. Like possibly indication of maybe plus superconductivity or maybe multi-gap superconductivity. So like, have you thought about the possibility based on the upper critical field measurement?
Can you show? I cannot use it actually, for some reason. Okay. Yeah, exactly. So can you go back? More. Stop. The other way. Okay. Thank you. So thank you for this question. So I actually should explain what we have here. So this is the Ginzburg-Landau fit. Just a typical fit, just showing that it doesn't work. That's the fit with the power law. And the power law is like 1.1 as far as I remember. And now, going back to your question, why it's so linear? Well, one of the explanation based on the the models Ruslan Prozorov studied in some time ago is that it's just the multi-gap superconductor. Just the multi-gap superconductor. We don't know. Actually, we showed that this is not the multi-gap superconductor, but there might be also some anisotropy effect. From the other hand, it's not a crystal, right? So it's open question. But nevertheless, this is what we observe. For us, the most important is the fact that the upper critical field is actually even higher than obtained from the WHH theory.
Okay, thank you. And I think before would like to give him certificate of excellent presentation on behalf of the organizer. Okay.
Thank you very much. Thanks a lot.
Thank you.
Thank you.
And the last talk is by Professor Masumdar from Shiv Nader University, India. His talk will be through online. Okay, if you are ready, then I think you can start.
Hello, am I audible?
Yeah, I think
Hello.
We can hear you, but we can
Okay,
see
okay.
your
Let me share
slide
the
at all.
slides.
Okay.
Is the slides visible?
I can see your slide now. Can you put it? Okay, I think it's good now.
Okay, okay, fine. Okay. Let me get the pointer. Okay, okay. Let me then, with your permission, may I start?
Yep. Please go ahead.
Okay. 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 Thank you very much. So, first of all, thank you very much for allowing me or giving me the opportunity to present my research work in this in such a nice conference. And unfortunately, I was not be able to present physically, but nevertheless, it was also good to kind of listen to your talks and all these things. Okay, so to start with, as you can see, rather a big title, evidence of spin liquid behavior in the extended quantum critical regime of pressurized cerium, palladium, aluminium. So in the title itself, you can see that there are these two terms that are that has to be kind of addressed before for the sake of completeness, because I know that there are several most of you are kind of aware of the ideas of spin liquid or quantum criticality. Okay, but for the sake of completeness, I would like to say a few words on that. So, to start with, let me start with the idea of quantum criticality. So before going to the idea of quantum criticality, let me first discuss about the idea of classical criticality. So what is what happens in case of a classical magnetic second order phase transitions? Okay. So of course, I'm not going to go to this sort of second order phase transitions because I'm not interested in that for the time being, of course. But of course, I am going to talk about for a system on a serious note where there is a classical second order magnetic phase transitions. So as you know that for a classical second order magnetic phase transitions at higher temperature, you have thermal fluctuations that are dominating over the exchange interactions between the electrons. But below a certain classical critical point, the system ordered to a particularly magnetically ordered state where the exchange interaction between the electrons is actually winning over the thermal fluctuations, right? And just above the classical critical point, you see some sort of critical regime. Okay, so in that regime, you would expect that all the physical parameters, as for example, specific heat, susceptibility, relaxation rate, in evaluated from NMR or MUSR, that all diverges towards the ordering temperature. Okay, and all the kind of diverging properties, so they follow some sort of power law behavior. And we know that these are several power law behaviors, and we also know that there are also several universality classes. Depending on the different universality classes, you would expect different sort of power laws. Okay, so these are the things that is rather well established. Theoretically, it has been proposed. Not only that, experimentally, there are several examples of such kind of second order magnetic phase transitions where you see critical behavior just above the critical temperature. So now let us little bit start discussing about quantum phase transitions. So in analogy to the classical phase transition, in case of quantum phase transition, suppose you have a tuning parameter, as for example, pressure or magnetic field, of course, non-thermal tuning parameter. So if you have a system that has a long-range magnetic ordering at a finite temperature, if by the application of the tuning parameter, if you are able to suppress down the ordering at t equal to 0, that point is called as the quantum critical point. And around the quantum critical point, you would expect strong quantum fluctuations. And if you increase further, then you would expect some Fermi liquid behavior and the suppression of the quantum fluctuations. Okay, so just to tell you that what is the sort of interesting behavior that one may expect in the region around the quantum critical point. So we all know that for any sort of phase transition, at the phase transition temperature, your spatial as well as temporal correlation length diverges, right? So now the thing is that if we consider that the energy associated with the temporal order parameter fluctuations is h over tau, and this tau is nothing but the spatial correlation time. So we know that for the classical case, where there is a classical second order phase transition, second order magnetic phase transition, we know that the ordering temperature is finite, that is non-zero, of course. And as I just mentioned, that the tau that diverges to infinity. So we know that for a classical case, the energy of the temporal order parameter fluctuations are much more less than that of the thermal fluctuations. So in case of a classical magnetic phase transition, we can of course neglect the impact of these temporal order parameter fluctuations or temporal correlation length. Okay, but on the contrary, in case of a quantum phase transition, we know that the ordering is at 0 Kelvin, right? So here it is just the opposite, that the energy for the temporal order parameter fluctuations are higher than that of the thermal fluctuations. So that sort of incorporation of the effect of the temporal order parameter fluctuations dictates the dynamics of the system. And you get different sort of universality classes compared to the classical second order magnetic phase transitions. And as a result, definitely in case of quantum critical points also, you would expect that all the physical parameter would be diverging towards t equal to 0. But still, as I just mentioned, that because of the effect of further temporal correlation length divergences, the critical exponents are rather less explored, or those are not that much known compared to the classical magnetic phase transitions. So these are one of the important points for dealing with, or this is the reason for which people have been discussing about quantum criticality quite a while. And not only that, on that point, because of the presence of these critical fluctuations, you would expect some non-Fermi liquid behavior. Okay, and of course, not only this, but also people have seen that there are some situations, there are some systems where the tuning, because of the tuning, before reaching to the quantum critical point, some system shows superconducting behavior as well. And of course, those superconductors are mostly, or I would say all of them are sort of unconventional superconductors because of the proximity to the magnetically ordered state. Okay, so these are the important ideas or important aspects of studying quantum criticality. Okay, so now the thing is that we now understand what is sort of quantum criticality is. So now the question is that by what are the things or what are the ingredients to like really see a quantum criticality in a particular system. So as I told that then there must be some competing interactions that has to be present in the system in order to achieve this quantum criticality. Okay, so we'll be discussing mostly about the systems that are kind of dealing with 4F-based heavy fermionic system. So in this sort of systems, what happens is that at rather low temperature, the 4F moments kind of couples with the conduction electrons, and not only that, but they'll sort of form a single type of state, many body singlet type of states, and as a result, what happens is that the conduction electrons quenches the moment of the 4F moments. Okay, and as a result, you can see that at a further lower temperature, there is no long-range magnetic ordering, but the system is kind of showing some Fermi liquid type of heavy fermionic state. Okay, so this is nothing but the Kondo interaction, and you can easily imagine now that because of the quenching of the 4F moments, you would expect that in that case, dominating the Kondo interaction is you have a lesser chance of having some long-range magnetically orders. Right. So, and along with the same, at the same time, we have also other kind of interaction that is called RKKY type of interaction, where both of the 4F moments interact via this interaction. Okay, and that actually promotes long-range magnetically ordered state. So now we see that if this 4F based heavy fermionic system, they have these two interactions, both are sort of competing with respect to each other. So thus there is a finite chance then you can end up with a quantum critical point if you sort of tune these two type of interactions. And indeed, it was a kind of quite well-known phase diagram proposed by Doniak. So here along the x-axis, this is nothing but the exchange. It can be the RKKY type of exchange. It can be the Kondo type of exchange. And along the y-axis, you have the temperature scale. So you see that while the J is rather small, the Kondo temperature that follows, that is actually, I mean, the Kondo temperature is subdominant, or that is not been able to dominate over the RKKY interactions. So as a result, when the J is rather small, you would expect there would be a long-range magnetic order. On the contrary, if you increase the J values, then you see that the Kondo temperature or the Kondo energy scale is increasing or is dominating over the RKKY type of exchange interaction. And as a result, you can expect that there would be a reduction of the long-range magnetically ordered state, and you may expect some sort of quantum criticality. Okay, so the point is that then it is really interesting to deal with this 4F-based systems because you have the chance of getting this quantum criticality. Okay, so now let me kind of discuss another way by which you can suppress down the ordering. Okay, that is nothing but it is called as frustration. So why it is called as frustration? So so you can consider that, let's suppose that there is one triangle, and each corner of the triangle there are Ising spins. Okay, so Ising, by Ising I mean is that the spin can be either up or down in the direction. Okay, and if you consider that there is a antiferromagnetic type of exchange interaction between the spins, then you see that the first spin and the second spin, they are aligned antiparallelly. Fine, no problem. But the third spin, it is not possible for the third spin to orient itself in a particular direction. So thus the third spin is sort of frustrated. Okay, and this leads to huge degeneracy of the ground state. So you can kind of construct different type of spin structure, and in all the spin structure, you have the same energy. Okay, and that leads to actually a different states of matter, and that is nothing but spin liquid state, where the spins are highly correlated with respect to each other, but there is no sort of spontaneous symmetry breaking down to theoretically down to t equal to 0, and the spins are rather dynamical in nature. Okay, so of course this is also an exotic state of matter. So now we see that these are the several interactions that can be incorporated in a system. So what is then is going to happen? So my point is that suppose you are dealing with a metallic system, 4F-based metallic systems, and not only that, but also the 4F moments are actually nicely arranged in a frustrated lattice. Okay, so like frustrated systems are mainly been discussed in insulators, but it is also very much interesting, as you can see, that if you have a frustrated lattice where the the magnetic moments are arranged in a frustrated lattice, so the effect of frustration will be there. Not only that, the effect of Kondo interaction will be there, and also on the top, RKKY type of interaction will be there. So things are, of course, much more rather complicated. Okay, so now the question is that if you have this sort of situations, then and you have the kind of this sort of different interactions are present, then would you expect that the phase diagram that I have shown, the genetic phase diagram for quantum criticality, would remain the same? So, so that was actually the question with which we have started kind of discussing or thinking about this sort of problems. Okay, so now the thing is that theoretically it was been proposed by the group of Professor ICQMT. So they kind of proposed this sort of interesting phase diagram. So along the y-axis you have quantum fluctuations, which means that along the y-axis, if you kind of go along the y-axis on the top, more the frustration, you are kind of having more quantum fluctuations. Or reduced dimensionality can also sort of incorporate more quantum fluctuations. And along the y-axis, along the x-axis, you have the Kondo interactions, but in the unit of RKKY type of interactions. Okay, so now you see that there are different type of phases, not only phases, but different type of quantum criticality has been proposed, okay, by them, and that includes spin liquid state. So as I told, that was actually our intention, that if we start with a system, 4F-based systems where the moments are arranged in a sort of frustrated lattice, and then what is going to happen? And if the system is tunable, if the system is tunable, because at the end of the day, we are like looking for the quantum criticality, right? So that was actually our intention, and we were looking for some systems which can be a good candidate material for looking this sort of issues. And we have found out that this particular system, cerium, palladium, and aluminum, that was there for a while. And if you see the structure of the system, you see that the cerium moments are arranged in a Kagome type of lattice. You can see that this Kagome is nothing but sort of cornered shared triangles. It is highly frustrated lattice, but of course the Kagome structure for this particular material is not perfect Kagome, but of course some sort of distorted Kagome. But still it has some frustrated magnetic structure and frustrated arrangement of the cerium moments. Okay, of course this system is metallic, and the other thing that we want is that the system must be tunable. And we have checked and we have found out that, of course, if you apply pressure, you can see in the middle, you can suppress down the ordering, maybe around 1.1 GPa. Not only that, but the chemical pressure also suppress down the ordering. Even magnetic field also suppress down the ordering, going through different type of magnetically ordered states. Okay, you can see that the parent compound without the application of magnetic field or pressure, it shows some ordering around 2.7 Kelvin. Okay, some long range magnetic ordering. But so that is why we have chosen this system. It has the tunable, so it is highly tunable by different means. Not only that, the cerium moments are arranged in a nicer Kagome type of frustrated lattice. Okay, so that's why we choose this particular system in order to address the problem that we have mentioned. Okay, so before going to this particular system, let me tell you one more thing, is that in a normal insulating system, where you do not have any Kondo or RKKY type of interactions, there, the definition of degree of frustration is defined by this parameter, as you can see. So it is nothing but the ratio of the Curie-Weiss theta over the ordering temperature. Okay, so so usually in a normal unfrustrated system, you would expect that these are almost would be similar in magnitude. Okay, but in case of frustrated system, the exchange interaction is much more, but the system is unable to go to a long range magnetically ordered state because of the effect of the frustration. The ordered state comes at further lower temperature. So more the difference between the Curie-Weiss theta with respect to the ordering temperature, you have more degree of frustration. Fine. So that is that particular description or that particular definition was rather very much well celebrated in terms of in the case of insulators. But you know, as I told, that we are dealing with in metallic system, because in metallic system at higher temperature you have this Kondo, you have this RKKY, there are others, all these sort of interactions are there. So there you cannot sort of use the same definition of frustration. Okay, so one of the paper mentioned in this kind of defined by Oliver and co-worker from Max Planck Dresden. So this is actually the data for cerium, palladium, aluminium at ambient pressure, susceptibility versus temperature curve. So if you just consider the data that I have denoted by this dashed red one, that the data has been taken at the field of 0.01 Tesla. So you can see that there is a hump at around Ts, defined by Ts, the hump, the temperature at which the susceptibility is showing the hump, and Tn is defined by this point. Okay, so now what they kind of have seen is that Ts is actually the point at which they have seen that there is a high entropy accumulation above the long range ordering. And we also know from our basic understanding that in a frustrated system, you would also expect, you are always going to expect that there will be a high entropy accumulation above the ordering temperature because of the presence of frustration. So what they told is that instead of this Curie-Weiss theta in a metallic system, you can consider that this Ts might be to some extent dictating the fact that where the system would have ordered if there would not have been any frustration. Okay, so that's why they sort of defined the fact that the temperature region between Ts and Tn it is some sort of spin liquid type of behavior, as similar to the example that I have given for the insulator in the left hand side. Okay, so this ratio is actually rather giving you the idea of this frustration, degree of frustration in a metallic system. Okay. Okay, so keeping that in mind, let us proceed further. So as I told that we are going to discuss about the quantum criticality in this particular system. And in order to know what is the quantum critical fluctuations, you have to employ some technique which has the capability to show dynamical behavior. And muon spin relaxation or rotation technique is one of the important technique in that aspect. Okay, because of the limitation of time, I won't be able to say you a lot of things regarding muon spin relaxation technique. technique or MEOSR technique in short, but quickly I will be going through one slide that will give you the overall idea that what it actually is. Okay, so just consider that these muons are spin half particles. So as soon as I tell you that muons are spin half, you can easily recognize that it is very sensitive to the local magnetic field. As soon as the muons that are being placed in the interstitial position of the crystal structure, it's if there is a long range magnetic ordering, it sees the local magnetic field produced by the local moments around it. Okay, and as soon as it sees the local moment or local field, it starts to precess. And this precision frequency is nothing but proportional to the order parameter. Okay, so now this is the typical MEOSR data, this asymmetry as a function of time. You see that there is a nice oscillations. The data has been taken below the ordering temperature. So this oscillation, if you take the Fourier transformation of it, it is going to give you the idea about the local magnetic field. Okay, this is nothing but the precision frequency. Okay, so if you track that, you will be able to figure it out, the order parameter. Okay, so now forget about the order state. In the paramagnetic state, you only see relaxation behavior, and this lambda denoted by and that is nothing but 1 over T1. That is actually, as you can see here, is probing the electron spin dynamics in the paramagnetic state. Okay, so this lambda over T, this parameter, is nothing but is proportional to the imaginary part of the dynamical spin susceptibility. So essentially, if you plot lambda over T as a function of temperature in the paramagnetic states towards the ordering temperature, you would expect that it is also going to follow some power law behavior. Okay, so essentially this is very important in order to understand the data that I am going to show you in the upcoming slides. One more thing is that there is another sort of experiment that can be done by MEOSR, that is called weak transverse field experiment, by which you can get an idea about the long range, about the ordering temperature. Okay, I'm not going to the detail of it. Okay, so now let us little bit discuss about the data on cerium, palladium, aluminum at ambient pressure and at zero field. Okay, so as I told you in the inset, it is clearly shown that in the long range order state, it shows some oscillations, and in order to deconvolute the spectra, we have used certain functions, and that tells you that there is an incommensurate magnetic ordering, and that is consistent with the neutron scattering experiments. Okay, nothing that much important to say. Okay, so let us concentrate on the temperature dependence of lambda over T. As I told you, in principle, it should show some power law behavior towards the ordering temperature, and indeed it is more or less the showing some power law behavior for this cerium, palladium, aluminum at ambient pressure. Okay, not only that, but in order to deconvolute the spectra, we have this electronic part, and we have seen that you need to employ some parameter that is called beta, that is well known as a stretched exponential parameter, and that the involvement of beta is only was there just above the ordering temperature. Okay, so there is a characteristic temperature denoted by T star, below which we have seen that the beta values are deviating with respect to 1. Okay, and interestingly, we have seen that the T star, this characteristic temperature, is exactly at the same point, more or less, within the error bar that mimics the temperature scale of the hump in the susceptibility. Okay. Okay, moving forward. So now we will be discussing about the thing, what is happening if you apply pressure. Okay. So we have applied. Yes.
We have 5 minutes left.
Okay, okay, yeah, I'll soon wrap up. Okay, so from the weak transverse field measurements, we have carried out the sort of ordering as a function of the long range magnetic ordering as a function of pressure, and we have seen that the critical pressure is of the order of 0.92 gigapascal. Okay, so now moving forward, maybe I'll skip this. Okay, so now as I told that we have done experiments, MUSR experiment at different pressures, and these are the points, data points I have shown you for the systems which has a long range magnetic ordering. As for example, this 0.89 GPa, it is very close to the quantum critical point. You see that there is a ordering at around 350 millikelvin, and you see, of course, there is a critical divergence of the lambda over T. So now the thing is that what is happening beyond the quantum critical point? And with our surprise, what we have seen is that you can see the data taken at 1.62 GPa and 1.18 GPa, where 1.62 GPa is almost 1.75 times than that of the critical quantum critical pressure. Still, we see some divergences of lambda over T. And that actually very much surprising. That actually tells you that you have the critical fluctuations, quantum critical fluctuations that are still surviving much higher than that of the quantum critical point. Okay, and that actually tells us that this is actually the genetic phase diagram that I have discussed, and that might be associated with the fact that because of the incorporation of frustration, we have not only a quantum critical point, but we have rather a extended quantum critical phase by the incorporation of the frustration in this particular system. Okay, so we have got the microscopic evidence of having an extended quantum critical phase in this system. And as I told you that this beta, this T star temperature below which the beta starts deviating from 1, that also changes as a function of pressure. Okay, and as I told you, this beta, the T star temperature is nothing but exactly mimicking this TS, okay, below which you would expect some spin liquid behavior. So what we have so this is actually the full phase diagram. You can see I have plotted this T star from our experiment as a function of pressure, and I have also given the value of these gray squares from other paper that is nothing but the pressure dependence of this TS, where you have the hum. You see that they are quite matching with respect to each other. So indeed, this T star and TS, they are kind of leading to the same energy scales. Okay, and as I told that below the T star TS temperature scale, we have sort of correlation of spin liquid like of correlations. So we have, of course, evidence of an extended critical phase, and not only that, but also it seems that the correlation between the spins are mimicking or kind of the correlation between the spins are to some extent similar to that of a spin liquid. Okay, and in my conclusion, I would like to say that we have got the microscopic evidence, local evidence of this extended quantum critical phase with the pressurized cerium, palladium, aluminum. Not only that, below a characteristic energy scale, we have seen that the that is nothing but critical spin liquid. Okay? And thanks for your kind attention, and I am open to accept any questions and comments.
Okay, thank you. Okay, so this talk is open to question. Any question? I have a quick question. So
yes, please.
One time you showed global quantum phase transition phase diagram. X-axis is J, Y-axis being frustration, right? Where do you put cerium, palladium, aluminum in those global phase diagram?
Okay, let me.
Yeah, I think
is it this is the thing? No, is it the slide you are mentioning?
The global phase diagram. This is just Young model.
Global. Okay. Yeah.
Here, where do you put palladium, aluminum?
Yes. I would expect that maybe the kind of cerium, palladium is aluminum is around this point where my cursor is. So you have a long range magnetic order state, yes, and with the pressure you are entering to the spin liquid state.
So what happens if you apply pressure? In which direction do you think it will go? Does it go straight upward or?
Yeah, it is rather difficult to say because under pressure, I do not remember. I mean, it might be difficult to figure it out that whether the condo interactions or the condo temperature is in which direction it is going actually. So that's why I do not know whether the movement would be along the or I would say maybe on a more safer side there will be some angle. It must not be completely straightforward in the upward direction. I would say that maybe with the application of pressure the condo is also going to enhance. As a result, you would expect that there will be some angle with respect to the y-axis.
Okay, thank you. Is there any other question? If not, let's thank the speaker and then all other speakers too. Thank you.
Thank you very much. Thank you.
And I think this is the end of the session.